The popularity of enterprise digital transformation, cloud, big data, 5G, and artificial intelligence promotes the rapid development of applications such as core transactions, virtualizations, high performance computing, AI, and AR/VR, which in turn demand larger, faster, and more intelligent storage. IEEE Bangalore Section and Huawei Technologies bring to you Data and Storage Symposium, an industry flagship event connecting technology leaders across various segments of the data management and storage world. We'll hear from technology leaders, innovators, entrepreneurs, and thought provokers who are passionate about addressing impactful problems by turning ideas into solutions. Industry stalwarts and technology practitioners together will share their vision on future technologies and how they will impact our way of working and living. As is the new norm, this event is organized virtually, and we are very excited that it can bring participants from all over the world, from corporate, academia, and industry. Today's sessions will shed light on various topics across the data and storage domain. We're going to have a little bit of everything, right from storage and big data analytics, unlock the power of big data with new age data storage architecture, storage optimized for processing big data with near data processing, function offloading and pushdown, to data-centric computational storage computational architecture with function in hardware, smart NIC and DPUs for extreme low latency data access for HPC and HPDA. We'll also be covering exascale storage achieving performance and cost objectives with data lakehouse and global namespaces, and sessions on containerized and composable storage efficiencies with virtualized and containerized deployment of storage, disaggregated composable storage architectures. With that, it's time now to kick off IEEE Data and Storage Symposium 2021 Winter Edition. A few announcements before we start the event. If you are not speaking, please ensure that your mics and your videos are muted. If you are going to be speaking, please unmute your mics at the time of your sessions. If you have any questions, please use the raise hand feature or the chat box to post your questions. We will be taking questions towards the end of every session. Speakers, please ensure that you keep the last 10 minutes of your session for a Q&A session so that we can answer all the questions that are asked throughout the session. I will be giving you cues throughout the session wherever your time checks are needed. Please keep a track of your chat box so that you can get an idea of how much time is left. With that, without further ado, let me invite on your screens Mr. Bindu Madhava BS, the chair of the IEEE Bangalore section, to welcome everyone and set the context for the summit. Over to you, Bindu Madhava.
Good morning, all, and good afternoon for people who are joining from different parts of the globe, and good evening also. So, because it's a time zone difference, so greetings from IEEE Bangalore section for this important intervention, which we have sort of started this particular activity in 2020, and we intend to continue for a long time in this particular space. So I would like to, first of all, do my duty of welcoming you all for this particular summit, for the symposium. And I think there'll be, I've seen the complete program. So it involves the industry, academia, and the researchers. So the stakeholders of the IEEE will get a full flavor of all the three activities: what is happening in industry, what is happening in research, and what is academia looking into. So these are some of the things which is of interest for the technical community at large. I think with the current environmental cycle change, what is happening, which starts from climate change and which leads to disaster. And effectively, there'll be a lot of issues on the health. So this cycle of the connectivity of the change which is taking place throughout the thing calls for regular monitoring of the parameters. So whatever might be the parameters, ultimately it sort of affects some larger section of elements. I don't say persons or any such thing, because it can affect many other things also. So with the basic thing being data, and then subsequently data taking its own formats and formats, and which goes on to the storage. And today, I think there was a good start point which Anvit has sort of brought out. The exascale storage, the exascale computing is a challenge in terms of the computing paradigm which is going on. And next is how you are going to sort of archive this particular large data, whatever the measure of unit might be, and make it a useful thing by rendering onto some augmented reality and other things. So these becomes very important. So handling of the data intelligently is what is the thing which people are looking for. I think with this particular thing, we at Bangalore section would like to sort of carry it forward for a longer duration of thing. With this backdrop, I would like to sort of announce the IEEE DSS data and storage, basically, a special interest group which will be formed we'll announce it today and then subsequently take it forward. Basically the terms of reference is to look at the architectures, processing and storage and deployment. So these are some of the things which we would like to sort of discuss in this SIG. And then subsequently, we would like to sort of transform this into a platform in the coming years, where we would like to sort of have a symposiums like this, might be every quarter, and then subsequently having some sort of international conference, which will sort of bring all the people together, and we'll be able to know what is the current state of the art, what is happening. The special interest group on data and storage systems, basically what is the thing. With the founding members as so, who are the founding members, Dr. Prashant Mishra, Mr. Changappa, then Ankit Mathur, Manu Avasti, and Sanil Kumar, and Desh Bandhu Sinha. So these are some of the founding members of this special interest group, which we would like to sort of formally announce. And then subsequently, we'll have a terms of reference, what are the things we did in this particular space. So with this particular background, I would like to wish this particular symposium a grand success. And I'm happy to see that this particular symposium already has got as many as 58 participants early morning in India. And so this is a sign of sort of improvement from our last symposium what we had. So I wish the organizers all the best, and then subsequently we can review it at the end of the day how the things are happening. Thank you for giving me this opportunity, and all the best. Thank you.
Thank you so much, Mr. Bindu Madhava, for welcoming everybody and providing your insights. And thank you for also the announcement of the SIG. We will be talking about that a little more in the towards the end of the sessions. But thanks again, and thank you for the welcome notes.
Thank you.
With that, it's time now to set the context for the setting for the sessions. Sorry. And we have with us Mr. Ning Xiang Sun, Director and Head of Storage of R&D at Huawei Technologies, who will be setting the context from Huawei. Over to you, sir.
Hello.
Yes, we can hear you very clearly.
Okay. Good morning, dear speakers, attendees, friends, and colleagues. Thank you for having me. And my name is Zhang. I'm responsible for R&D of storage product line, and I'm very pleased to represent DSIV product line at this IEEE Data and Storage Symposium 2021. And data is becoming the fuel of the digital economy here. Accelerating the digital transformation of various industries is a key requirement for the digital economy and technology innovation. In this new data paradigm, and this is an urgent need for faster, larger capacity and smart storage. At today's symposium, IEEE Bangalore brings together leading researchers from industry and the academy to share judgments on key challenges and the technology trends in data and storage. We are very pleased to partner with IEEE to provide industry and academy with such a world-class technology event as DSS. Okay, for the background of this workshop, I would like to share with you my view of key future-oriented challenges and opportunities for this data and storage industry. First, new connections of the applications bring explosive data growth. The value of massive unstructured data is gradually increasing. From 1080p to 4K and 8K, the video data volume will increase by 40 times. And from 4K to 4K VR increased by more than 6 times. Huawei Global Industry Outlook 2025 predicts that 180 zettabytes of new data will be added by 2025, 18 times the amount of new data in 2018. 80% of the data will be unstructured. So the data cannot be stored. The analysis efficiency is low. So the performance is most challenging. Second, the development of diversified data applications pose new requirements for data storage performance, reliability, and cost. Production transaction data has high read-write performance, pressure, and high reliability requirements. So the digital transformation of industry accelerates. The requirement for edge data storage and processing are stimulated. Supercomputing is challenging from computing intensive to data intensive. The amount of data, types of data become larger, and the data applications become more complex. Therefore, high throughput in computing, high availability data read-write, high bandwidth, and high IOPS are required at the same time. And third, the cloud-based evolution of data center IT architecture and diversified architectures and devices will dramatically increase the complexity of enterprise data transformation, which will be magnified with the rapid growth of data. Enterprise need to dynamically allocate resource and schedule jobs based on service applications characteristics and ensure consistent service experience in multi-cloud scenarios. In this way, applications have the distributed capability of run anywhere. Unified management of IT infrastructure and seamless data and the service flow in multi-cloud environments are the core requirements of enterprises. I'm confident that today's meeting will answer these challenges. And thank you and welcome you to this IEEE Data and Storage Symposium 2021 online, and wish you have a great learning journey. Thank you.
Thank you so much, Mr. Soon, for setting the context and welcoming everybody to this, the IEEE Data and Storage Symposium. Again, here's a small memento from our side, a virtual memento from our side to you. With that, ladies and gentlemen and others, it's time for the keynote of the day. We have with us Tom Coughlin, the president of Coughlin Associates Incorporated and past president of IEEE USA. Please welcome on your screens, Mr. Tom Coughlin.
Thank you very much. Let's see. So I'm going to need to be able to share my presentation, if you would. There we go. Okay, just a second here. Whoops. Can you see me?
We can see you and also the slide. You just need to go to the slideshow mode.
Got it. Okay. I just want to make sure because suddenly, there it is. Okay. Okay. You see the presentation view, right?
Perfect.
Yes.
Yeah.
Great. Well, thank you very much. I appreciate being invited to join you again. I think I was here also last year. And today I'm going to talk to you about storage and memory for artificial intelligence from the edge to the data center. So the things we're going to cover here today is we'll talk about emerging memory technologies, especially non-volatile memories, why we need them, how that's going to lead to some changes in the way in which we do computing. We're going to talk then a bit about some of these memories to introduce you to them. We'll talk about who's making these emerging non-volatile memories, some real-life applications that are starting to show up, an outlook on where this may lead to, and finally a summary. So something really interesting is happening in the memory market. There have always been numerous alternatives to today's leading memory technologies, metaphorically, waiting outside trying to get in, but they've never had the opportunity that's recently developed. So we're going to look at 4 of these memories in particular, which are essentially metaphorically waiting at the door, while the market's dominant memory technologies, DRAM, NAND flash, SRAM, and NOR flash, have kept them out because of their lower prices. So we're going to look at why these things are changing and why the market has changed in a way that will provide opportunities for new technologies to replace their entrenched memory competition. So one of the big drivers here is that there's a lot of growth, data growth. IDC is well known for its projection of 175 zettabytes of data generated annually by 2025. Their projection says that would be up from about 59 zettabytes generated last year. And most of that data is seen to come from new applications, for instance, Internet of Things devices. And a lot of these things, be like cameras, sensors of various sorts, has the most value when it's processed real time. Now that is going to increase the need to store and process data in the device or at the network edge where you have low latency access to the content. And probably only a few % of this data, or more likely, something that resulted from that data will be stored long term. Another driver is the greater use of AI, artificial intelligence in devices at the network edge and in data centers is increasing memory requirements. In addition to the growth of data being processed, power consumption as well as latency and data rates are important considerations in future system designs. So that's leading us to look at the memory technologies that will enable handling this data tsunami. The semiconductor industry is being forced to change the memory technologies that are used, especially in embedded applications like microprocessors, ASICs, application-specific integrated circuits, and other system on chips. And that's because flash memory can't scale to keep pace with CMOS logic process advances. In particular, we're talking about NOR flash here. But it was a scaling issue initially with planar NAND flash. Planar NAND flash stopped scaling at 15 nanometers, and the industry had to spend billions of dollars to build new factories which could manufacture 3D NAND devices to continue to provide Moore's Law type cost reductions. System on chips use NOR flash, and NOR flash stopped scaling at about 28 nanometers with the adoption of the FinFET. Some sort of new memory technology is needed to support these chips' code storage requirements, which have often been kept on NOR flash. And that's suddenly providing an opportunity for some other non-volatile technology to replace NOR flash for all processes in these embedded devices below 28 nanometers. But it's not just NOR that it's heading for replacement. System on chips use static random access memory, or SRAM, to store temporary data. And static random access memory also is poised to stop scaling, or at least slow dramatically, around 14 nanometers. There's also going to be side benefits of this change. Alternative memories not only scale past the limits of established technologies, enabling making them cheaper to produce, but they are also persistent and have more balanced read and write speeds. And that's going to impact the way systems and software are configured. So we're going to discuss some of these changes during this presentation, both the hardware as well as some of the software developments. So this is a chart that a colleague and I have done a report on emerging memory technologies to illustrate the issue of scaling. It shows two lines. So this red line represents NOR flash, for example, and the black line represents a new emerging memory technology. So process shrinks have been used, and the process geometry goes from larger on the left rather, to get smaller on the right, which sort of follows the progression of time that we seem to be going to smaller and smaller process geometry. And then the vertical axis, that's in the horizontal axis. The vertical axis is a log scale of relative cost for these devices. So process shrinks have been used to reduce costs for the entire history of the semiconductor market. Process nodes, again, run along the bottom, and the relative cost is on the vertical axis. But flash memory has a problem after the 28 nanometer node, especially with NOR flash. This is the memory that these SoCs and other devices use to store the code in microprocessors, ASICs, and other SoCs. So that's causing its cost decline to cease around 28 nanometers, as the red line shows, because it abruptly goes horizontal. Even when I've got smaller process nodes, I can't do those with NOR flash, and therefore this cost doesn't reduce. So manufacturers can address this issue by migrating to a new memory technology, which can allow further cost reduction. So this black line represents a memory like that. It starts off twice the cost of the NOR flash, but when NOR flash stops scaling, it continues to scale, and therefore it eventually becomes less expensive. Although it starts off more expensive, it can then become less expensive than the NOR flash technology or another dominant memory technology. This shows how the scaling can allow you to move from one type of memory device and into new ones. So SRAM has a similar problem. Its scaling seems to slow or stop around 14 nanometers, according to presentations at a recent IEEE conference over the last few years. The cell area, which is proportional to cost, that's on the vertical axis. And the process geometry again runs along the horizontal axis, going from larger processes to smaller processes, moving from left to right. The cell area has been shrinking to keep pace with the process, but then it seems like it abruptly stopped shrinking at about 14 nanometers. In addition, static random access memory is much larger than the persistent memory candidates because it generally uses 6 transistors in order to be able to work. So this leveling off for SRAM makes it another reasonable candidate to be replaced by some alternative memory technology. So the emerging memory will increase the wafer cost over that of a standard CMOS logic wafer, which is what you use for building SRAM. But the die size for some chips are also going to be smaller, thanks to the fact that the emerging memory technology will consume a smaller space than this 6 transistor SRAM would. And most of these emerging memory technologies just need one selector or one transistor oftentimes. And so that reduces the cost of these chips and makes the design based upon this emerging memory more economical than its SRAM-based counterpart. And that could drive future chips to migrate to an emerging memory as an alternative to static random access memory. DRAM is the working memory used in almost all electronic devices, from consumer to industry to enterprise applications. Like many semiconductor technologies, it has become more difficult to continue the pace of these lithographic shrinks and increasing transistor density than it was in past decades. This figure shows the slowing of DRAM scaling since 2007, after about 37 years at running about 37% reduction annually in the size of these devices. It slowed to about 8% annually starting in 2008. To show what all this means to chip sizes and costs, I'm going to show you an animated graphic. So this is a photograph of Intel processor chip made on a 45 nanometer process. you can see two different parts of the layout here. The less regular part of the chip at the top is the logic, and the lower half with its very regular patterns is the SRAM used for the on-chip caches. In the past, the entire chip would scale with process shrinks, as is illustrated here. As a process moved from node to node, from 45 nanometer to 32 nanometer to 22 nanometer, and finally 14 nanometer, the die's area and cost would be half that of the prior generation. That would follow a very nice scaling curve. Now, this assumes that the SRAM keeps pace with the process technology, though, and as we showed in the prior slide, this doesn't happen at the 14 nanometer node. So we'll use the same chip again. Again, keeping in mind the top half is logic, which will scale in proportion to the process, and the bottom half is static random access memory, which scales less aggressively. You can see in this series that the top half of the chip gets really small towards the end and only accounts for about 20% of the total die area at the smallest process node, representing 14 nanometers. Yet the SRAM doesn't scale, resulting in a pretty large chip. In fact, the die size trend starts to level off at the end. This black line only indicates one dimension, but we're really talking about a two-dimensional object, so the difference in effective area is even larger. So the SRAM is causing the chip to be larger and more expensive than an alternative memory would be. So it makes sense then to be thinking about moving into alternative memories as we start to approach and get smaller to the limits on the conventional memories like SRAM. So the acceptance of an emerging memory technology also depends though upon its pricing. It's a key area here. To capture a mainstream market, a memory must be cost competitive against established technologies. So this cost structure can only be achieved through high volume shipments. Products that don't reach this volume must play in niches because of their higher prices. A good example of this is the Intel 3D crosspoint memory, or as they call it, Optane. This chart represents computing's memory and storage hierarchy. For a memory or storage technology to make sense in this hierarchy, it must be cheaper than the next faster technology on the horizontal axis and faster than the next cheaper technology on the vertical axis. To get 3D crosspoint adopted into this memory, Intel has to overcome a chicken and egg problem that 3D crosspoint must be cheap to sell in volume, but on the other hand, it must sell in volume to get cheap. So they've done this by, we believe, probably subsidizing the production of these chips with the hope that the volume increases and the cost drops. The same problem, though, stands in the way of other emerging persistent memories acceptance. And it's something we need to keep in mind is needed for these emerging memories to become commonplace. Now, these changes in the memory are going to cause computing to change since all emerging technologies are non-volatile. And this brings persistence not only closer to the processor, but it could eventually bring persistence into the processor itself. We're not going to talk about that today, though, but just to let you know. Development of Nvme enables new ways to access data for processing. And Nvme, which is the interface on the conventional SSDs, can be transported over a fabric called Nvme over fabric and extends this model across the network. And this basically is showing a SNIA persistent memory programming model here. And this has been developed over some time. It actually about the time that the Nvme was being developed. And you can show moving from the left to the right here, different ways to address persistent memory devices replacing conventional volatile memory. And all the way to the right, in fact, is sort of a holy grail with direct application access to the memory. In the meantime, you can do things like remote direct memory access, and these emerging fast persistent memories can enable new computing connection models in greater efficiency, but having the software support, which is what this programming model is helping to develop, is essential to make that happen. So there's a lot of excitement about using emerging memories in standard computing systems. So not only is that emerging memory attractive as a new layer in the memory storage hierarchy, but it also provides a path to interesting architectural innovations. In particular, innovations that solve data motion issues, since a von Neumann computer, the conventional computer technology, uses lots of energy and time moving data around. So these energy and time issues can be addressed by moving from this von Neumann architecture, as illustrated on the left here, to a more memory-centric approach, as is illustrated on the right. And that's led to the development of several different protocols, OpenCAPI, CXL, C6, and Gen Z, The one that looks like it's going to have the widest adoption is CXL. We'll talk a bit more about that. But these approaches are going to allow memory disaggregation by removing some memory from behind the processor. Memory pooling and sharing allow you to more efficiently use memory and storage to address new problem classes. And heterogeneous computing, which allows you to put computing closer to the memory. Specialized processors, for instance, close to the memory, allows data to be processed by a variety of these different types of accelerators. Now, this memory-centric system includes also, in addition to this CXL-based, call it FAR memory, because it's a switch-based, it has somewhat higher latency. There's still DRAM connected directly to the CPU. We'll call that near memory because it has lower latency. And this SCM memory in here, that stands for storage class memory, which just represents these different types of persistent memory. Since this FAR memory on the CXL is shared, its data path to the CPU must be arbitrated, and that adds latency. Thus, we have this term near and far. CXL is backed by a big consortium. It's a switch memory channel enabling pooling of non-heterogeneous memory with different latencies and data rates in storage boxes. And with Gen Z, they're also talking about that between storage boxes and even between racks in a data center. CXL supports memory and accelerators for resource pooling and allocation. The DDR channels continue to be used for low latency memory, at least through DDR5. That's that near memory we talked about. Now, what happens beyond DDR5 is higher data rates may drive a lower latency rather than a parallel memory interface, for example. And so let's look a little bit at that. So for memory, the industry appears to be moving towards a specific mix, divided by whether the memory is this near memory directly connected to the processor, to the CPU, or a far memory that's maybe pooled. So CXL, again, is gaining popularity for pooling this heterogeneous memory and also combining that with the accelerators. Near memory, that's this memory directly connected to the processor. DDR is a traditional way, and LPDDR for mobile device, etc. Should continue to be used for smaller near memory systems, at least through DDR5. High bandwidth memory is another approach, which provides more bandwidth in DDR, but it's less flexible and more costly. It involves stacking a whole bunch of DRAM wafers and then have massive number of interconnects directly to the CPU. There's another technology out there. It's called Open Memory Interface. It's currently used in IBM's power processors and certain FPGAs. So let's take a quick look at these near memory interfaces compared against each other. And this chart illustrates the operating spaces for these near memory interfaces. DDR4 and 5 are shown here, high bandwidth memory, and also this open memory interface. So DDR provides a satisfactory solution for near memory in PCs and smartphones. But on the other hand, if you're in high-end servers and accelerator cards, it doesn't give you the same kind of performance that you might want. Many accelerator cards today use high bandwidth memory because of this high bandwidth, especially if they can operate in limited memory space that you can get with HBM, with high bandwidth memory. That's HBM. There's stacks of DRAM chips. They have about 1,000 to 2,000 parallel signal paths. It improves performance, but the processor and the high bandwidth memory have to be very intimately connected. And it's an expensive process to be able to stack all those wafers and connect them together. So it's used in applications that accept a significantly higher price in return for its very high performance. Although high bandwidth memory is a help, it's considerably more expensive than standard DRAM. It's available in stacks no more than 12 chips, so that's why it has this lower capacity memory arrays. This OMI uses existing high-speed serial signal PHYs with a custom protocol to connect the processor to its DIMMs. And these are differential DIMMs. They're made of standard low-cost DDR DRAM and an OMI transceiver chip. It can provide near high bandwidth memory bandwidth and a DDR-like capacity and price. So it's an interesting consideration for these near memory opportunities. So we talked about interconnect software. We talked about the demand drivers. Let's look at some of these non-volatile memories. They're going to remake the ways that we do computing. There are many emerging memory types that are vying to replace NOR flash and also some SRAM applications. They have some very similar attributes. They have a small single element bit cell that promises a scale smaller than the current technologies to support small, inexpensive die and also 3D stacking, especially cross-point type stacking, not like the NAND flash. They also promise to be easier to use than flash memory by supporting write-in-place And they don't do a block erase, and so they have more symmetrical read and write speeds. And they're all non-volatile or persistent. Data doesn't disappear when power is lost, so they can all be used as a persistent memory. New memories are necessary for Moore's law scaling to continue. Those include ferroelectric, RAM, FRAM, magnetic random access memory or MRAM, resistive RAM, and phase change memory. The example is Intel's Optane memory. So let's talk a bit about these individual memories. MRAM's already shipping, but relatively low volumes today. Over the history of the technology, Everspin over a decade, has shipped over 12 million standalone MRAM chips. Most of these are small buffer and cache memories, non-volatile buffers and cache. The company has a partnership with GlobalFoundries, who's building 300mm wafers both for Everspin's use, but they're also offering MRAM to other customers for embedded memory applications and system on chips. So we've listed some high-profile applications for Everspin's MRAM on this sheet here. Another company, Renesas, is shipping an MRAM chip that it inherited through its acquisition of IDT. Other foundries now offer an MRAM option to their system on chip clients. They include GlobalFoundries, TSMC, and Samsung. Phase change memory is another technology that's shipping in volume. Most widely known of these is Intel's Optane memory. It sells that both in SSDs and DIMMs. And actually, you could say that there's a history of this that Gordon Moore actually wrote, well, there was a product that was introduced by Intel in 1970. Gordon Moore was actually involved in it, which is, I think, a 256K bit phase change memory device back then. So they've had this in development for decades, or phase change memory technologies for decades. Their first Optane SSDs, Nvme, shipped in 2017. Their first DIMM devices shipped at the end of the following year. Both are currently used in storage systems and other computing applications. Intel, so that's a bit about the phase change there. Resistive RAM is our third technology, is also in production, but in a relatively quiet way. It's been shipped by Desto, now part of Dialog Semiconductor, since 2013. Dialog is licensing its correlated bridge RAM memory technology to GlobalFoundries to be offered as an embedded non-volatile memory option on its 22FDX platform in the future. There's another company called Surfy Labs, which is a spin-off from ARMS, that is developing and licensing new types of non-volatile memories based upon correlated electron materials, as well as a ferroelectric device, and those are joint development projects with Symmetrics Corporation. Other companies currently are shipping resistive RAM into both commercial and military aerospace applications, and leading foundries are supporting resistive RAM as another alternative to embedded NOR flash. Finally, the oldest emerging memory technology is ferroelectric memory, or FRAM. Now, this technology predates the development of the integrated circuit in 1957. The photo on this slide, which was published by Bell Labs in 1955, shows a single SBT crystal with vertical and horizontal metal traces that can be used as a non-volatile memory. Also, from the perspective of unit shipments, FRAM has been shipped more than all other emerging memory technologies combined, having been found its way into over 4 billion chips. It's most commonly used in RFID cards because of the extraordinarily low write energy requirements, and can actually write it using harvested energy from the interrogating signal. Until recently, ferroelectric RAMs were based on unfriendly materials like lead and bismuth. But in 2011, NAM Lab in Dresden found that the crystalline form of hafnium oxide, which is a common high-K dielectric used in the semiconductor processes, can have strong ferroelectric properties. So that's created new life for ferroelectric memory devices. And besides, hafnium oxide is a material commonly used in fabs. People are much more comfortable than working with materials based on lead or bismuth, like the older ferroelectric RAM devices. There also have been people doing interesting things with this hafnium oxide with DRAM technologies, for example. Now let's look at who's making these emerging memory technologies. Leading foundries, we mentioned before, those with processes finer than 28 nanometer, now offer emerging memory technologies to their customers. They include TSMC, Samsung, GlobalFoundries, UMC, and others. They offer spin tunnel torque MRAM today, which is often being used for this NOR flash, and higher level SRAM cache replacement. There's another that's spin tunnel torque STT MRAM. Spin orbit torque, or SOT MRAM, is being faster with using lower energy, It's actually being seen as replacing even more SRAM, as its performance is closer to that of the highest speed SRAM. So we see replacements possibilities in NOR flash and SRAM, possibly even some DRAM as the price gets lower. Other companies are offering resistive RAM and ferroelectric RAM. Let's look at some real life applications coming out of these foundries in particular using these emerging memory technologies. This is a block diagram of Ambic's 4th generation Apollo system on chip. It serves as both an application processor and a coprocessor for ultra-low power battery-operated IoT endpoint devices. If you look at the lower left corner, you will see the system memory subsystem, which is made of MRAM and SRAM. So the chip pairs a 2 megabyte MRAM with a 1 megabyte SRAM. Another device that's shipping with embedded MRAM is made using memory technology by Nvme, which is an MRAM intellectual property house. It's being used by NASA for distributed computing in space, where the latencies can be very high. They're talking about neural network type devices that can make decisions in space. MRAM is less sensitive to radiation than flash or DRAM, and therefore it makes a lot of sense to use in those type of environments. MRAM is also being used in Sony's GPS receiver on a smartphone, which can be found in Huawei's GT2 smartphone. It's actually built on Samsung's Foundry's 28 nanometer FDSOI process and includes 8 megabits of embedded MRAM. So there's other emerging memory devices that are shipping in volume today. They include an MRAM microprocessor from NXT, phase change based microprocessor from ST Microelectronics, and ferroelectric random access memory device based microprocessors from both Texas Instruments as well as Fujitsu. Now, with all of these devices coming online, my colleague Jim and I do a report on emerging memory technologies, and so I'm going to show you our latest developments on the outlook for this market. This again comes from our recent report called "Emerging Memories Find Their Direction." And by the way, Jim, I think, is going to be the next speaker, or a speaker following me at this conference. And this shows that the total emerging memory market, which here we're modeling by MRAM plus 3D XPoint, could exceed $44 billion by 2031. The chart shows how petabyte shipment growth could drive that number. We're comparing current and projected capacity shipments for the next 10 years for emerging non-volatile memory technologies, here represented by MRAM and 3D XPoint, versus DRAM and NAND flash. And you have to realize this horizontal axis of petabyte shipped is a log scale. So we don't see that 3D XPoint or MRAM are seriously taking away market, are replacing DRAM or NAND flash, although they will have an impact on them in that time frame. Now, the assumptions here are that 3D XPoint's adopted widely by Intel customers and Xeon servers. Embedded MRAM replaces most SoC NOR and SRAM, and that MRAM has strong appeal for artificial intelligence applications. And this chart on the MRAM includes both standalone as well as embedded technologies. So, in summary, NOR flash and static random access memory have stopped scaling. DRAM scaling has slowed. New non-volatile memory types are there. They will get there. They're there, and they will be able to fill the void from these other memories. This will lead to whole new memory-centric computer architectures. Could potentially lead to persistent memories replacing volatile memories everywhere, even potentially in the long run registers in the computing device themselves. That's going to change the whole way we do computing. The storage and memory hierarchy itself will also change. And there's 4 leading candidates for these emerging memories that could make this impact. They're magnetic random access memory, phase change memory, resistive RAM, and ferroelectric RAM. And the leading foundries are already supporting these new memory technologies. They're in use today, just starting to come out, and products, especially some embedded products with AI inference capabilities, etc. And MRAM and the phase change memory revenues, we believe, if they follow these trends we projected, could exceed $44 billion by 2030. And with that, here's just our report here that it's now available. It's a 230-page report, 36 tables, 155 figures. If you're interested to find out more about the report, you can look at both my site, tomcoughlin.com, or on the objective analysis site, which is Jim Handy's site. Finally, here's some references for the presentation today. And I want to thank you very much. And I think we may have some time for questions. I'll be glad to take some.
Thank you, Tom. We do have a couple of questions. Ankit, over to you.
Well, thank you so much, Anvit, and thank you, Tom. It's always a pleasure listening to you and your deep analysis into this field. So let's get to the questions right away. And well, one of the questions, and that's from Lokesh. Why Intel stopped manufacturing consumer NVMe Optane SSDs?
Yes, that was earlier this year that Intel stopped manufacturing the consumer SSDs. I believe there is one that they're still supporting, which is a combination of conventional NAND flash with Optane memory. So there is one product there that I think they're still selling. I think they did not get the kind of market results that they wanted to get with the consumer NVMe SSDs, and that's why they quit manufacturing them. They're still manufacturing them for data center and enterprise type applications.
Okay, and here's another one. So you presented a graph and it's looking amazing, as well as it points to like stark reality. The graph where you show that beyond the 14 nanometer manufacturing process, that SRAM actually holds up bulk of the space, and rest of the compute logic, the processor itself, is still scaling down. But then also, as per the slowing down of Moore's law, or maybe stopped, should we say, like even the processing components would stop scaling at some point.
Mm-hmm.
So maybe SRAM showed up on the show early, like it's not scaling down. But then what do you see as where would the industry go to? What are the technologies that are going to replace? You talked about SRAM, but how about the compute side? Because that's going to hit the block as well.
The compute side. Well, there's a whole nother, that's a whole different talk, I think, talking about the compute side. I think one of the things that's going to happen is that at the same time that our scaling starts slowing down for compute, that we're also having greater demand for data that needs to be computing. So some of the things that are being developed to deal with that are people are moving to these memory-centric compute models, offloading CPUs to special purpose processors that are closer to the memory or the storage is one of the things. There's also trends going on with heterogeneous compute. That's some of the heterogeneous computing, but they're also talking about heterogeneous integration, where they actually stack chips on top of each other, including memory as well as logic chips and things of that sort. That's another trend that's going on. A little bit expensive, but there's applications where the space constraints may require that. They're also starting to break down the chips and focusing on the more expensive and harder to do small lithography on specialized parts of the chip. So that's where this idea of these chiplets come from, where they break up the chips, different processes used for different types of applications, and then they put them all very close together and they operate like a standard chip, but it's actually a bunch of chips. Now, in addition, and in fact, there's another IEEE conference that was going on yesterday and today, which is new ways in which we can be doing computing. That includes things like quantum computing. It includes various thermodynamic computing models, stochastic computing. They've got reversible computing, approximate computing. There's a whole bunch of technologies that are being developed of new computing models. And those may be better than our conventional processes for certain types of problems. So I think what's kind of interesting, we're kind of getting into a time when there's enormous interest in new technologies, both on the compute as well as the memory and other sides of things, in order to be able to continue to advance and to meet the human needs. So it's a very creative, a very interesting time. I think we're going to end up out of this with a greater variety of ways in which we do compute, which we store information and even move information around than we had before that. So it's kind of a Cambrian explosion, if you will, of compute, networking, memory and storage technologies that I think will come out of this. It'd be 10 years from now, we are likely to be doing things in very different ways than we do them today. And certain problems will be solved by special processors that are not good for other types of problems, for example.
All right. So actually, the line of thought that you mentioned, interesting, leads to the next question I have is, like for the scaling down of the memory itself, is having a fatter bus or interconnect to the memory a workaround or something that can help us in the interim? Can we have like a farm of memory that sits slightly away, separate it out? So that's the next question I have.
Oh, sure. So some of these heterogeneous devices, they're actually talking about making very, very thin wafers, making wafers and then thinning them down, essentially making via holes through the wafers, and they'll directly connect one wafer to another in order to increase the proximity, say, of memory and of a processing device. So there's a number of things that are, I mean, there's just like enormous variety of different things that people are playing with now. And a lot of it's because the traditional Moore's law scaling has slowed down. It's not as easy to do that. People are looking, but the demand is greater than ever. And so people are looking at clever ways in which they can continue to increase our ability to process and use this information.
Sure. Well, there are lots of questions awaited
I see that.
for you. So next question is from Supratim. He's asking, is there any disruption in interconnect technologies that promise that you could pool in various low latency memories across multiple servers? As in, of course, somewhere you will hit the physics itself,
Yes.
but then are there some disruptions in interconnect itself?
Well, so first of all, on the memory side, there's that whole CXL, right, which is being used for and part of the driver for CXL, which Intel is highly supported, is it was a way to make Optane memory more readily useful. Right now, so Optane memory is slower than DRAM, and in order to be able to use that with the processor, you had to modify the processor because DDR thinks it's dealing with memory that runs at the same speed. So these are running at different speeds. They had to actually build the capability in. CXL is a switch network memory interconnect that allows you to hide the performance of the individual memory and be able to pool these things together and use them, tier them and use them in various ways. There's also clever stuff that's being done in terms of optical interconnects and things of that sort. Again, we're limited by the laws of physics on what we can do, but there's a enormous, like I say, there's a lot of discovery, a lot of development work of the memory technologies, specialized processors that can be used for different applications and offload general purpose processors, and also for the networking itself. Hope that
I
answered
see
that.
yeah. So I see that Jim is online, so maybe we'll take one final question online and maybe reach out to you for other questions. So, well, the last question from Sanil is that you mentioned about the emerging technologies and memory technologies going into watch or some of the smaller devices. But how about the edge computing cases? Are there memory technologies that are going to impact how edge computing itself is done?
I think so. So the endpoint devices particularly are power constrained, right? And so these offer particular advantages to that. But I think even in edge applications, they're not traditional environments, traditional data center environments. They may have constraints on power. And I believe that these non-volatile memories are going to play roles in the edge, in the endpoints, but also in the edge as well. And even in data centers, data centers themselves are also undergoing demands in terms of their power usage. And especially in data centers, I've heard numbers like the DRAMs can consume up to 20% of the total computing power, just keeping the DRAMs refreshed, so getting away from the volatile memories to a non-volatile memory can have a significant potential power improvement. I think that holds especially important on battery powered devices, but I think also on edge devices and data center devices, that'll end up being true as well. Thank you very much.
Thank you so much. And it was great listening to your thoughts and how the world is evolving. And thank you so much. Over to you, Anvit.
Very good.
Thank you. Thank you. Right. Thank you so much, Ankit. And a very, very big thank you to Mr. Tom Coughlin for that very informative session on where we are headed with the memory world right now. Thank you so much, Tom. That was really
Thank you. And thanks to all my IEEE friends in Bangalore. Take care.
On that note, we are now heading into our next session on computational storage. We have with us Mr. Jim Handy, who's a widely recognized semiconductor analyst at Objective Analysis. Speaking on computational storage is Jim Handy. Over to you, Jim.
Thank you very much. This is the first time that I've used this system, so I'm going to have to learn how to share, but I think that I've got that. First of all, though, let me thank you for having me in to present. You know, it's nice to be able to do this, and hopefully I'll provide something of some value to the IEEE members in Bangalore. So let's see. Okay, so my presentation is going to be on computational storage, and just a little bit of a brief thing about who is this guy who's sitting in front of you right now. That's assuming that I can move the slide forward. Excuse me while my computer acts up.
We're able to see your screen and we can hear you clearly. I'm just that the slide hasn't changed yet. It's on the first slide.
I'm having that problem here myself. So
all right.
Yeah, I may have to go to the edit view instead because it doesn't seem like it wants to move ahead. Here, I'm going to try going to a different screen here. My apologies for this. I'm just going to try to go into the presentation one more time. Aha, there we are. So I just wanted to tell you a little bit about, you know, Objective Analysis, and we're a semiconductor market research firm. There are 3 of us, all ex-Gartner DataQuest analysts, and you know, we do reports, custom work, forecasts. And one thing that we're very proud of is the quality of the forecasts that we put out. This is something that's actually on our website that shows our forecasts since 2008 for how we expected the market to turn out. This was done the year before. And you can see that, you know, sometimes we were very wrong, but most of the time we were pretty right. And this is something that most forecasting firms really don't like to show, because forecasting usually doesn't turn out quite the way that people expected. We've got a model that seems to work very well for this. So, you know, if anybody wants market research, you know, we'd love it if you came to us. But that's not why you invited me to talk. You asked me to talk about computational storage. And so that's the subject of this. First, I'm going to present a problem and a solution, and then different architectures, and then talk about performance, who the suppliers are, and I'll take your questions after that. So this is a slide that just kind of visualizes what's going on and why there's a network bottleneck. So you look back a few years and compute and network and storage were all pretty well matched to each other from a speed standpoint. But over time, the performance of compute ended up going up, and storage with SSDs ended up getting much faster. But the network really hasn't improved in performance all that much. And so that ends up being the difficult part of this equation. Well, one of the approaches to solving this problem is to move some of the compute over into the storage. And that's what computational storage is trying to achieve. Another way to look at it is if you look at a system and how it actually processes the data. The processor will request data by sending a request down to the storage. The processor then will get a response from the storage and receive the data. And then it will process the data internally. And then once it's done with the processing, then it will write the data back out to the storage. That's a lot of traffic for just modifying some of the data inside of storage. Now, what would be a better way to do it is just leave the data inside the storage and have the processor initiate a process and then have the storage process the data internally. And so that's what this new technology is trying to do. Now, there are certain classes of data that this works very well for. And there are other kinds of data that doesn't work as well for. But I'll just list some of the ones that are ones that they find this application works very well for. And database operations are a big one. And, you know, that's a very big part of the overall data processing marketplace. So analytics, search, and sort, all of these can be done without the intervention of the processor and without moving the data into the processor and then back out again. Another one is AI training and inference. With training, especially in a training system, you go over the same data time after time after time after time. And if you're pulling that in from external storage all the time, that ends up consuming an awful lot of bandwidth. But inference too, and you know that's why I've got all the cute pictures of cats, is because this is kind of a problem that people look at. Facial recognition is probably a much more widespread one, where people will look at pictures and try to decide, yes, you know, is that whoever, you know, some famous person, or is that the person who broke into the store? And you can do that with inference. Inference has the ability to consume an awful lot of data as you're inputting images into the database. And so having the processing where the database is saves an awful lot of data motion. Genomics is also a very data intensive application, but there are also some very mundane applications, and data compression and encoding, those kinds of things are sometimes done inside of SSDs in order to save having to burden the processor with them. And so these are places, these are the kinds of applications that computational storage does well at. So let's move next to the different kinds of architectures that are there. And a lot of people jumped into computational storage about 3 years ago, and they all had a different approach. And something that people have been trying to do is to find a way to categorize those approaches so that software can look at a piece of computational storage, know what it can do, and then offload those tasks to it. So there are 3 key device types in computational storage. There's a computational storage drive, which is kind of what I was showing before, where something happens inside the drive that aids the computation from the processor. You've got something called a computational storage processor, which doesn't actually have any storage of its own. And usually those go into something called a computational storage array, which is an array of SSDs managed by a computational storage processor. The Storage Networking Industry Association, SNIA, has been spending an awful lot of time and effort trying to make sure that all of those devices are well defined, that their software interfaces are consistent with each other, so that somebody can write a piece of code that will adapt to whatever piece of hardware happens to be attached to it. So looking at those device types, this is a typical storage device. This would be a hard disk drive, it would be an SSD, it could be a CD, you know, any of those things. And it has management, it has an I/O channel, it has a storage controller, and it has storage. Now, I put this up so that you could compare it against the following diagrams of some of the computational storage devices. The most basic one is just called a computational storage drive, or a CSD. And it has the top part of the diagram very much similar to the others, but then down below it's got computational storage processors, one or many. And in some cases, people even reprogram the controller inside of an SSD. That doesn't usually get them really great results, but it is good for example, database primitives that can be managed within the SSD without an awful lot of processing power. So that happens inside, and it's, you know, a very simple thing. But other CSDs, computational storage drives, have very powerful processors with a lot of DRAM inside, and those processors sometimes are dedicated ASICs that were designed for this, which is a very expensive thing to develop. Other ones use just FPGAs, and we'll get into that a little bit more later on. This is a little bit more complicated of computational storage drive, because this one allows you not only to interface with the storage controller from the host processor on the right-hand side of the diagram, but it also allows direct access to the computational storage processor, so that there are two access paths in there. And that gives some flexibility that, frankly, I don't understand all that well, but it allows more functions to be done between the host and the computational storage drive. And then we have the computational storage processor. You notice that there's no tan box in here. The processor is all there is to this. And the reason for this processor to exist is so that it can manage data and actually process data within a storage array. And so this will go into the final class of device, which is a computational storage array. And if you look along the bottom of this, you've got storage or a computational storage device all lined up along the bottom of the drawing. That's the SSDs or computational storage devices that are being managed by the computational storage processor, the green box up above. So, this is the most complex of anything. And this is something that is advocated by certain vendors that we'll go into later on, that they turn a JBOD into, or JBOF, I should say, just a bunch of flash into a smart device that can offload an awful lot of data processing from the central processing unit. So let's talk a little bit about what these do for performance. You probably already intuitively guessed that there's a lot of performance increase that can be had by sending things out to the computational storage device. And yes, it does. This is something from ScaleFlux that shows their particular example of a CPU with hard drive storage. So it's a little bit of a slanted approach compared to their SSD with an internal computation thing. And they were able to get twice the throughput on this TeraSort plus TeraGen example by using their computational device. Another thing that I think is very interesting about this that actually came about, it was something that was highlighted at the Flash Memory Summit probably about 2015, maybe earlier than that, is the idea that if you add computational storage devices, which is what the bottom of this chart is trying to show, that you actually can get pretty much a linear improvement in how the performance happens. So with this is a fuzzy search algorithm. It's the best algorithm that ScaleFlux had for this. And they said that if you had one computational storage device hooked to a processor and you offloaded the fuzzy search to that, you'd get a 3 times performance improvement. But if you added 24 of their processors onto this system, then you'd end up with a 100 times improvement. And what's interesting about this is that the line is straight, that you don't have it tailing off with diminishing returns as you add it. That basically the server is doing nothing more than housekeeping, just kind of issuing orders, which are very brief, to each one of these computational storage devices, and then they're doing all the work. So because of that, you can get great performance out of this. And I like to say that it's conceivable that somebody might even put together a system where the central processor was some very, low power, insignificant kind of a processor that was just issuing orders to these high power processors that are inside the computational storage devices. So, that's certainly something that could happen. So now we'll talk a little bit about who are making these things. So, who are the suppliers? And the suppliers that I've got here are the ones that are, really doing something in a big way. There are an awful lot more companies that I haven't detailed here, but we've got NGD, ScaleFlux, Idetacom, Samsung, which is important, but, is playing a smaller role in this entire space. Xilinx, which is an FPGA provider, and then IBM and Cohesity. I'll be doing individual profiles on all of these companies except for IBM and Cohesity And the reason why is because what IBM and Cohesity are doing are extraordinarily dedicated appliances. IBM is, they've got SSDs that perform their own internal compression. And so, and encryption. So, that's something that they do internally, but it isn't a general purpose kind of computational storage where you can offload, for example, database tasks or anything to it. It only does those two things. Cohesities, likewise, their computational storage drives are used for video encoding. And I think that television studios buy those and use them to encode the data before they, send it up into a satellite or something like that. And so it's a single purpose type drive as opposed to the general purpose drives of the companies listed above. So let's talk about NGD. The company name started as Next Generation Devices and shortened its name to NGD. They were an early mover. They produced their first computational storage drive in 2017. It's completely self-contained. It doesn't use an external controller. And it also does all of the flash management internal to the SSD, which we'll find out why I said that in a moment. It uses an internal ASIC design. So this, if you look at the vertical one, the M.2 that's standing on its end, you'll see a large black square with a gray square in the middle of it. That's their ASIC. And they're actually getting good traction. They're going through an awful lot of proof of concepts where they're getting good results for that. And their customers seem like they're very happy with it. The next is Flux. And Flux decided to team up a very high capacity SSD with a very high performance processor. So they put an awful lot into that package. Something that they did do that's very different from the way that NGD did is that they've offloaded a lot of the flash management to the host processor. That is a plus and a minus. It's a little bit of a burden to the host processor, but on the other hand, it allows the host processor to synchronize what's going on in the processor with what's going on in the SSD, which is what causes most of the problems you have with SSDs. When an SSD slows down or stalls, it's because it's gotten out of sync with what's going on inside the processor. And there have been these I'm trying to remember now, there's a certain kind of an SSD that was developed a few years ago, mostly for Baidu in China. And that SSD was designed so that it would offload tasks to the host processor so that the host processor could make sure that when it needed the SSD, it was open. And when it didn't need the SSD, then the SSD could do its internal functions. That's something that the Flux solution supports. It's installed already at a number of hyperscale data centers who already know how to deal with this. And they've gotten very solid benchmarks like the ones that I showed you before with very key applications. So they've got good products. The next company is different. They're a computational storage processor company or CSP company called Idetacom. And the processor is in the storage array. So what they do is they take advantage of the fact that you can have a different device than the processor, than the central processor, using the NVMe channel to control the SSDs. So in a system with an Idetacom computational storage processor, either the server processor or the Idetacom processor can grab the PCI bus and control what's going on with the SSDs. That's something that works very much to their advantage, that it's not an SSD in itself, but it can control a lot of very low-cost SSDs, and it offloads a lot of tasks for the server. I'll show that in just a moment. So it makes just a bunch of flash JBOF considerably more than just a bunch of flash. It ends up being an appliance that can help the processor out an awful lot. This is the way that some people look at this, is that they say, okay, in a conventional system, you've got an NVMe Express SSD on the left-hand side and the bottom, and you've got some kind of a data processing unit. This is a Xilinx slide, so naturally it's got Xilinx in there. And that data processing unit is being told by the processor what to do. And so it requests a block of data from the SSD. And all of that data has to go through the host, tying up the CPU in order for that to be transferred. The idea with a computational storage processor is that it moves that down to the PCI bus so that the only communication that's going on is between the computational storage processor on the right and the SSD on the left. The host just issues commands and responses go back to the host. You know, yes, I found it. No, I didn't. Samsung is a more general purpose thing. They are working with Xilinx for FPGA based systems, and they do have something called the Smart SSD, which they haven't really been making an awful lot of noise about, although they did show it off at the supercomputing conference a year ago. They're very deeply involved with general purpose storage functions. I think that the role for this to Samsung is so that they can get better at designing the high volume SSDs that they want to sell most of. And so because of that, they're promoting lots of standards, and, you know, two of those areas that they've focused an awful lot of attention on that are not tied with their Smart SSD, they're growing them into other parts of their SSD ecosystem, are key value pairs and zone namespaces. Samsung's partner is Xilinx, and Xilinx, even before Samsung, was showing off what could be done with Xilinx FPGAs. And while they were doing that, they designed software tools to make it easy for people to use their FPGAs in computational storage devices. One of the things that they highlight, and you can look at this presentation, you know, kind of closely to see what's going on in the diagram in the lower right-hand corner, is that they've got a bunch of RAM tied to processing units, and it can have enormous parallelism inside of this. But also they've got support on their FPGAs for high bandwidth memories, which require very special support, and they're, you know, 1024 bits of data coming into or out of the processor very quickly. But they also have DDR4 support, and they will soon have DDR5 support. So Xilinx has a number of processors that could be used by other companies who have yet to show any products. So in summary, compute needs better solutions than the one where you move the data out of the storage into the processor and then back into the storage again. And computational storage is a good solution for that, not only because it reduces that load, but also because there are certain applications that it does mesh well with. I wanted to stress that there are many ways to build a computational storage device, and SNIA is trying very hard to make sure that all of those ways get accommodated in some kind of a global fashion. So that's working very well for them. I think that probably the most impressive thing is that performance scales with resources, that as you add computational storage devices to a system, then you get a pretty linear increase in performance. And, you know, that's certainly something that you don't see with an awful lot more scale out types of problems. And I think that the suppliers in general are solid, even though most of the ones that I mentioned are small companies. Samsung has certainly added an awful lot of credibility to this. And so I'm expecting to see this market develop very seriously in the future. One thing that I didn't say is that it is going to require an awful lot of software support, because basically programs are going to have to break themselves into pieces and ship off certain pieces of their code to the computational storage devices. But that is something that can happen over time, especially with the standards that are being developed by SNIA. So with that, I'm open to taking questions.
Well, thank you so much, Jim, and very nice to hear your thoughts around the computational storage and how it is coming up, because it's a fairly new technology and everyone has their own interpretation of what it means to them. Everyone thinks like, well, this is what computational storage is, and every vendor wants to push their way, and glad that SNIA is also trying to normalize things there. So here are a bunch of questions, and I think these topics are up the sleeve for Tom as well. So feel free to chime in, Tom. I see that you're still online. So I guess both of you don't need any introduction to each other.
No. As a matter of fact, we live within 2 miles of each other.
That's really nice to know. So let me start with.
India is much farther away.
That's true. And with all of the pandemic affecting us, the distances have actually become close to infinite right now.
Yeah, yeah. On the other hand, this is the second time that I've ever spoken in my career in India, and the other was only about 3 months ago.
That's
This is
really amazing. I think we should soon have an in-person conference once all of this settles down, and we should have you here.
Yes.
This is Tom. Yeah. So yeah, like Jim said, we only live a couple miles from each other, but we've been seeing each other remotely too, for the most part. So it'd be nice to see people in person again. I'm looking forward to that.
Yeah, I think it must happen really soon. So, all right, let me get started with the first question. So, the question is from Lokesh. So, it looks like computational storage devices can provide increased throughput, but can it actually help improve latencies as well, lower latencies for the computation? And also, do you have any thinking or like some info on how much of performance can we see improved if it really gives lower latency?
Okay, you don't think about latency with these devices the same way that you would think about them in a standard computing system. In a standard computing system, the latency would be in that network that I showed in a very early slide. And the whole idea is to bypass the network and to move the computation to where the data already is. And so for that piece of the computation, the latency drops enormously because it's got no network protocol to deal with and no delays from the network. As far as, the latency of the processor telling the computational storage device what to do, that won't change. That will be the same as in an older device. So then the question is, do you get higher performance from this, even though you still have the same latency for the command? And, you should, because of the fact that you've got that extra processor right next to the storage. And in some cases, it has more communication channels with the storage than it would have through the network.
Sure. Well, next point actually maybe sounds controversial, maybe if I'm not over speaking about it. So this particular question is that is computational storage an attempt by storage vendors to keep themselves relevant? Because earlier in the talk, you mentioned about that the processor is just giving instructions what to do. So it's much lower powered processor, whereas you're now investing much more onto a device that's manufactured by the storage vendor. So is it something like instead of having a generic storage manufacturer, they want to be in the game and a way to transform or gravitate the computation aspects towards the storage, as against how the compute vendors have been taking away functions of the storage by doing snapshotting, data protection, and things in the app itself? So is it like, and also just a related question is, the network guys are also trying to play their part by DPUs, where you say, like you can have compute run in the network card instead of running it on the CPU. So is it a tussle between the different vendor component vendors, or how is it?
I think that there's always going to be a wrestling match between the storage vendors and the compute vendors. I look at things more from a chip level. And so I look at a company like Intel selling processor chips and making 60% gross margins year after year after year during good times and during bad times. And then I look at the memory companies that I focus most of my attention on. And those guys during a really good year will make a 40% gross margin. And during a bad year, they'll make a 0% gross margin. And so they look at Intel and they say, how can we get a gross margin like Intel's gross margin? And they try various things. And one of the things that they're trying right now is to build SSDs that have some processing power inside, that hopefully that will get them higher margins than what they're used to. So you're right, there is a little bit of that going on. Now, as far as, the storage arrays offloading tasks, that I can see that happening. And that was part of what I was talking about with the synchronization between the processor and the SSD, that this, I'm trying to remember what the name is of the thing. I think it's OpenSSD that came out a few years ago. Offloaded an awful lot of the flash management into the host, with the benefit being that the host could then understand what was going on inside the SSD and could tell the SSD when to do certain functions so that it wouldn't get in the way. You would no longer have garbage collection hangups, and write amplification just, it becomes almost non-existent with those kinds of SSDs. You could look at that as being the host taking some of the functionality away from the SSD and making the SSD worth less. But in the long run, it's a higher performance solution, and so it's probably better for the industry. So yeah, you're right. There is some motivation for people to take things away from each other for profit, but there's also motivation to take things away from each other for performance.
Sure. Tom, do you have any thoughts on this? Since you're online, I think it would be great to hear your thoughts too.
And that is the, sorry, ask the question again.
Okay, so, well, the question was that is computational storage actually an attempt by storage vendors to keep themselves relevant? Because the compute guys are taking away things that storage vendors do, and network guys are trying to play their part with DPUs. So there's like a wrestling, as Jim puts in, like each one wants to play more in the vertical stack from the application down to where you keep the data.
I think that there, yeah, I think there's an eternal battle for margin, and yeah, exactly. And so everyone is trying to find a way of addressing these needs. Whether you come from the storage side first, or you come from the compute side. And what I think is really interesting is that and again, I think this all fits back into the traditional scaling, is failing. And so people are scrambling to find new alternative ways to meet the increasing demand at the same time that the traditional approaches are declining. The demand for computation, for memory, for bandwidth have increased enormously. And so everyone is scrambling to play a part in that business, because that business is going to be huge. Meeting all those needs for, especially a lot of it's driven by AI of various types, and providing that, whether it's at the data center, an infrastructure in a smart city, or in autonomous vehicles, or in endpoint devices. And there's going to be different things that are going to work out for different sort of balances are going to work out in each of these areas. So I think it's going to continue to be a struggle. People are trying to redefine everything in a sense. So it's not surprising at all that you see the storage guys trying to play in the in the compute market, in some part of the compute market, and the compute guys trying to play in the storage market. And it'd be interesting to see how things balance out in the end here.
I'm guessing like across all of the CSD devices, you might have to have, again, a distributed system on top of it at some time.
I think we're going to see more and more distributed storage, and especially in the data centers, there's going to be a great, more virtualization, better ways of managing resources, in order to lower overall costs and performance. And at the same time, they're subject to new environmental requirements or demands at the very least, that are going to change the way that a lot of computing potentially is done. And like I was saying, when I was giving my talk, people were asking about what's there. There's all kinds of computing approaches that people are making, and all those are going to require some kind of memory, memory and storage as well. So it's going to be very, like I say, it's going to be very interesting times ahead of us here in the next few years, and how we end up doing this. And fortunes are going to be made and lost as a consequence, I think.
In 10 years, we're going to look back on how we do things today, and we'll say, boy, that was dumb.
Yeah. How quaint.
So yeah, Jim. So another follow-up question. There are lots of questions for you. It was an
Mhm.
interesting talk, and so this question is that when you have a centralized compute, you can do erasure coding, RAID, compression, and data dedupe and space efficiency things in a central place across multiple drives. But then if you actually give the responsibility of managing the whole thing to the drive, so in a case of a computational storage drive, how does it affect things like EC or things like space efficiency, where you could have deduped across multiple drives, but now the drive wants to take over?
Yeah, the people who use these drives will need to use judgment in how they split up their data, especially for a very large data sets. And for example, you would probably do very poorly to split up a large database across several computational storage drives. And I've never done this myself, but my understanding is that shards are, something that's a necessary evil in certain cases, and that joins are something that's just an absolute misery to try to do once you have performed processing on a sharded database. What you'd do if you were in that case is you might gravitate towards a computational storage array, and then you'd be able to put the entire huge database into a very large array that was controlled by a processor, a computational storage processor. So I think that there are workarounds, and I would imagine that, where you'd run into problems is where you have a data set that fits just fine into a computational storage drive, and then all of a sudden, 3 days later, you've got 10 times the number of subscribers, and you need to shard all of your database and rethink everything. That would be a real problem. There's some issues that people are going to have to think about, and they're going to have to look hard at their growth paths when they do this. But things like the encryption, those are generally done in small chunks. And so I would imagine that those could be handled very well in a computational storage device.
A compression or encryption would be fine, but then data deduplication would be sort of a challenge, because
Yeah.
you are looking at data blocks within the drive, and otherwise you may have to have an index outside or a distributed way of cooperating between the CSDs. Like, by the way, you have the data virtually, but it's with me, right? So so it makes it fairly interesting. I guess we need to rethink of newer algorithms for that.
I've never seen anybody claim that computational storage drives are good at deduplication. They probably say, well, let's not talk about that. Let's talk about database management.
I
Well,
think this, on that one, I think there's talk about using some accelerators, though, that might be close to the storage or memory for dedupe, as one of the accelerator functions, maybe not in the device itself. So
well, you're talking about then again centralizing things.
yeah.
Yeah. So of course that wrestling, as Jim had put it.
Mhm.
Okay, so there's another question. So you briefly talked about, Jim, about that you can rewrite the applications designed to take the best benefits of computational storage, because you can chunk it down, maybe something like a map reducer, or like in a database, execute and join, or something on those lines. But what are your thoughts or trends that are happening for the legacy applications? Because asking for a rewrite of all the plethora of applications, we have seen it back in the year 2000 and around for the Y2K and various other times, that it's not easy to just go ahead and throw all the old applications and replace them.
No, it's terribly hard. And Intel has found that out when they're trying to get people to bring persistence closer to the processor with their 3D crosspoint memory, their Optane, what is it, persistent memory modules. I call them Optane DIMMs. But the problem is that any time that a company has a piece of software that has been established and proven, it works, it's solid, and then somebody says, well, would you please change this? Then they resist very strongly. And Intel, after a few years, was able to get Oracle and SAP to support persistent memory simply by showing that performance was going to be significantly better if they did that. That will need to be done with these devices too, because the people who are making database management software or any of these other programs, the artificial intelligence things, are going to need to split up their programs into the piece that goes into the computational storage drive and the piece that does not. And that is something that could slow down adoption very seriously with this.
Sure. And also you might have to look at what kind of instruction set can be executed on the computational storage and what cannot be.
Yeah, somebody is going to have to do that port.
Right. So it was really nice listening to you, Jim. There are questions that are pouring in, but then, the time is never enough. And I will have the questions sent across to you to get your thoughts on it and get the answers back to the audience. Thank you so much. And over to you, Anvit.
Oh, and thanks for having me.
Thank you so much, Ankit, for having that lovely question and answer session with both Jim as well as Tom. Thank you, Jim, once again for spending the time, making time at the last moment and giving that brilliant talk on the computational storage and where we are headed. Thank you once again.
Oh, thank you, Anvit.
And we hope to see you soon in person sometime.
I hope so too.
Absolutely. With that, we'll dive right into our next session. We have with us Rama Govindraj, Director of Engineering at Google, who's going to be speaking on, challenges and opportunities for managing data at planet scale. Over to you, Rama.
Thanks very much, Anvit, for the invitation and for the kind introduction. Can you make me the presenter so I can share my slide deck here?
Can you try now?
Yeah. So when it says share screen and application, what should I pick here?
You can share just the application if you're presenting from slides, maybe just a tab if you want to.
Okay.
Depends on if you're using slides or PowerPoint.
Can you see it?
Yes, right now it's in edit mode. You can present and.
Okay, how do we make this the primary part of the screen?
We are good to go right now. We can see just this presentation and your video is up top. So we are good.
Okay, sorry, I should go back to the beginning here. Okay. So what I'll talk about is some of the emerging challenges in building planet scale storage systems. And the first question is, why do we need planet scale? So Google serves the entire world community with its applications and services. So it's important to build services that can scale to that level. You might think that personalized data like Gmail and what have you can be easily sort of moved to wherever you move it around the world. But there's a whole bunch of services that are always concurrently in use from all parts of the world. So a simple example is, let's say, Uber. It's driving its drivers and sort of driving notifications to them and what have you. They're across the planet, and they need to be able to interact with the system in real time from anywhere in the world. Another simple example is, let's say you have an ad system that's running on Google services, and you're a JCPenney, and you have $100 that you have enabled for advertisers. It could be that you have customers that are logging into the JCPenney site and clicking on the ads from Sydney in Australia at the same time from San Jose in California or wherever in the world. So there is a need for services that can scale to planet level and operate at real time. And that's the kind of challenge that Google is sort of trying to address. So I'll be using examples mostly from Google, but not as advocating for Google services, but to demonstrate the challenges that it poses on technology and also on how you build such services to scale for the kinds of services that we have to enable here. So that is the point that I want to make, and that's the point of making it a planet scale kind of a discussion. So the key messages that I'm hoping to sort of put across today is, how do you plan for such scale? That's an important thing to sort of think about right from the beginning. And how do you sort of compartmentalize this kind of a problem into something that is more tangible? And that is where we talk about data warehousing across the world and coordinating them. So, and then also running queries on the data sets that span planet scale. And some example services like BigQuery are there. Right? The other issue is when you have planet scale databases, one of the issue is how do you sort of keep track of synchronized time? How do you order events that are occurring across the world? And so for that, you need a time synchronizer across all your data centers. And that's an important piece of technology which was developed as a true time service to ensure that these transactions could be ordered and reasoned about to provide strong semantics for distributed NoSQL databases. And then the other thing that is very important at planet scale is the data sets on which they operate. And to that end, there are many data sets that are now made available to everyone for their use in Kaggle. And there's a link to that I have shared here. Also, the other thing that you need to sort of consider is when you're operating on data at planet scale and need to deliver results from these services in real time, current traditional computing just doesn't cut it. So you need to leverage accelerators that can help with the real-time nature of some of these problems. And one of the other messages that I want to make sure we get across is to make these services sustainable, you have to have functional flows that are self-serving. So when you have a problem that happens at planet scale, debugging is a real nightmare. So, or anything that requires manual intervention is just bound to fail. So building sustainable functional flows that enable operation to go smoothly at planet scale requires deeper thinking and deeper planning here. So today I'll just briefly summarize this into three parts. First is I'll discuss industry trends, technology trends, and some workload trends. And what do these trends mean and what kind of meaning can we extract from this? And the second part, I'll discuss some of the opportunities for emerging markets. This is, after all, a conference in India, which is an emerging market. So what kind of opportunities does this present? And in part three, I'll focus on how can we prepare ourselves to address these opportunities. So in terms of the technology trends, the first trend that, and this is just like I said before, I'm using an example from Google because that's the data I have, not to say that I'm trying to advocate for Google services, but to illustrate the points here. This represents the technology improvements in the networking space over the last decade. It's slightly dated, but it shows the trend. And what it shows is over the span of about 10 years, the networking technology has improved by 130x. So significant improvement in the networking capability of the compute capability in our data centers. The second slide here is data from YouTube, which is showing, which is the red line here, which shows how much YouTube videos are uploaded in each minute. And so the growth of data is far higher than what we see is the improvement through Moore's law in the compute space, which is the blue line. So what it shows is just a single service like YouTube outpaces the computing capability improvements that we are seeing from technology here. So the key trends that you see is networking and storage are growing far faster than the compute capability. So there's a system balance that we have to consider to adapt to this moving trend here. One other example I'll give you is Google Photos. It reached 1 billion active users in 3 years. And some of the fastest growing other services that we know, Gmail, Facebook, Instagram, all took about 8 years to reach 1 billion users. So to be able to build services that rapidly scale to a vast volume of the planet, you need to think about these end-to-end functional pipelines that I mentioned earlier. So for Google Photos, there are 1 billion photos uploaded each day. The other thing you note is the photo quality is also increasing. The cameras are getting better. The cell phones are having larger precision. They also have better storage and better camera technology there. So some of the operations is how do you support this wide number of user formats for photos? There's JPEG photos, there's other kinds of formats. How do you sort of improve on the photos through editing, filtering, smoothing, and what have you? How do you build the kind of end-to-end functional pipelines that enable users to organize the photos into albums, timelines, and enable them for searching? So those are some of the example use cases for planet scale services. An interesting data trend in terms of other technology is obviously artificial intelligence has just taken off in the last decade. This is sort of easily seen through the number of archival submissions, which is doubling almost every 18 months. If you look at the Google directories and the Google code base, that's for AI is just doubling every 18 months. And what is also happening is the time to train a model is doubling. Why? Because the data sets that it has to learn on is increasing very, very rapidly. So what this needs to be sort of considered is to be able to manage this kind of volume of data. Any manual intervention obviously will not work, or any algorithmic approach will not work. You need a learning-based approach here. The other thing that we noted in the last 1 year with the pandemic is the use of video conferencing has also exploded. So what this is showing is there's a new change in the way data is organized, in the kind of data that is being organized, which means that instead of previously, which we were accustomed to and computers operated on, is mostly textual or numeric data. But now, if you look at the internet traffic, there's a report from Cisco which says that over 60% of the internet traffic is video, right? So the media is changing from textual alphanumeric data to more rich media context here. Something that we need to learn to adapt, which means the computing model that we have also needs to adapt to this change. So this is what I was talking about, is the report from Cisco, which says 60% of the global internet traffic is video, right? And resolutions and frame rates are growing. And the complexity of compressing these formats, video formats, is also becoming harder, because as the precision grows, it becomes harder to compress them because there are less zeros there. There's more detail in each pixel that you have to capture. So an example of this is some data on video compression that I have from 2003 onwards. And what it shows is the time to encode, time for best quality, is increasing very rapidly. But the compression efficiency isn't growing as rapidly. And the video formats that were popular many years back, which was H.264, then transitioned to VP9, and now to a new standard called AV1. So what this indicates is this kind of computing that is needed to compress video formats requires specialized accelerators, because traditional computing is just not going to be cost effective. So this is the follow-on to that slide, which shows that the the number of pixels in each image of the video frame is also growing to capture more detail and for a richer viewing experience. So for processing this volume of data that is being created and sort of uploaded at each minute requires the kind of processing capability that can only come from accelerators. And this is an example of data from Google, which is very interesting. What it shows is the red one, which is multiple output transcoding. So where you transcode a given video into multiple formats because it may be viewed on different devices which have different capability. And the SOT is the single output transcoding. And the yellow one is done by an accelerator in all formats. So what it shows is how much accelerator compute has enabled the savings of CPU cycles to enable this transcoding function. Just showing you the power of accelerators for these specialized functions and the need for them to make them cost effective for the general consumers here. So just a quick summary of the industry trends that I wanted to capture is the diversity of workloads is rapidly increasing, and that is also changing the kind of data that we are creating and operating on. There's new kinds of frameworks and techniques for ML and AI that are becoming very, very popular. There's also video conferencing, which is rapidly increasing, and the pandemic has just helped accelerate that to a significant level. So there's an exponential increase in the data that we need to manage. And there's a running joke in Google where the question is asked is, what do you call a condition when you have only double-digit petabytes of data available, data space, disk space available? And they say, oh, it's a crisis mode. So that's the kind of data generation that is happening. And there's a big transition that I mentioned from alphanumeric text-based data to rich media, which we need to sort of figure out how we get better at operating on. The other thing that I also want to emphasize is for any of these services to work at planet scale, you need well-designed functional pipelines that just do not require any manual intervention, because at planet scale, manual intervention just does not work. So the other point that I want to make is clearly accelerators are critical here. And this is some of the accelerators that Google has for its AI and ML services, which are called TPUs, or the tensor processing units. And this shows a picture from 4 years back. So in 4 racks, we were able to pack 11.5 petaflops. Okay. And that's very, very significant computing capability in just 4 racks. And that's a real image from a data center there. Next slide. But what it also shows is, just like we have TPUs for the AI and ML workloads, and we have the VCU accelerator for video transcoding, we will need a whole set of accelerators for many of these services to make sure that computing continues to be affordable for all the services that we have to offer. Right? And so there'll be a variety of heterogeneous platforms. There'll be CPUs for traditional processing, GPUs for graphics processing and other workloads, TPUs for AI, FPGAs for some customization, and there's a whole bunch of other processing units that are yet to be developed. And the question mark PU is an indication that to figure out what is it that we can accelerate requires a deeper hardware-software co-design, which means a deeper understanding of your applications, the services, where their bottlenecks are, what kind of repeated computing pattern they have that lends themselves to acceleration. Next slide. So this is just a summary of what I just tried to capture in the trends that we should sort of understand, and then sort of step back at a higher level to see what do all these trends point to and what opportunities do they enable. So some of the opportunities, the way I think about it is, this picture is a good example of the kind of trends and opportunities it presents. So the big container ship here is sort of an abstraction for what we would call a massive data center or a cloud operation center, where you have various workloads that can be packed. But one of the key challenges that poses is when you have a container like this, a ship like this with lots of containers, how do we make sure we're making improvements? If we make changes in our infrastructure, where some of the containers see some improvement and some of the containers see some degradation, how do we measure forward progress? How do we evaluate if something is worthy of deploying or enabling? Because there'll always be cases where there's some trade-offs. There will be some services that will experience improvements and some degradation. So you need a rigorous methodology that can reason about such complexity of sharing environments in data centers and in cloud environments. So this is an example of how you can go about it. And there's an ASPLOS paper from 3 years back called WS Meter, which will dig into this in more details. And I could spend about half an hour just on this slide, so I'll skip that. But for those that are interested in how we measure overall performance of all services in a complex data center environment, I'll refer you to the ASPLOS paper called WS Meter. And if you search in Google search, you should be able to find it. The key insight from that is, depending on the margin of error that you can tolerate, the number of machines you need for your careful experimentation to validate your hypothesis can be determined. And once you have that, running that experiment in a controlled fashion will yield the kinds of insights that are necessary to make forward progress on how we improve the efficiency of our data centers. The next slide is an important one. And I mentioned the importance of having functional flows that eliminate the need for any manual intervention when you are operating at planet scale. A key concept that enables that is clean abstractions. So without clean abstractions that users and applications can depend on to not change and always function, it's very hard to build planet scale services. So the other challenge here is when you define these abstractions, oftentimes, like I mentioned earlier, that the underlying compute platform is not homogeneous. You have CPU-based platforms, you have GPU-based platforms, you have TPU-based platforms, FPGAs, and custom accelerators for AI, ML, other workloads. How does this abstraction deal with that heterogeneity while still enabling the applications to realize the full benefits of the computing capability underneath? And that requires a lot of engineering work to make sure that this mapping of the applications to the right underlying platform is a critical infrastructure piece that has to be enabled here. So the other obvious one, which everyone is sort of hyped up about for good reason, is deep learning has shown that if you have good data and you have good computing capability, then where traditional methods, algorithmic-based methods, have not succeeded, deep learning has. And this has been demonstrated in a large number of grand challenge problems. So we should understand, deep learning is not a new concept. This was actually invented in the 70s. So why is it now that it's starting to see such rapid adoption? And there are some key reasons here. In the 80s and 90s, when deep learning was also attempted, they were severely limited by the compute capability. You had uniprocessors, they were very expensive, and the data sets weren't large enough for these methods to succeed. So what we have found is, neural networks are, deep neural networks are very, very successful in solving some grand challenge problems now, because many of the underlying themes that were prevented its success in the 80s, 90s, and the 2000s are no longer true. So, for example, the compute capability and the scale of data that is available is significantly larger now. And if you have a large amount of data that's well curated, deep learning methods work extremely well. And with our ability to scale compute operations at planet scale, we have been able to gather and operate and organize very vast amounts of data. And so larger data sets obviously help with accurate training. The other thing is that computing has also become very cost effective. And in combination of this cost effective compute and large amount of curated data lends itself to very efficient learning through deep learning methods. So as an example, what it has enabled us is to look at some of the grand challenge problems that were posed by the National Academy of Engineering in 2008. And From these list of grand challenge engineering problems, the 4 areas that Google has sort of made significant investments and advances are in restoring and improving urban infrastructure. Google Maps is one example, which has helped with traffic congestion problems and what have you. Advanced health informatics, and I'll show you some examples here. Engineering better medicines, and that's again some very recent examples. Even the pandemic has illustrated why the genome sequencing was so important in enabling mRNA vaccines. And then, of course, engineering the tools for scientific discovery. So I'll go through some of these examples of the grand challenge problems that Google is trying to address, and how the confluence of vast amount of data at planet scale, cost-effective compute can enable really amazing things, and what opportunities it presents for an emerging economy like in India. So some of the technology breakthroughs that this model has enabled is truly remarkable in computer vision, and where visual search service has now better accuracy than even humans in being able to sort of capture the details in images and be able to segment them and to understand what they mean. Language understanding, natural language processing, especially through the transformer models called BERT, have been extremely good and can sort of have accuracy much better than humans already. Translation is in huge use and sort of has helped break barriers for tourists and what have you, enabling easy and very accurate translation among many languages just through your cell phone. Understanding speech and sort of predicting events. We didn't predict the pandemic, but now this technology that will be able to predict this and how pandemic sort of evolves also very easily. Self-driving cars. These are all some examples of true breakthroughs in engineering excellence that has been experienced in the last decade here. And AI is now finding its way in almost all applications and services that we use. And this is just a sample from Google. And if you look at all the other examples from all the other companies, the list is just huge. So what are the foundations for AI? And so some of the things that I want to alert everyone is there's a lot of services and infrastructure that's already available. So you don't need to build this from scratch. So there's open source. There's a whole bunch of services. I'm sure many of you are already using this. I highlight the one from Google, which is the TensorFlow, enables AI and ML applications to be easily written for both training and serving. Then there's a lot of technology that has been made available and distributed infrastructure know-how through publications that I'll list in the next column. And then for even the users that want managed services, there are many of these services now available through Google Cloud and through Amazon Cloud. There are similar services through Azure Cloud. There are similar services. So I'm not advocating for Google here. I'm just trying to sort of demonstrate that many of these services are now available for the general population to enable their own infrastructure there. And what you'll see is over time, this will just get even more denser on the right-hand side of this chart here. But among all these, the key point here is they're all driven by data. There are sort of data, how to store and organize them, how to operate on them, how to develop them, how to manage them, and what have you. TFX, which is the TensorFlow ML framework, is the programming model that we use, and this is open source for you to write your training and serving applications with a huge list of library functions and orchestration and what have you, and enabling the distribution of this computing framework, parallelizing it and collecting the results and being able to monitor and debug. A fantastic framework. By the way, this is not the only framework. There's many other popular ones. There's one from Facebook, which is PyTorch. There's Keras. There's a whole bunch of them. So any one of them is perfectly good. Key point here is take advantage of them. Don't try to build anything from scratch. There's a ton of existing infrastructure that can be leveraged. Another important piece that I want to sort of highlight here is the use of embeddings. In machine learning and AI, there are typically 5 different operations that are the most popular. One is the fully connected layers network, in which it's dense matrix multiply operations. Then there's convolutional networks, which is very popular for image networks, image applications. Then there is sequence-based operations, or LSTMs, which are very popular for where there's a cause and effect kind of transaction that happens. There's a time series of this data, like you have a sentence that you want to parse, the ordering has a meaning. So for those sequence-based operations are very, very popular. And then there's recurrent neural networks, which were popularized by DeepMind, which are very good at game theory. So if you want to play chess or Go, anything that is very complicated, and so AlphaGo and AlphaZero are examples here of recurrent neural networks where you build a risk-reward function and then you throw data at it. In fact, it can learn by itself without much data. So if you just give it the rules, it can play with itself. For example, AlphaGo, AlphaZero learned chess by playing against itself. And the fifth one, which I think is the most important, is embeddings. And embeddings is the key concept, is to simplify it, is to convert every entity into a vector of floats. And the vector of floats, the floating point values are learned, and they're learned in such a fashion that you can actually now do mathematical operations on it. I'll give an example here. So on the left-hand side, you have an association of vectors where you have countries and their capitals. And so what you can now do is, once you learn these vectors, then you can do mathematical operations like Berlin minus Germany plus Russia should result in Moscow. So although these are words and country with meaning of countries and their capitals, if you can create an embedding that is learned, then you can actually do mathematical operations. And the right-hand side gives you another example, is you have words with variant of those words, and take minus took plus drew equals draw. You can draw these kind of conclusions. And this presents a very powerful technique to operate on data that you want to sort of reason with, which has a large number of parameters or feature functions. So the feature functions can all be embedded into a single floating point vector from which you can do mathematical operations. And the other advantage is this lends itself to huge parallelism. Everything can be done in parallel here. Right? So each vector in its own index can operate in parallel to arrive at conclusions that you want here. So YouTube recommendations, for example, uses these embedding vectors, and the embedding vector has a watch vector, a search vector. So what are you searching for in YouTube? What have you watched in the past? And your geographic embedding, which is where are you looking for this from? Which location are you in? And then the rest of your personalized information can all be embedded in a vector, which we call an embedding, that can then be used for operations, mathematical operations, to draw conclusions on what is the right recommendation for you to watch next. That's a slightly difficult concept, but I spent a little bit of time to give you a sense at a high level as to why such a construct like embeddings can be very powerful. And this doesn't have to be word embeddings. It can be embeddings of any entity. The other thing I want to sort of emphasize is to understand the transition that is happening to cloud and how best to leverage it. And there are many models, right? You have your own data, you have your own models, and you want them to run on, more distributed and easily available, planet scale available infrastructure. And that is perfectly good. The other is you don't have the ML expertise, but you have lots of data. You can use existing models for many of these services, recommendation engine or speech recognition or translate or what have you, and have it operate on your data. And the other is you just can use Google's own data and models and just build applications on top of it. So they're all different kinds of models, but it's important to start thinking about what is available and what is important and what you can leverage. And I think this sort of presents a picture that is very useful to keep in mind. And again, I just want to mention I'm using Google just as an example because I'm familiar with it. And I don't want it to come across as I'm advocating for Google. You can use Amazon Cloud, you can use Microsoft Cloud, you'll have similar services even there. So once we understand what exists in the framework, what the trends are, the next question is, how do we prepare ourselves for these opportunities? And how do we leverage and exploit these opportunities here? Of course, I'm going to skip this just in the interest of time. I think I'm running a little behind. Also very important is AI, although very powerful, also is very susceptible for misuse. So very important to create founding principles or grounding principles that everyone must abide by, so that these technologies are not used for malicious purposes or with any intent to harm others. And we have seen the cases with in the last few years as to how misuse or misinformation can derail the best of organizations and best of countries and what have you. So if you break it down at a higher level, what is needed for success here? So I think I break it down into very simple parts. You need technology, which means you need the best AI algorithms and the best infrastructure to enable that. So that can be achieved through AI methods that are available on cloud. You need speed, which means the best accelerators for the workloads that you have. You need the scale, which means it should be available everywhere. It should be planet scale, right? If it's available everywhere, then you have nothing to worry. You can enable everything. And then you need reach. And thankfully, mobile phones are the best vehicle to interact with all these services, right? So much of the entities that are needed for success in many of these areas are actually present today. We have very good AI technology. We have cloud services that are enabled for planet scale. We have the reach with the cell phone. Now, the key is how do we leverage all these to help us here? I'll skip this just in the interest of time, given how slow I'm running. This is Kaggle, which I mentioned earlier. It's also important to contribute back to the community. There's many data sets that Google has contributed to enable others. In this industry and in this current environment, whoever has the most data and the best curated data will always come out ahead. Because if you have large amount of data, even simple methods work very effectively. So it's also important for community good and for universal planet good that we contribute stuff that will benefit everybody, right? But we should make sure it is protected against any privacy challenges and make sure it is filtered out or anonymized to the extent that no one can decode. Let's say medical imaging is a classic example, which can have tremendous benefits as long as we can make sure that the patient information is protected and is not sort of inferred from any of the images that are there, right? So these are important things to consider as we become citizens of this community and enabling new services here. So from all this, what are some examples that we already know that have had huge success? And this is an example from New Delhi, where some engineering students built an app called Air Cognizer, which just takes a picture of the image of the weather outside and can tell you what the air quality is at that time. So this is very helpful in figuring out, is this around the right time to go out? Or if I do go out, what kind of protection do I need in terms of a mask or what have you? So this has lots of applications. So this is a simple example. This was built by some students in less than one semester as a class project and hugely successful, already in use by many already. Yeah. So this is what is possible. Another thing that is very important is, combating fake news, which is very, very important. Unfortunately, bad news travels faster than good news or accurate news. So this is something that really needs a lot of work. There's many student projects that came out of India that had examples on how to build this, and with varying degrees of success. But what it shows is, if there's bad players in the system, good players also have the tools to stop the bad players here. This is an important example of improving brain MRI. So what happens is, this is a very expensive procedure where images of the brain are taken for the doctor to do a diagnosis. But based on how the images are taken, they may be able to get the details they want. Sometimes they may not, and they may have to take an MRI again. And when mostly these are operated by technicians, and technicians almost always will not have the best insights on where the detail is necessary. So now there's systems that enable this to automatically sort of be trained, so that it figures out where there might be areas of interest from what is taken from the initial set of images, and automatically go and extract that kind of detail by changing the MRI angles, so that the doctor has the clarity they need to make an immediate and correct diagnosis without going through multiple iterations or trial and error. A huge improvement that has been demonstrated here. Some other examples is, sharing economy. Of course, urban traffic engineering has become a big challenge. But sharing economy, Uber share and what have you, all are starting to become possible because of this. Figuring out how to do congestion control and how can maps help in guiding passengers and travelers to avoid congestion, to maximize global optimization. Many of these ideas are now starting to work. How do you control the traffic lights so that you minimize traffic congestion? How do you sort of put in incentive structures to minimize congestion challenges and what have you? Many such examples are starting to take hold here. The other examples, which is probably very relevant in India, is, I remember I grew up in a town in India where, every year the monsoon season, the village would be wiped out and lots of lives would be lost. There'll be huge damage that is done. And often these came with almost no warning, so that any precautionary measures could be taken or lives could be saved. But these are all preventable. And some of the new capabilities that are being enabled here are, when you see a weather pattern, you can ask the system, hey, have I seen this kind of pattern before? If so, how did that shape up? How can I use that information to, tailor my current simulation for more accuracy? How can I get even more advanced warning? All these are starting to become possible. I've listed, I'm running way out of time, so I'll just quickly skip ahead. There's many examples in healthcare where all this infrastructure and services start to become very, very important and very easy to sort of address. Given I'm running out of time, I'll quickly skip ahead. This is on diabetic retinopathy. Very important. People who have diabetes often lose their eyesight because of diabetic retinopathy, but if detected early, can be easily treated. And this is an example of a picture from India where there's queues in front of a Shankara Eye Foundation clinic, just showing you that there's a huge shortage. And 90+% of these patients probably don't need to see the expert. So if you have medical imaging of their eye, which can easily say that, hey, look, you don't need to see an expert, here is the diagnosis, you'll be able to filter out the non-critical cases and allow the doctors to be able to focus on the ones that really need critical care, right? And this is an example where even experts struggle. You take an image of the back of the eye, and if you're rated 1 or 2, you have no risk of losing eyesight because of diabetic retinopathy. If you're in 3 and you're detected early, then it's easily treatable. 4, if you detect, there's a chance that you can treat it, but there's a risk. 5 means you're already too late. And unfortunately, in India, about 45% of those that lose their eyesight never even have an image taken to be able to determine what their problem is, or they don't think this is treatable. So this is something that can really help a country like India. And these technologies are now available, and you just have to enable it for the mass scale. I'll just skip ahead and take questions because I realized I ran way out of time. And I'm sorry about that.
I believe we do have a few questions. Ankit, over to you.
Sure. Thank you, Anvit, and thank you so much for a lovely talk, Dr. Rama. So it is something where you have covered like a breadth of different technologies, and so many people eager to know more details and how to use those technologies to advance the requirements of humankind. So I'll get to the questions right away. So you talked about customization and close working of the software and hardware to get the best out of the system. But then coding everything to a specific available hardware would be fairly a hard thing to do. And also the improvements or the evolution of what's available is happening so fast. You develop some software today, and then few years down the line, there is something else that is available. And it may not be always possible to keep on rewriting or recoding as per the new paradigms, new methods of writing the software. So how do you see the convergence of the CPU, GPU, TPU, and the XPU that you mentioned about?
Yeah, that's an important question. You're right. So, I also mentioned very important that you have clean abstractions. So let's say you're writing an AI application. You should not have to worry whether this is going to run on TPU or GPU or CPU or XPU or what have you, or FPGA. You write in, let's say, PyTorch, or you write in TensorFlow or what have you. Then the abstractions, the software-defined server that I had shown you there, I didn't get into the detail, needs to understand that, hey, here is an application that is of this type, and given the underlying hardware options I have and available resources I have, this is the platform which is most suited. So let me orchestrate the distribution of the execution of this on this underlying platform. That orchestration has to be automated. It has to be learned, right? So it should know that, among all the options that I have and among all the workloads I have, this is the best mapping of the applications to the underlying platform. And that has to happen through that abstraction that I discussed. So there has to be a programming model. The application guy only thinks about, I'm writing in TensorFlow, I'm writing in PyTorch, I'm writing in NumPy or what have you. They should not have to worry about anything else. The layer and the orchestration below has to have the smarts to figure out what is the most appropriate platform for this execution, right? And it could be varying over time because the workloads that it has to schedule are also varying over time. So among all the resources available, it has to make that assessment and also feed that back as to, okay, this is how it ran, this is how much time it took. So this kind of workloads take this much time on this platform. You need to build that infrastructure to automatically learn all that as well.
So, which means that puts a preference for something that is compiled in time rather than something that lies around as a binary, I guess.
Yeah, I mean, so you need to have a model that enables multiple binaries, to be generated. So it might be possible that, you need to preempt a job that's running on, let's say, TPUs because a higher priority job has come and you need to move this to FPGA or CPU. So you need to be able to sort of make sure that you have, all executable forms that are necessary for this flexibility of the various configurations that you are able to support underneath.
Sure. So next question is from Rajesh. So he caught up on your talk, the part where you talk about the planet scale. So he's asking, network latency is also a key challenge. And with the geo-distributed kind of setup, your data may be coming in from somewhere, or you may want to collate across or process multiple data sets. So how do you look at reducing the network latencies?
Yeah, that's a very good question, and it happens especially in live events So if you're streaming live events, let's say the World Cup is being played and it's being sort of streamed throughout the world, you need fairly sophisticated content distribution network. And thankfully, with the YouTube, Netflix and all, large part of the infrastructure that is needed to lay down the fiber, across oceans and what have you, are already done. And the other enablement of cloud has forced data centers to be opened in almost all countries. So it lends itself to a caching model where not everything has to be real-time streamed across continents, right? And then prefetching methods and all take control. So much of the latency that is seen or needs to be perceived in real time is hidden. So it used to be a challenge about 15 years back. We didn't have the kind of fiber or what have you that is now currently laid across the world. Now with Netflix and YouTube and all these being used at huge volume, the infrastructure has gotten a lot better, and the content delivery networks have gotten much better in terms of ensuring that there is a seamless experience for all users here. So it's certainly a challenge, but it's a problem that has been mostly, I would say, solved.
So there's a nice segue when you mentioned about the data centers being present in different countries and geolocations. The next question from Rohit, it talks about that there are various regulations, policies, and compliance related things like as regards data. So you also mentioned about embeddings. So wherein you are embedding some additional information in the data along you're analyzing it. But then when you're really talking about different geolocations, maybe the data is good to be in one location, but then the same processing, if your algorithm so decides that it needs to be executed elsewhere, or so the compliance, maybe European Union has GDPR coming in. So how do you build that into the algorithms themselves?
Yeah, I mean, this is becoming more and more important, right? As all countries are now demanding that data of the users in those countries must stay within that country. And so these localization rules make it harder, but it is also what is being enabled through cloud. This is now becoming a standard requirement by all countries. So all cloud providers are having to build this kind of capability that, okay, you need a disaster recovery mechanism, so you can probably have a copy outside just in case. But you also need to make sure you comply with all the local regulations and GDPR requirements and other security requirements and audit requirements. These have put a tremendous amount of work that needs to be done to build that infrastructure. It's not an engineering challenge, it is a logistics challenge, because each country has slightly different rules, and it's a logistic challenge. It's a logistic complexity that is very, very hard. Engineering wise, it's not as hard as some of the other challenges that we have seen in the past year.
Sure. Great to know your thoughts on some of these very, very interesting topics. Thank you so much for joining us today, and over to you, Anvit.
Thanks much for inviting me, and thank you for the opportunity.
Thank you so much, Rama Govindraj, for sharing your time and a very interesting talk, planet scale. Not everything can be discussed at planet scale, and I think the question and answer session also actually threw light on many topics which we never considered before. Again, thank you so much, Rama, for spending your time with us.
Thank you.
All right, next up, we have with us John Bent, Senior Director from Seagate Technology. He will be speaking on how to achieve durability at massive scale using multiple layers of declustered erasure. John, are you here with us? Are you able to connect? I believe you were having some issues with the connection.
Can you hear me okay?
I can hear you now, yes, just about.
Oh, Fantastic. Okay, so I'm going to try and share my presentation.
Sure.
I wasn't able to get WebEx working in the application, so I'm using the browser. So hopefully it works. Yeah.
It should be all right. I've used the browser, so we can see.
Okay.
Cannot see you yet though, but we are able to see your presentation. Yeah.
Oh, great. Okay.
Perfect. Over to you, John.
Yes, so thank you so much. Yeah, so my name is John Bent. I'm a senior director at Seagate. I work on our distributed S3 object storage system. It's 100% open source. It's called Cortex. So I'd urge everybody to go and check it out. And we're Seagate, so we really care a lot about protecting data. And object storage is for scale out, right? There's 175 zettabytes of data that the world is going to produce in 2025, and Seagate really wants to enable the world to store that data without losing it. So this is really not so much a talk about Seagate products, but just about decluttered parity, which is the technique that you can protect the data at scale, really have some pretty strong levels of protection for massive amounts of data. So I just want to start, with just a real simple sort of example, right? So Seagate sells hard drives, and the world has things that they want to store on them. So it seems like, it's a pretty easy problem. You store your precious, data on your disk drive, and you got nothing to worry about, right? Everything is great. Well, Seagate's very proud of our drives. They are, some of the world's best storage media. But the fact is that drives fail, okay? And I just have a list here of papers that other people have written, but some really, really good papers about the complexities of and not just Seagate drives, of course, right? I mean, all the drives, right? All the storage media. So drives do fail, okay? And by the way, this is a funny scene. This is very much sort of like an American cultural thing. But this is a funny movie called The History of the World. And this is a story from the Christian Bible. This guy, some people consider this sacrilegious, so, I apologize in advance, right? But, this guy Moses, he goes up on the mountain and God gives him 15 commandments, right? But he comes down and he drops one. So he says, whoops, just 10 commandments. And so this is really just the idea that as long as the world has had data and has had media to store the data on, no matter what that media is, whether it's tablets or what, the world has needed, pieces of rock that you etch into, right? Or paper, whatever the storage media that the world has, the world needs mechanisms, algorithms, processes to protect that data from the inevitable failure of the storage medium, right? And just, as an example, on the left is a picture of this old-fashioned device where you can hold one of those pens and write a letter, and simultaneously the other pen will write a second letter, right? So you're making a copy. And the picture on the right shows monks copying books, right, before we invented the printing press. So we've always needed these mechanisms. And what you can see is these original mechanisms are just replication, right? And so that replication technique is also a modern technique as well, right? So if you have, your precious data, you just make multiple copies of it on multiple storage mediums. But of course, the problem with this is there's a lot of capacity overhead. So one of the very first people to document the solution, a better way to protect your data than replication without the high capacity overhead, is David Patterson and Garth Gibson from University of California, Berkeley, back in 1988. That was the RAID paper. It's not a bad paper. So what RAID says is, don't make copies of the thing, split it up into pieces, and then onto another drive, store something that's called parity, okay? And so I'm just gonna, give you a very simple example of how parity works. And I'm not a mathematician. I'm somebody that understands parity just well enough, I think, that I know how to build systems that use it, but I don't necessarily really understand the math all that well. But essentially, RAID 5, which is the original RAID, is using XOR logic, right, to store data, right? And so it really does it at a large granularity, but the principle is the same. Imagine that it's doing it on just a single bit at a time, right? So you've got 4 bits of data. You've got a 0 and 3 ones, and now you have to compute a parity bit. And all you do is you essentially count the number of ones. And if it's an odd number of ones, then your parity bit is a 1. And if it's an even number, then your parity bit is a 0. So then what that allows you to do is if you lose one of those bits of data, you count the remaining ones and you look at the parity and you say, well, I'm missing one now. I know that I was supposed to have had an odd number of ones. So therefore the missing bit, must have been a 1. Okay. And giving a talk virtually is a little weird. I just want to make sure that people are still hearing me and the presentation is going okay.
Yeah, all good, all good.
Thank you. Okay, good. So before we get into the rest of the talk, I want to just introduce just a fair amount of terminology, right, that makes it easier. So, a chunk, when you split up your data into those pieces on the individual devices, a chunk is the contiguous piece of data that you store to a single device. The chunk size is, the size of the chunk. You've got some of those chunks are data chunks, some of those chunks are parity chunks. The stripe is the collection of all of those chunks that form a contiguous logical unit of data. The layout is the devices on which a stripe is stored, okay? And then pattern is the shared configuration of all stripes. So what we were just looking at before was 4+1 parity. You could do 8+2 or 3-way replication. A full stripe write is a very important concept for performance. We're not going to talk about it here. A partial stripe write is a write that's smaller than a full stripe write. It causes read modify write. So that's, the big performance inhibition that's caused by partial stripe write. And then finally, a pool, which is a concept that when we finally get to decluster parity, a pool is all the devices on which a stripe could be stored. Okay, so we're going to talk about a lot of these as we go. So one of the things I want to talk about, right, is how long does rebuild take? Okay, and so imagine that you've got a failed drive, right? So the first thing that you have to do is you have to find a replacement drive, and for each chunk that was on that failed drive, you have to read all the other chunks from that chunk's stripe, from all the other drives in the stripe. You use the parity to reconstruct, and you write the lost unit to the replacement drive. So the time to rebuild is fundamentally the time to write the entire drive. And the time to write the entire drive is the capacity divided by the bandwidth. Because what you do is you bring in a replacement drive, and for every single lost chunk, you reconstruct it and you write that lost chunk to the replacement drive. So how long does it take to write an entire drive? Okay. And so what we're going to look at, right, sort of as we go through the talk, is the evolution of data durability. What are the mechanisms that we use to protect the data, right? And we started with replication, and then we added RAID 5, okay? But what comes next, and what's wrong with RAID 5? And that's what we're going to talk about. Well, what we mentioned was that the time to rebuild was the drive's capacity divided by the drive's bandwidth. And a really important characteristic of disks is that the growth in bandwidth is approximately equal to the square of the growth in capacity. or the growth in capacity is approximately equal to the growth in bandwidth squared. This is a really important characteristic. So I want to explain, why this is. Okay, so how do you increase the capacity of a disk? Well, there's basically like 4 ways. You could increase the form factor. You could actually make individual disks a larger size. But nobody wants to do that because, data centers have standardized. So that's really not going to happen. There's also some physics reasons why it's hard as well. In the upper right corner, another method is you can increase more platters. Well, you can insert more platters. So inside that box in the upper left, you have a bunch of platters inside, and each one of those has an upper and a lower surface. And so you could try to get more platters into the box. There's between 8 and 11 platters in most disks these days, and there's not room. It's too hard to get more platters in there. So that's not really happening. The other thing that you could do is you could put more tracks per surface, which is essentially each surface is a whole bunch of concentric circles on which you store bits. Each of those concentric circles is a track. You could try and make those tracks skinnier and put more tracks on the surface. By the way, some of you may have heard of shingled disks. Shingled disks was a particularly aggressive way to add more tracks per surface. That's actually also very interesting to read about. We're not going to be talking about it here, though. And finally, in the bottom right, you could, on each track, put more bits. So the problem, and so that's how do you increase disk capacity. And now what about increasing disk bandwidth? Well, one, you could spin faster, but that's really hard. The disks are already spinning very fast. 2, you could try to access more tracks simultaneously. Or 3, in the bottom right, more bits per track, which, by the way, was one of those techniques to increase disk capacity. So adding more bits per track increases both bandwidth and capacity. The reason it increases bandwidth is because in each rotation of the disk, there's more data passing under the head. The head is the part of the disk that actually reads and writes the data. So why is the growth in bandwidth approximately equal to the square root of the growth in capacity? Well, it's because we've got these 4 ways to increase capacity and these 3 ways to increase bandwidth. But what we see is that actually 2 of those ways of increasing capacity don't typically happen, and 2 of those ways of increasing bandwidth don't typically happen. So typically, it's those 2 factors. Every time Seagate has a new drive, it's got an increased capacity because of those 2 factors, and it has an increased bandwidth because of that one single factor. And one of those factors is the same. It's common across both. Now, having said that, there is something very cool coming from Seagate. Again, we're not going to talk about it in this talk, called Mach 2, which is a way to access more tracks simultaneously. So that does occasionally happen, but for the most part, it doesn't happen. Okay. And what we see is that the bandwidth of a disk, in generation n+1 is really the bandwidth of the disk at n times the growth in bits per track, right? So the disk that you had in 2019 is faster than the disk that you had in 2018 by the growth in bits per track. And the capacity of the next generation drive is essentially the capacity of the last generation drive times the growth in bits per track, also times the growth in tracks per surface. And the growth in tracks per surface is approximately equal to the growth in bits per track. And so therefore, the capacity of the next generation drive is effectively the capacity of this generation drive times the growth in bits per track squared. Therefore, the growth in bandwidth is approximately equal to the square root of the growth in capacity. All right. So now, when you take what we said before, that the time to rebuild a lost drive is the capacity divided by the bandwidth, and you also take into consideration that the growth in the bandwidth is approximately equal to the square root of the growth in capacity, that means that your probability of data loss with RAID 5 is approximately 1, is approaching 1, right? Because what happens is every new generation of drive takes longer and longer to rebuild, and eventually it takes so long that it basically becomes, you know, probabilistically determined that you're going to have another error during the rebuild. So that's why RAID 5 is no longer good enough. You know, and here's some graphs that show this, right? That the time to rebuild in the upper left is going up, 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 and the statistical probability of failure during rebuild is approaching, you know, 1. That's the blue line in the bottom right. The orange line is RAID 6, which we haven't told you about RAID 6 yet, so just ignore that for now. Okay, so what comes after RAID 5? RAID 6. So what is RAID 6? We've got the same thing. We split our precious data into 4 pieces. We added 1 drive's worth of parity, and now we have another drive, and we add another piece of parity. Now, some of you that are familiar with RAID might be thinking, hey, John, this is wrong. You know, most RAID systems don't have dedicated parity drives. That's true, but I'm ignoring that for now. Just for the purposes of this talk, this is, I hope, sufficient. So what is the parity on that second drive? Again, I'm not a mathematician. I don't really know it all that well. But the way that I think about it is with high school algebra. If you have 2 equations, you can have 2 unknowns. And by the way, that's a little bit of a hint of erasure, right? If you have 3 equations, you can have 3 unknowns. So now imagine instead of a single bit that you had integers, right? And so you want to protect those 4 integers. Well, what you could do on one of your parities is take the sum of those integers. And what you do on the second parity is take the product of those integers. And again, this is not actually how it works. One of the major reasons why it wouldn't work like this is because of integer overflow. But conceptually, this is the right idea. You know, and you need to be a mathematician, I think, to understand this, or certainly more of a mathematician than I am. Okay, and now, right, so you lose 2 of your disks, no problem. You set them equal to x plus y. You have 2 equations. You do the math. You restore them. Okay. So what comes after RAID 5? RAID 6, right? RAID 5 was good enough for a long time until it wasn't. Well, what comes next? What's wrong with RAID 6? The same exact thing that was wrong with RAID 5 is also wrong with RAID 6. RAID 6 helped, it helped for many years, but eventually the drives got so big that even RAID 6 wasn't good enough. That your probability of data loss, even with RAID 6, is approaching 1. So what comes after RAID 6? Sort of declustered, okay? But before we get to declustered, we need to talk about large systems, because declustered parity only works in large systems. So first imagine that you've got this large system with 100 disks inside, and what you can do is you can break it up into 10 fixed groups of 10 drives each. And imagine you've got these 2 hot spares. So what you could do then in each of those disk groups is you could do RAID 6. And now when a drive fails, you have to rebuild that drive to one of the hot spares. And this is still that same exact RAID 6 problem. So if you have 100 drives, the easy thing to do is to split them up into fixed groups and do RAID 6 inside each fixed group, but you still have that same rebuild problem. So the question is, how can we do better? And the answer is we can do better with decluster. So in declustered, there's a couple of key concepts. So the first concept is virtual spares. So first of all, when you look at the picture of the 100 drives on the left, you can see there's just one big red rectangle around them, okay? So they're all in one pool. And the other key thing is that we've left a little bit of virtual spare space on every single drive. And so when you talk about RAID, you often talk about, or when you talk about erasure, you often talk about N plus K. And so that's how many data chunks and how many parity chunks. When you talk about declustered parity, you often talk about N plus K plus S, where it's data chunks and parity chunks and the amount of spare space that you have. And so there's the other key concept in decluttered parity is that there's a rebuild phase and then there's also a replay phase. I'm going to show that in a second. Then there's also a pseudo-random layout. So every stripe goes to a different random N plus K drives. So say you're doing 8 plus 2, not every stripe goes to a different one, but pseudo-randomly, all of your stripes are distributed across all of the drives. And what that allows is your rebuild to be 99 to 99. When a lost drive fails, when a drive fails, when a drive is lost, every chunk of that drive is part of a stripe whose siblings are 9 pseudo-randomly selected drives from the entire pool. And so for every chunk, you're going to pseudo-randomly rebuild that chunk from a random set of the 9 drives. And so with enough chunks, which there's lots of chunks on a drive, you're using all of the drives evenly. And also, you're rebuilding into the virtual span. So remember, in RAID 6, our time to rebuild was bound by the time to write in a single drive in its entirety. In decluttered parity, the time to rebuild is the time to write a disk's worth of data across all the drives. So it scales with the total population of drives. The larger your pool, the faster your rebuild. So, imagine you had a failure. This drive failed, and I'm not going to draw the arrows. But what happens is all 99 of the drives are writing to all 99 of the drives. So that's 9,702 arrows. I wasn't able to draw them. I apologize, but you can imagine. So the rebuild time scales with the population, right? The size of the pool. And so this is just a super simple model. The entire model is right there. You can get it if you want. Imagine you've got a 20 terabyte capacity drive, and it's got 200 megabytes per second. Then the time to rebuild, if you're using fixed erasure groups, is about 27 hours. And with fixed erasure groups, it doesn't matter how many drives are in your pool. But with decluttered erasure, you can quickly get down to a rebuild time that provides a very high level of durability and availability for your data. Okay. So what comes after RAID 6? Declustered RAID 6. Then what comes after RAID 6, even decluttered RAID 6, because even decluttered RAID 6, can be better, is decluttered erasure, where instead of 2 equations, 2 unknowns, you have K equations, K unknowns, and to the best of my understanding, the math becomes even more complicated. Now, by the way, what was happening in public cloud was public cloud started doing 3-way replication. It was doing decluttered 3-way replication. And now public cloud is doing decluttered networked erasure. And because, I do work for Seagate, I do want to mention that decluttered RAID 6 and decluttered erasure are available within our Core Vault product line, and decluttered network erasure is available in our open source Cortex distributed object store. What comes next and what's wrong with these? Okay, so here is 2 existing approaches for data durability and availability. So on the left, is something that people refer to as hardware local decluttered erasure, right? And so a lot of systems, some of the HPC systems, Lustre, PBFS, BGFS, are using hardware local decluttered erasure, where at the network level, they're not adding any protection at all. And they're relying on high availability server pairs and hardware RAID to protect the data. And there's sort of, a little bit of a backlash. I apologize, my font somehow changed size. It used to not be overlapped on itself. But on the right, you have, another approach, which is software network decluttered erasure. And, you sort of think of this as a more modern technique, although I'll mention that it's been around for a while in systems like Panasys, where at the network layer, you do the erasure. And now you just use JBOD and you just use, a single server. So Cloudian, ActiveScale, a bunch of solutions use HDFS, Hadoop use, this solution.
John,
well,
John, we're very short of time. We have about 5 minutes to go. Maybe you could summarize and we'll take some questions.
I thought I started at 10:10 and I had 40 minutes.
Yeah, we were just waiting for, you can just, we have a few questions as well.
I mean, yeah, I can certainly jump to questions. So, but I thought I had 15 minutes left. Are we doing 15 minutes for questions?
No. I'm saying, or maybe you could just speed up a little bit for your slides, maybe, and
I'm sorry.
Towards the end.
Okay. So, how many more minutes do you want for me to talk? Because
we've got about
8
to 10 minutes to go.
Including questions or not including questions?
That would be including questions, please.
So what you see here in this graph is that this is a really good paper from Google about availability. And the graph is showing failure events, okay? And the failure events have a particular signature. And so the size of the circle is how many times a failure event of that signature occurred. So big circles, the event occurred a lot, and small circles, it didn't. And then the vertical axis is the number of drives that failed at the same time. And the horizontal axis is across how many racks were those drives distributed. And so that's why there's nothing below the diagonal, right? If you had 10 drives fail, the most racks that they could have been on is 10 racks. And so I think that the blue oval, those failures, is a well-known problem. And that's why, systems like Hadoop did rack-aware replication. But the diagonal orange oval is a surprising oval, right? Because that's a bunch of disks failed at the same time. There's a temporal correlation, but not a spatial one, right? And so sometimes, there is an explanation for it, and sometimes it is a spatial relationship. It could be a bunch of drives at the top of the rack because there was a sprinkler event, or there was a flood and it was drives at the bottom, or, the fan went out and it was drives on one side, or it could be, the bathtub mortality curve, a bunch of drives all got old and failed, or it could be a firmware, lots of reasons. But so if you look at these two existing approaches, the hardware local decluttered erasure doesn't protect against the aspatial failure bursts, and the software doesn't protect against the spatial failure bursts. So what we're doing in Cortex is multi-level, right? And so I guess I don't have to get into this. But essentially what this does in Cortex with our live rack product is it protects against a larger number of failure events. And specifically what it does is it gives you, at comparable capacity overhead, a multi-level configuration provides more nines of durability. So if we get back into this, you've got basic multi-level erasure, and you've got multi-level aware erasure, and that's what LiveRack is. Okay. With that, I'm happy to take any questions.
Thank you so much, John. Really nice talk. And I think for every storage developer, it's a very good information to know like how the lower layers work about to make sure that the data can be returned, what was saved to the disk. And apologies that because of the online thing, transitioning between slides, we end up losing some minutes here and there. So, well, I have one question from your talk. You mentioned about how Seagate goes about adding more capacity and bandwidth to the system. So, and one of that you mentioned was that you add more bits to every track. But wouldn't that mean that you're packing more things closer together, and probably you will reach a stage that closer to just one molecule or few molecules are just representing a bit here and there. And that might result in much higher chances of losing data because of some interference or bit flips, which would be far more than if it was less densely packed.
Yeah, that's a great observation, and that's 100% the challenge that we have in the storage industry. The tighter we put those bits, the harder it becomes to read them and interpret them correctly, and the more likely it is that when we write, one track, we're going to mess up another track. So the recent innovation that we have at Seagate is Hammer, which is essentially it's sort of cool. We put a laser inside the head and we shoot a laser at the track, and I don't understand the physics, but it turns out that if you heat up the track, it allows you to to get that density with a lower probability of those failures that you get with the density. So, Moore's law always finds a way to survive, right? The disk industry was starting to plateau a little bit, and now we found this Hammer thing, and we believe that the future looks really good. We've got 20 terabyte, 30 terabyte, 50 terabyte drives all on our roadmap.
Well, I would like to have few of those for saving my data at home too.
Yeah, you can save a lot of data.
Right. So actually, I had few more questions, John, but then since we are running short on time, I'll have those questions sent across to you offline and maybe get those back to the audience. Thank you so much for joining us today. And
yeah, absolutely. Thank you for the
this.
invitation.
Thank you so much, John. John Ben, the Senior Director at Seagate Technologies. Thank you again for spending the time with us at the IEEE Data and Storage Symposium. With that, it's time now for our next session, and that is on AdaSwarm, Augmenting Gradient-Based Optimizers. We have with us Professor Snehanshu Saha, Associate Professor CSNIS and Center Coordinator for the Anuradha and Prashant Palakurti Center for Artificial Intelligence Research, that's AppCare, at BITS Pilani KK Birla Goa campus. On your screens now, Mr. Snehanshu Saha.
Thanks for inviting me. I already can see in a one-day symposium like this, there is information overload, and I'm sorry, if I have to pile on you further, but my talk is going to be slightly different from the previous two talks, although I would say that I enjoyed both talks very much, John's and Rama's, where both speakers actually spoke about the storage capabilities and processing capabilities of data and what kind of data systems we live in and use, right? My focus, which is primarily based on what I do my research on, is more on the method side. So I hope my slides are visible. Sorry.
Yeah.
Yeah. Okay. Yeah. Okay. So
All good now.
Yeah. Okay. All right. So just one thing before I begin is that you would probably see a lot of slides, and of course, in the interest of time, I wouldn't have the time to go through all of that. But I would like to make my presentation sort of self-contained, because After every presentation, at least when I'm in the audience, there are more questions than answers, right? And so I have already shared the slides with the organizers so that, I mean, if any one of you is interested, I mean, you can actually get the broader picture. Okay. All right. Having said that, I would also, like to, I mean, love to take your questions offline after the talk, because right after the talk, I have to actually rush to a class that I teach at 12 noon. Okay. So the broad idea of today's talk is that given large streams of data that come in, I don't know why slides are not changed. Okay, all right. Yeah. So given large streams of data that come in, how do we write methods that could scale? Okay. I mean, and when I say scale, I mean scale between the CPU and the GPU, right? I mean, if it's a edge environment, of course, the algorithms have to be redesigned and retrained, right? And I was also requested by Prashant to talk a little bit about some of the unusual things I do with data, and one of which is astronomical data. Okay, so I'll just talk about a little bit about the data first, and then I will present the challenges, and then a very broad landscape view of how we try to solve those challenges. Okay, so I'll begin with the astronomy data. Primarily the kind of astronomy data that I work on are exoplanets, which are planets living outside our solar system, right? And it has been a relentless search by NASA and now majorly by the Chinese Academy of Sciences to try to find life outside the solar system and in one of those planets, right? So there is a very large data set curated by one of NASA's largest observatories in Puerto Rico, where they have an extremely large telescope. And now with the advent of the James Webb Telescope JWT, we have streams of data coming in, and every day there are, I mean, at least a few hundreds of exoplanets being discovered, right? So the data is sort of unstructured. We have, thousands and thousands of rows and about 70 columns, which are the features of the exoplanets. The trouble with astronomical inference is the following. One is that the training accuracy or the validation accuracy is not the only thing. So if you write a method and you say that, okay, my training accuracy is about 100% and my validation accuracy is 98%, that may not mean much for the astronomer. For the simple reason is that a lot of these astronomers, in fact, most of these astronomers do not actually believe the annotations that come with the data. So there are some problems with the labels itself. Okay, so what would they like to know is that, okay, you gave me some accuracy, fine. What I would do is I would have some measure of my own, which is completely has nothing to do with machine learning per se, right? To cross-validate. So the efficacy of the method that you write, I mean, depends on this kind of cross-validation, which is post facto, right? At the same time, you would actually require your algorithms to be fast. So at least as far as we are concerned, storage is not much an issue for us. Processing is, right? And the inferences have to be really, really fast. Now, in the sense that, the speakers before me spoke at length about the architectural solutions on the hardware side that you could impart so that, you could do things really, really fast, okay? We assume that we have such state-of-the-art architecture, but even then, there are lots of data sets like this, exoplanets, and then there is this Sloan Digital Sky Survey and the Galaxy Survey, which actually maps the millions and millions of objects, which are stars, galaxies, and quasars on the space, right? And these are objects that we need to first detect and then classify, right? Okay, and these are really, really complex problems. So what do we do? So the corpus that we have is too big for training, too big. I mean, you cannot actually take the entire data for training. So what you do is you have to judicially choose a subsample or a subsample set, right? So in other words, if you think of in terms of, vector spaces and stuff like that, you need to have a sort of a subspace projection from your vector space of data points, okay? All right, so that in terms of the statistical distributions, the subspace that you projected your data onto are like sort of very, very similar. At the same time, while doing that, you need to make sure that your classes are representative of the data, right? And if I choose one subspace over another, the inferences will not change. So these are some of the mandates that we have in terms of, while we choose a slice of the data. And the next point is that how well does it generalize, right? Okay. And in order to do so, how many samples you actually require in your subspace to train? Because I mostly work on deep learning and neural networks, and we all know that deep learning and neural networks are data hungry, right? They require a lot of data, right? And if each and every time you actually require your subspace, like for example, this 10 to the power 7 million objects, I mean, if I can take just one slice with 1 million objects, I mean, it's not small enough, right? So I'll have to choose judicially in such a way that the distribution is representative, right? The inference is fast, and it does generalize pretty well. And when I say generalize, I have to sort of quantify that generalization in the sense that what sort of statistical confidence can I impart to my inference, okay? Then the other important part is how many iterations do I really require to converge, okay? Is there a cap, is there a bound that I can put on that, okay? So these are astronomical data sets that come with sort of different challenges. I actually wanted to show you something else as well, and I hope my internet connection is steady enough so that I can just show this to you. Or probably I'll need to just go back, and it's probably something that I need to do in terms of have movie that I want to show you. I don't know, is my movie screen visible?
No, not yet, Snehanshu.
Went wrong here. I mean, in the codec file. So forget it. I'll just go back to my slides and try to run this. Do I need to do something in terms of the sharing?
Probably share the application. Instead of sharing application, share your desktop. I think you just share the application at the moment.
Just shared one window. So do I
share entire screen? The option share entire. You can stop and just share entire screen.
Okay, so here, let's see whether this, can you see this? Yeah.
Yeah, it's still sharing. I think just give it a moment. Yeah, we can see the browser now. Yes.
Okay. Do you see this now?
Yes.
Okay. All right. So this is another example of continuous data stream. So it's just one example, one person, driving a manual wheelchair, right? And so the problem that we were, trying to solve at that point of time is that given there are different surfaces in the United States and China, and there are multiple people using manual wheelchair and power wheelchair data, I mean, we collect the data at some certain point of time, and can we infer in such a way that from the vibrations of manual wheelchair data only, can we infer the surfaces where a power wheelchair navigates to, right? Okay, so it's continuous stream. There are multiple users, so we get a lot of data. So what you see in the screen are my student who is on driving the wheelchair and my collaborator, Professor Bhaskar Rai Chaudhuri at Miami University. Okay, so I'll just stop this now and go back to the slide. So So these are the kind of problems that we sort of try to work on. So the key for us, I mean, is not on the hardware side, but rather on the approximation and fast optimization techniques. Okay, so at least here you see that there are a small slice of data or a moderate slice data which we will use to actually infer on the total corpus. Okay, so I mean, we have moved from small data pattern recognition, which had lesser training issues because the corpus was always small, right? But there are certain things from small data pattern recognition that we could actually import and use it. Like for an example is the support vector machine kernels that are used in convolutional neural networks, right? And so on and so forth. The reason why people like small data pattern recognition methods is those are elegant, right? Unlike the neural network based methods, which are now becoming elegant, a little bit more sophisticated. But primarily, when you say neural networks, people say, oh, it's a black box, right? It's a stochastic method, primarily, right? It's a function approximator, but there are many, many things that we think are not controlled by us, right? Okay, but the turns out, so and there are then very large language models like transformers, which has like 784 layers. So the questions that we need to ask is that at least for certain data sets which are large enough, right, may not be similar to a natural language data set, does it still require that many hidden layers? Because if you are using that many hidden layers, you're also in a fully collected neural network, you are using that many weights and that many hyperparameters to tune, right? So, and then there is your learning rate. So there are different components at play here, right, which needs to be controlled simultaneously. And that could be a really, really tedious task and will lead to higher inference time, definitely higher training time. Sometimes training time runs into days and so on and so forth, right? So there are certain patterns which I call is a fragmented pipeline that we have been now able to slowly evolve into. Not entirely solvable because when we say generalization in a deep neural network setting, there isn't a single solution for all problems. It doesn't work that way, right? But there are some problems based on the implicit nature of the data present in the problem that we are able to solve a few of them, okay? At the same time, I think Rama was mentioning about useless AI or something similar. He did not exactly say useless. I mean, he was talking about AI that makes sense. So your interpretations, I mean, your inferences need to be interpretable, right? I mean, you cannot build a system and then say that 110 blood pressure is, I mean, your model 110 blood pressure is actually risky, right? Or something like that, okay? So, once again, back to an astronomical data problem. And this is the kind of a separation problem between stars and quasars. So what you can see is that in space, right? I mean, if you think of this as a manifold, in space, what happens is the data is not easily separable. It's not, okay? So you cannot really use something like a linear discriminator kind of a thing to separate the yellows from the purple ones and so on and so forth, right? Here people make mistakes. I mean, they tend to use a feature which should not be used. For example, I was actually talking about a post-factor cross-validation, right? After you are done with your training and testing. So that post-factor cross-validation is done using redshift of stars and quasars. So it turns out that from the catalog of 10 to the power 7 million objects, there are about 75% of stars and quasars which can be separated by looking at their redshift values. Okay, so this is what the astronomers like to use, to see how somebody else's machine learning model is good or not. However, since many of these objects are easily separable by redshift, you cannot really use redshift as a feature when you're training the model, right? Because your machine learning model isn't then doing much. I mean, what do you need your machine learning model for, right? So this is the problem when, I mean, these are some of the domain knowledges that you need to impart when you do inferences for astronomical data. So the challenge, do you see the challenge? The challenge is you are not using redshift as a training feature. You're using other features like spectroscopic, different wavelengths, right? Different wavelengths that are captured, right? But when your inferences come out, your classification accuracies will be measured based on the redshift values. And you are not able to use redshift at all when you are training. Okay, so in order to, but then redshifts are, sort of also spatial entities. So all of this, I would like to see this as a manifold problem. I mean, do you know what a manifold is? So let me give you an example. So let's say I have some curved surface, right? And imagine an ant moving along that curved surface, okay? So at any point of time on the curved surface, at anywhere at the curved surface, if the ant stops, right, and looks at surroundings should appear as a plane, irrespective of whichever dimension the ant is, right? I mean, a very simple example of a manifold is the Earth, which is a sphere where we live, right? But when we walk, I mean, and we take a look around ourselves, things look flat, right? I mean, this is why many people are, they believe in that flat Earth kind of, that's utter nonsense, but that's what it is, right? So that's what a manifold is. So a manifold could be like a sausage, right? A sphere, a torus, like these are the manifolds. So the data, the manifold theory comes into play is that the data is being thought of a manifold, distributed in space, right? And obviously, in higher dimensions, what happens is the distribution, the decision boundaries are fuzzy. I mean, there are no clear decision boundaries. They are mostly nonlinear. So that is why neural networks come into play, and they have become extremely popular because neural networks are supposed to infer these decision surfaces quite well, given that you feed the network with a lot of training data points. Okay. So, but I mean, so there are several control agents, what I call as control agents in a neural network, is that I think of neural networks in the following sense, is that the following. So you think of certain architecture, whichever architecture, you can take a sample architecture, right? And as I just described, your data is a manifold, right? It's distributed in space. I mean, if I may show you a picture, it's something like this. Okay, all right? Or and a lower dimensional representation of the same manifolds looks something like this, right? Where you are supposed to separate the red points from the blue ones, okay? Now, so therefore, in a neural network, there is some forward pass that goes on, and then there is some backward pass, and based on whether you have inferred correctly or not, you need to backpropagate your errors, and you need to update certain things like possibly you have chosen wrong weights, probably your learning rate is not chosen correctly, and all that. So a lot of this used to be based on heuristics, okay? I mean, I would choose, let's say 0.1 learning rate, it doesn't work, let's choose 0.01, so on and so forth. Maybe learning rate with an exponential decay, right? Okay, what kind of activation functions should I choose, right? Okay, so you know that those who are familiar with neural networks know that people started with the sigmoid, right? And then some problems were discovered of sigmoid, like vanishing gradients, flattening at the ends, right? I mean, so it does work very well if your data is normalized between 0 and 1, not so well when the data is not normalized. And then people say that, okay, all right, here is something else. And then there is something else. So every year, if you actually look at the deep learning literature, you will see a bunch of different activation functions emerge, okay? And this has sort of become a cottage industry, all right? So the point that we try to push, and me and my students, is the following, that the activation functions that you use or propose needs to be trainable. And this is particularly relevant in the context of inferring your deep neural network based data distributions and class distributions, is because the data, as I said, you think about that manifold, right? The shapes change, okay? So you need to have an activation function which would be able to align itself with the change in the shape of the data, because of their inherent latent class distributions, right? So you need, it's an activation function that you should be able to train. At the same time, the activation function should also be nonlinear, right? Because what you are trying to do is trying to infer the inherent nonlinearity in your data.
I believe he's having some network trouble. We'll just give him a couple of minutes. We'll just see if he can join back in. Sir, if you're still connected, maybe you can turn off your video. Yeah, seems like there is some network trouble on Professor Snehanshu Saha's end. If you're just signing in, this is the IEEE Data and Storage Symposium Winter Edition in December 2021. We've got a lot more sessions. We also have a panel discussion coming right up. Until then, we have Ankit. He's here on screen. Ankit?
Yeah, so what an amazing set of sessions covering so many different things since the morning, right? We started off with technologies, trends in the memory, and then moved on to adding compute to that memory. So with computational storage, we had Tom and Jim Handy talk about it. And then was the users of all of this, the planet scale systems from Rama Govindraj.
Yeah.
And then we had a session with John Bent, really going into the core of the storage that is close to the hardware itself. How do you make sure that you get back the same data that you wrote? Because, well, that's what storage is all about. You must get back what you wrote. So how do you feel about these sessions today, Anvit?
Many of these sessions were something which give me some new information, especially something like Rama's session, which spoke about planet scale. But there were so many things which we do in normal life, just to think about planet scale and those small issues. Like, for example, photographs. Just a simple example which he took was enough. Like, imagine everybody on the planet uploading photos, and where will all of these photos be saved, and how will you scale up to ensure that everybody doesn't run out of space? And the downside, or rather the other end of it, is where John Bent was speaking. Where will actually all of this be saved, and how will you pack it together? So lots of new things to learn, and I believe that's what these IEEE sessions are all about. The new trends, how we are adapting to the newer technologies, and how older things are getting shelved along the way, I believe.
Yeah, so something really interesting, like the era before YouTube, when we used to use Real Player and maybe Windows Media Player, and trying to watch those small screens, and maybe the pause in the video was a given thing. And now you can flick out your phone and, well, Netflix or YouTube videos or anything else, you can start watching anywhere. So all of the video compression and things, well, some of these things you feel like, well, it's assumed, it's already there in the system, but then what all goes on behind the scenes to get it to you?
As in, imagine streaming 4K on our older connections. I don't think we would even get away with 1 second of data in our older days when we were actually using this. Having said that, let us just have a check whether Professor Snehanshu is back. Oh, it looks like he is. Sir, you seem to be muted. Could you please unmute?
Right. So I'm sorry. Okay. I mean, I sort of lost the connection. So really sorry about that.
That's all right. So maybe you could turn off your video if there is a network issue on your end.
It shouldn't be. Okay, I'll just stop the video. Okay. All right.
You can. All right. So over to you, sir.
Thank you.
We just a time check though. We are about 12 minutes away, so just a time check.
Understood. Okay. All right. Okay. So I mean, enough of the landscape. So what are the usual suspects? So I'll just focus on two things. One is what kind of learning rate shall we choose? Can the learning rate be trainable? And if the learning rate is trainable, does that help us? And the second one is there a way to without computing so many gradients, because there are millions of error gradients that we need to calculate, right? Instead of calculating so many error gradients, is there a way to approximate the error gradient? Okay, so these turn out to be critical operations that helped us achieve a pretty good performance benchmark across multiple data sets, but also we have been able to cut down the training time to at least sometimes 1/10, sometimes 1/50th, and so on and so forth. Okay, so the Adder Swarm, which is the title of the talk, is a state-of-the-art optimizer that came out of this effort. Okay, so what happens really is that if you have some standard loss functions, okay, which have some nice properties, like for example Lipschitz continuity. Now what is Lipschitz? Is that what it says, roughly speaking, is that if I have inputs.
Mom, can I tell my today's class?
Yes. Same problem.
Sorry, somebody else's. Okay. All right. So if irrespective, I think somebody is can someone mute their microphone?
Request to all the attendees. Kindly.
Yeah, thank you. Okay. So what really happens is the following: is that, you know, irrespective of the input, like it could be, your input could be large enough, it could be distributed in space, but this particular nice property helps us contract the input to a very small output. So the point is, irrespective of if your function has this property, irrespective of your input, your output is always bounded by a positive number. Okay. How does this help us? It helps us in converging, because what happens really is that neural networks are optimization problems. So a correct classification of data points to multiple classes actually amounts to lowest error, right? Okay. And the idea is to find out your local minimas efficiently. We don't really bother much about global minima, because over a very large corpus of data set and an extremely complicated architecture, right, the complexity of your algorithm increases exponentially, right? So local minimas are good enough, right? That will help us actually settle it out, right? So what really happens is, if I have that nice property, what kind of learning rate shall I use? I can actually set my learning rate as the inverse of that Lipschitz constant of that particular function. So for example, if your loss function is a mean square error or a cross entropy, right? You have to find the Lipschitz constant, which is an analytical computation, and then you take the inverse of it. Okay, and that inverse of it you use as your learning rate. Clearly speaking, that means that your learning rates, and it also depends on the size of your data. So your learning rates will change at every epoch. So it's not a fixed learning rate. Okay, but what we have, there are other implications as well. If I use such a learning rate, then we were also able to show, and people have been able to show, that your changes in the weights, which are sort of random, which you thought you cannot control, your changes in the weights are also bounded by 1, which means you do not have large weight updates between successive iterates. Okay, so that's something nice that actually helped us converge really, really fast on very extremely large data sets. Okay, I don't have the time to talk about another data set, which is a gene expression inference, right? Anyway, so that's one thing. The other thing is, it's about, you know, trying to get to as close to the global minima as you can, right? So what we did, and then you know that your loss surfaces can be really, really complicated. I mean, it doesn't have to be a soup bowl. It can be like in the shape of a Pringle chips, where you have a saddle point, which means you do not have a minima, you do not have a maxima, right? So you cannot compute the exact gradient. So is there a way to approximate your error gradients? So it turns out we sort of came out with a formulation, an analytical formulation, where we show that the error gradients for all the data points, I mean, for all the weights across, can be approximated using the parameters of a meta-heuristic algorithm known as particle swarm optimization. And there is a variant of particle swarm optimization that we have to write first. Now, those who are familiar with PSO will ask me, okay, particle swarm optimization also has parameters, right? Hyperparameters, you need to tune those. The answer is no. We actually kept the particle sizes and the values of the C1, R1, and C2 are fixed. Okay, as I know, I do not experiment with the learning rates if I'm using, and also the best part of this approximation is agnostic to the loss function. So irrespective of whatever loss function you use, right, based on the kind of problems that you are trying to solve, I mean, you would be still able to use this kind of an error gradient approximation. Okay, so these are the primary, because the thing is about deep neural nets, which Mike has expressed, many times in many places, is that with the amount of data that comes to us, if we are not careful about the inherent statistical properties of the data, then it will lead to an epidemic of false positives, right? Which exactly what he said. And we have already seen examples of that. If you are familiar with that MIT tiny image dataset fiasco, right? And that was so disastrous that they had to pull down the data from their server and they had to issue a written apology, so on and so forth. Okay, so I mean, I'm going to skip, I have to skip many slides, right? But the point I'm trying to make is the following, is that at least the way we look at optimization and the way we look at inferring from very large corpus of data sets, the tools that we use are different, but they do sync well with the hardware tools as well, at least as far as central processing units or graphical processing units are concerned, right? So the title of my talk, if you notice, is that bandit optimization. So the idea is to tame the bandits, right? So the last thing that I would like to say is that when I say that the activation functions are trainable, I mean, what I imply is that I would just parameterize my activation functions, right? And these parameters are responsible for changing the shape of the activation function as the shape of the data changes in the manifold space, right? But then once again, the question is, how do I get a very good values of these parameters? Once again, the answer is the same. I would actually use backpropagation and error gradient upgradation, and I'm not going to experiment with the learning rates, try to tune it. I would use that particular loss function and use its Lipschitz property, and most loss functions are Lipschitz. However, this does not work with Huwaei loss kind of loss, but most other loss functions, this works, right? So this is not a solution to all of your problems, but it turns out, at least for the kind of data sets that we have so far worked on, and that's pretty diverse from astronomy, biology to the wheelchair data and other systems data, it has worked so far, okay? And the other important part is, if you do these things right, you actually need only a polynomial many samples to train your data well and achieve very good generalization error. And we have shown that with a statistical confidence of 1 minus delta, where delta could be 0.05, which means you have a 95% statistical confidence, you should be able to infer your class levels or class probabilities quite well. Okay, all right. So, so what we always do, I mean, when we benchmark our models, and I think this is a good practice, apart from the standard benchmarks like accuracy, loss, epochs to converge to optima, right? The CPU memory utilization and carbon footprints. And we would like to compare our method with some other methods and try to show that, okay, at least in terms of carbon emission, our methods are more efficient without compromising too much on the accuracy. Okay, so I think one important thing about, because now that the architecture and there are edge systems, it is very important to know how to redesign your models so that it runs on edge systems. I mean, you may ask that, okay, does your models run on edge systems? I mean, I would say with moderate success, but we're not really exactly happy with what's happening on. So what it means that there needs to be additional changes that we need to make, both on the on the mathematical foundation side as well as on the hardware side. Okay, all right. And I think I will stop. I did not get into the math because I don't have the time too much, right? But I would just say one thing, that the approximation of the error gradients, we pretty much rely on Taylor series approximation. And that explains why it's a very good local approximation and not so good global approximation, because Taylor series are really good around x is equal to 0 and in its neighborhood, and not so good away from it, right? I mean, which is fine, which is exactly what we needed, because we actually do not need to approximate the loss function everywhere or the error function everywhere throughout the landscape. We just need to do it in a small neighborhood. Okay, so with this, I would like to conclude and probably take questions. If I think I lost, I mean, you're speaking. Yeah. I can't hear you. I lost it. I'll just stop my video. Can't hear you actually. Hello. Hello. Sorry. I mean.
Oh, all right. Some technical glitch, Professor Saha. Actually, when there was some noise on the call, I think everyone got forcefully muted, so I was unable to unmute. So it was a really nice talk and a great way reducing the problem space and trying to resolve by getting an approximation. So I had a question from a related space. So with all of these problems come huge floating point numbers, and you can have like multiple bits in there, but then with either you can have speed or you can have accuracy. You can actually maybe reduce the number of bits. So what's your take or like heuristic that you put in to have the right speed and also the accuracy? How much of the data set should you try to cut down, and what's a good way of testing that out?
Right. I mean, okay. I mean, it's a very, very good question. So there is no, as I said, right? I mean, in one of the theoretical results that we proved, we showed that based on the number of classes that you have, you need polynomial many samples in some of the parameters of the data, right? So that will give you an upper bound of the subspace that you need to choose from your corpus. Okay, so it turned out for us that for that particular wheelchair data set, which has close to 1.5 million data points, I think if I remember correctly, I think about 1,200 data points are good for us to train. Okay, and of course, there is still something to explain that I'm not sure myself. I'm not sure why by choosing such a small subset, we are still able to actually achieve pretty close to 99% validation accuracy. Okay, and we have checked multiple times. I mean, there doesn't seem to be anything wrong in it, right? But that is for that particular data set. It's not a standard that you can use. So if your data set changes, that bound will also change. And regarding the second question, I mean, in terms of speed and accuracy, I think at least 5 years back, there was this obsession with accuracies, like you have to have 100% accuracies, 99% accuracies. I think people realize now that with the multitude of challenges, I mean, it's not only accuracy, you see, it's also, as I was giving examples from astronomy, your training accuracies could be complete nonsense. I mean, if your domain experts are not able to verify, they are not able to reconcile your inferences with what they already know, right? So it's probably speed that I would give more emphasis on without compromising too much on an accuracy. Okay? And some of the floating point things can also be taken care of even if you use truncated polynomials and stuff like that. And you can probably control some of these floating point operations as well.
Sure, right? Sure. Yeah. And it is right, like there are certain data sets, especially like analytics around fraud detection and all, where you really cannot compromise on the speed. And thank you so much, Professor Saha, for squeezing in time right before your class starts.
Yeah,
It is really great to have you here. And there are more questions, but then if we had the luxury of time. And thank you so much once again. Over to you, Anvit.
Thank you so much, Professor Snehanshu Saha, for sharing your thoughts and also letting us know about RSWARM. Thanks again for sparing the time, sir. All right, then. If you're just signing in, this is the IEEE Data and Storage Symposium Winter Edition brought to you by IEEE Bangalore Section and Huawei Technologies India Private Limited. Till now, you've been listening to sessions, but it's always better to be able to listen to different points of view and opinions on the topic. We have with us an action-packed panel discussion lined up for you today. We have with us Mayuk Datta, Distinguished Technologist at Hewlett-Packard Enterprise, Niranjan Pendarkar, Architect Storage at Nutanix, and Giridhar Yasa, CTO at LendingCard. Moderating the panel is our very own Ankit Mathur, Chief Architect Storage at Huawei Technologies. Over to you, Ankit.
Thank you so much, Anvit, and thank you, Niranjan, Mayuk, and Giri. Well, for those of you who have been seeing me or just joined in and don't know who I am, I'm Ankit Mathur and I'm Chief Architect. I work for the storage team at Huawei. And today I will be throwing in a question and let's see the responses. Well, the question is like, can storage live up to the demands of the new era data analytics and intelligence? And for the panel, let me introduce first is Niranjan. So he is someone who has worked on storage for over 22, 23 years, Niranjan. And he has worked on the traditional storage evolving all the way to new technology. And let's hear from him later as what the new technologies are bringing to the whole analytics and storage and the setup. And also is Mayuk. He has been a distinguished technologist at HPE. He has designed storage and now he uses storage and he develops AI and ML for the storage to make it much better, much lesser influence of people not needing admins to work on it. And we have Giri, who is the CTO of LendingCard, but in a past era or past life, he has also designed storage devices. He has then built big analytics systems on top of them, and now he is actually running a business on top of it, right, Giri? All right, so let me put in a few questions so that we can hear from the experts. So Niranjan, you have been in the storage industry for fairly long. So how have the storage devices evolved from first when you started touching them, making them, and now today?
Hey, Ankit, thank you so much for having me here. I really appreciate. Yes, over the last 22, 23 years, I have seen storage evolve across multiple dimensions. It could be capacity, it could be storage media, it could be latencies, it could be the architectures that involve storage. For example, back in those old days, we used to have hard disk drives with few gigabytes of capacity. Soon it became larger and larger capacities with solid state devices coming in and recently 3D crosspoint like devices coming in. The bandwidth is growing at such a rapid space, rapid rate at this point that it basically goes beyond the rate at which the bandwidth of the buses that read data from these devices, for example, PCI buses and things like that, that is growing, or the computational power of CPU is growing. So essentially what is happening is that the capacity of the device is growing at an enormous rate compared to these other subsystems. And that is where some of these other newer technologies coming like computational storage, where we want to, instead of copying all the data from these storage devices into the compute memory, can we process those in the storage devices themselves. From latency perspective, hard disk drives used to do a few milliseconds back when I started. Now we have capacity SSDs, which do 100 microsecond latencies. Then we have performance SSDs like Optane SSDs and things like that. They do tens of microseconds. And then recently we have been having persistent memories that do about 300 nanosecond latencies. with DRAM doing about 100 nanosecond and CPU register doing a few nanoseconds. So that's a complete storage landscape. And back when we started, we used to have direct attached devices. Devices were directly connected to the computer, which was running the application. But soon the sharing of the data was required. That's when the SAN, the storage area network, came up. Then as the sharing, file-based sharing became more prominent, network attached storage came up. And then different architectures came up like hyperconverged environments or disaggregated storage and things like that. So we can see that the storage landscape have changed substantially from where we were to now. And for that matter, even data formats have undergone a lot of changes, like from structured to semi-structured to files and objects to streams and events and things like that. So,
I myself can recall, like when we were designing the storage, we would be dealing with the fact, like, can we put in more spindles? Because we have so much of spare power, we need to have the bandwidth coming in, put in more spindles. And today we talk about, oh, well, we cannot add more SSDs because the CPUs are already bottleneck dealing with the data. So, well, with holding that thought, Mike, so you have been designing storage earlier, and now you are using it to make it just a more generic device because the machine learning will take care of rest of managing. So do you see that the storage is going to become like a cookie cutter generic hardware and rest of it will be just fine-tuned by AI, or do you see some specialization or response coming in from the storage side as well, some innovation there?
Ankit, I think there's a lot of innovation that is going to happen in the area of storage management, continue to happen on the area of storage management, especially driven by AI and machine learning. So that's one of the field that I specialize in today. So if you see today, like you said, I mean, it's kind of perceived that in the world of analytics and big data analytics and machine learning and stuff, storage is only a device to hold the data, right? But that's not true. If you see the boundaries of machine learning that we're pushing now, right? It's the model training, most of the model training that happens in the research and academia, they tend to run for weeks together, right? So at that, when you're training on such high volume data, it is very important to ensure that your storage is able to keep up with the performance of the GPUs that you're running on the devices, right? Because you have several GPUs and you need to be able to feed the GPUs all the data they read from the storage, and you cannot get bottlenecked on the bandwidth that the storage is able to provide, right? So that's very, very important. And so innovation will continue to happen in the area of storage management, how efficient storage can become over time in order to be able to keep up with the pace at which the analytics and machine learning is going, right? And I see that, you know, when you provision a storage, right, the responsibility of all the automation and on all the engineering that we put in or in terms of automated management of storage has to ensure that it continues to perform at the same level when it was originally, when we originally created it, right? Because you know, you may not, you may think that, okay, it's once I provisioned it is going to perform at the same level all the time, which is not true, because you know there will be like
it may degrade because of multiple reasons or because of other participants coming in.
Correct.
So Giridhar, coming to you, let me repeat the words of Clive Humby. So data is the new oil. So with that, how do you see, like, this lending business has been there for ages? I think it has been around for thousands of years, I guess. People would have leased out their land and got money, but now you are doing it with data. So how has data analytics changed the way the business is carried out?
So Ankit, traditionally the lending business has been a very judgmental process, right? I mean, you would have to walk up to a bank branch, you'd have to dress up nicely. The branch manager would actually look at you and then sort of go over a few parameters, talk to you, and then decide whether you're credit worthy or not, right? It's a very judgmental process. So data analytics has removed that. And that is one. And it has gotten a lot of side effects, right? You know, if you look at a traditional lender and look at the pool of people from a gender diversity point of view that they lend to, you know, you'll see a lot of skews. But if it is an analytics driven approach, you won't see that skews.
right? So a lot of biases that are there out there, just sort of vanish. The other thing is that it has made the entire process really, really fast as well, right? I mean, traditionally it would take up to a month or more to get credit, even, for a secured credit. I mean, let alone the kind of space that lending card operates in, which is unsecured credit. And the turnaround time for that, can be anywhere between a few minutes, as long as you are able to provide, some amount of information that will help us determine creditworthiness. And the ecosystem around this is also changing. I mean, recently, for example, RBI announced account aggregator, wherein your banking information with your consent can be made available to a third party via an intermediary who manages the consent. That has made things even more accurate and faster. So overall, I think, I would say that data analytics, the ability to use all of this in a meaningful way has substantially improved the lender's life, the people who are taking credit, their life as well.
I'm seeing it going in a way where probably before I get a feel like I need money, probably some organization like lending card might know, wait, by the way, you need money, don't you? And here is the money already ready. So that aside, so let me throw in a common question to you all. So in the analytics world, do we treat all the data same, or what's the expectation of the storage? Like, do you put in like this was old data, this is new data, or this is relevant data, not relevant, and so on and so forth? Probably you can take it, Giri, since you are someone who designs the app on top of it.
Right. So, Ankit, I think the identification of what data is important, right? And to a certain extent, with analytics, machine learning, even that is a machine learning problem, right? What are the features that are relevant? Right, and hence, but it's a discovery process, right? First you have a bunch of things in front of you. You definitely need a domain expert to sort of figure out, right, saying that here is what looks relevant to me, right? And then go iteratively and then figure out what is really important in terms of making, not just making sense, but in terms of optimizing the entire process, whatever business process that you are trying to optimize. So on storage specifically, right, the slightly higher order construct of being able to discover storage, right, or discover data, the higher order construct of understanding where is this data coming from, right, and who owns it. And the third point about the quality itself, is it complete, right, is it accurate, and will someone who's published this data take responsibility for it, right? So, and things like freshness, all those come into picture. So I think these slightly higher order constructs start becoming very, very important over and above the base storage layer and the speed with which you can access things.
Sure. So Mayuk, what's your take? Like, what can storage do specifically to make all of this process smoother or easier? I think Mayuk, your audio is.
Yeah. So like you mentioned before, like the data acquisition is a very expensive thing in the world of machine learning, right? So that's one of the reasons why none of us ever delete anything, right? So which means that you continue to accumulate data over and over a period of time. You don't, at this, when acquiring data, you don't know that whether you'll be needing it at what point in time in the life cycle of your, building the models and stuff like that. So you continue to keep all of that. Now, what I've seen organizations are challenged with is that there are different categories of users who look at the data, right? So there are data scientists who are exploring the data over and over again. They're looking at the same set of data. If your team has 100 data scientists, they're accessing the same data, probably running into several hundred gigabytes every single day. They're scanning the data over and over again. They're exploring that, right? So you will have to provide, mechanisms for them to kind of explore the data in a much more variable fashion. So we call it democratization of the data, right? Different users in the organization are looking at the same data, but they are looking at a different projection of the data, different dimension of the data, right? But you still, would you mean that, does it mean that you're going to make clones and copies of it and restructure them? That's going to be super expensive for any organization to do, right? So you will still have to provide intelligence, some sort of an abstraction on top of that, so that it still caters to the different users. But the data is not stored multiple different ways, right? So I think as an organization, as the storage vendors will have to evolve in order to be able to provide those sort of tooling mechanisms on top of the storage solutions that they provide. Plus, there are a lot of other things in terms of machine learning itself. When you're doing the deep learning itself, right? When you're accessing the data over and over again, right? So you are doing shuffling of the data. That's one of the natural process of machine learning. You to shuffle the data. So you're not reading them sequentially. You're just randomly accessing the disk, right? So does it go to an object store? Does it go to primary storage with microsecond latency, right? So all those decisions should be abstracted away from the end business user who just wants to train a model. They do not want to be bogged down by all these complexities. Should I have an Intel Optane drive sitting somewhere in there so that I can cache all my data there? I mean, all these complexities have to be taken away by the vendors who are providing these sort of tooling and mechanisms. So I think we have a very, very big role to play in terms of how to make the whole process of data discovery easy and data analytics easy for organizations.
So Niranjan, how are you getting the storage ready to respond to some of these asks in an abstract way, or like putting in technologies to make some data available faster, slower, cheaper?
Absolutely. I mean, in the end, I think that some of these requirements have to be driven by the application, the SLAs that the application defines, and correspondingly, storage has to gear up to support those SLAs. If some real-time analysis has to be done, then storage must be able to provide the access times that that data need to be accessed at, or if there is some more accuracy required, some specific formats of data are there, then storage should gear itself to provide that particular data in a way that is that meets the SLA for the application. So yes, storage. There are different types of storage, and it also depends on the volume of data. It also depends on the format of data. But at the end, we have to ensure that the SLAs are met, whether it's storage tiering, whether it's the quality of service we are talking about, or because of course there are trade-offs related to the cost, because the volume of data we are talking about is very high as well. So I would say it should be driven by application. Applications should be able to specify, and as Mayuk said, storage should be able to auto-configure itself so that the application SLAs are met.
Sure. So basically is a segue into another question that I have, is that how do actually data scientists view the storage? Mayuk, you just touched upon that fact, like you don't want to look at whether there is a daemon setting somewhere, or there is a specific type of processor or GPU available somewhere. Data scientists are probably mathematicians, and they are playing with numbers, and to have them also look at certain other aspects. So in a day-to-day life, how do data scientists want to view a storage system? What do they expect of a storage system to give them? Giri or Mayuk?
Mayuk, do you want to take this?
Yep. So data scientists probably do not have, that much of an insight into what type of storage should I choose in order so that my whatever activity I'm doing is more optimized and efficient. So think of the scenario, right? You are deploying a deep learning notebook, for example, which is going to configure everything. For example, it's going to install the CUDA drivers, and it's going to install the software stack, Jupyter, Python, and everything else, right? And then it's going to create a notebook environment and give you an URL. That's what a data scientist in today's cloud operating model. That's an experience that any of the data scientists in an organization want, right? Now, at the point when it comes to selecting the storage device, you have an option to select whether I want an HDD or an SSD, right? So far, if you see, the options are only those. You don't really have options of Lustre file system, parallel file system. All those things are not even made available because they probably will not be able to associate what these even mean, right? Right. So there, even that choice itself, I would say that people would spend less than 5 to 10 seconds in that, probably saying, okay, if I have more money, I'll go with SSD. If I am kind of strict on the budget, I'll go with HDD, because the cost will be reflecting right somewhere on the right hand side. What's the effect of my selection? And that's it. That will be pretty much done about in the workflow, right? But that's something that has to change, because in the end, how did this decision of selecting a class of storage during the provisioning of that environment, how did that eventually affect the whole machine learning experience or data exploration experience, right? Is something that I wouldn't expect a data scientist to be able to judge or comprehend, right? It is for the storage administrator or the system administrator of your organization who would know whether this was an optimal choice, because there were a set of hardware components in the stack that were in play. There was a GPU, there was a fabric, there was a storage, and whether there were bottlenecks in any of those components. And if there were bottlenecks, then they have to be rectified automatically, preferably by relocating this workload from here to somewhere else, so that the bottleneck is kind of streamlined, right? So you couldn't have seen that the GPU has 14 gigs of memory, and your data set that you're attempting to load would potentially fill that hole up, right? But your disk bandwidth or the fabric or the ports on the storage controller were blocked at, say, 5 gigs, right? And that's going to be evident. That's going to be evident for a storage administrator. But you want somebody to go drill down and look at that? Wouldn't, right? It should automatically be taken care of, so that the end users can kind of get the experience that they want, right?
Yeah, I agree with Mayuk, but I think I'll flip this question a little differently, right, Ankit? In the sense that, what does a data scientist do that influences this choice? That is more important, right? And I think there, the most value add would come from being able to characterize the workload accurately, right? And laying out the use case really well. And once that is in place, I think data scientist is sort of abstracted out from what goes underneath, and there are multiple layers, right? I mean, and probably storage comes down and the fabric comes further down towards the end. And hence I think the top level aspect, saying that, look, I want to use this to do sciences, right? And I want to use this to do analytics. One needs to probably go beyond that and characterize the workload, saying that it is more streaming in nature, and I'm going to look at it in maybe these intervals, or I'm going to explore this data, right? I mean, I'm going to use it for exploratory analytics, or saying that I would like to probably generate a month-end report. It's okay if it is stale, right? It's okay if I have to run something, go for a coffee and come back. Or saying that, no, it's important that when I eventually do this, it should respond within a few milliseconds. I think characterizing it that way, right? Explaining
And I'm
it.
sure, like how it is in the learning phase when you are developing your algos or training a model, to when you actually deploy, also these things might be different.
Absolutely, yes. And I think the better you characterize that, the more accurate it would be for a system builder to recommend something.
So Niranjan, do you see some cues or something that can be passed across these hard boundaries, or it's an iron curtain?
Yeah, I feel that there has to be a way to abstract. I would echo with Giridhar here. There has to be a way to abstract things out, because a single person cannot take a view of end-to-end or take an end-to-end view, right? So there has to be an abstraction, and storage experts have to come in to configure the storage accordingly, and that's where the storage systems have to be configurable to meet the needs of SLAs. So that abstraction, I don't know whether it's a data scientist who does the abstraction, or there is some another person who understands the requirement from data scientists and does that abstraction for the storage storage layer, right? But I can see that data scientists may not understand storage that well, and storage people may not understand the view of data scientists. So there has to be a translation that must happen.
So you are hinting at you need a marriage maker to really get the understanding of the app side or data scientist side, and have an understanding of the storage side, and probably come up with a proposal like, is this good enough for you? Is this something you can provide, right?
Absolutely. Someone who describes the workload in a way that storage can understand.
Sure. All right. So around like close to 100 years back, there was this guy in Germany, Heisenberg. He said like, you cannot measure something very accurately and also measure its momentum, like its position and momentum accurately. So I'm thinking of when we are processing data, it's more like, can I have an accuracy of what I'm inferring and also have the speed, do it quickly enough? So how do you go about setting up a system that performs the job right? If I go for too much of accuracy, I think the inference may be irrelevant at that point in time, I guess. Giri, you want to take that?
Sure. So I think, Heisenberg said that you can't do both at the same time, 100%. So it naturally is a trade-off, right, Ankit? The ability to sort of measure, right, is important, and you have to again, work with a margin of error, right, or in certain cases a risk budget. And the amount of design that you put into the system and the amount of testing that you do will really be proportional to that assessment. If you were to take the lending space, for example, anyone can lend, right? But the challenge is really in collecting money. So, and then, you give a 3-year loan, you really don't know whether you've been able to collect well till 3 years later. So there's a huge time gap there as well. So it's a little more nuanced, right? So let us take another example. If you are creating maybe a machine learning model to identify maybe faulty phones on an assembly line. A trivial model which says this phone is good would probably give you 99.9% accuracy, but that is not a good enough model. Right. So I think, you'll have to then look at, okay, what am I really looking at in terms of accuracy, right? So your target set really is not how many phones are good, but within the set that is bad, how much am I able to predict? And hence the speed with which you are able to predict, needs to be taking that into account, saying that, okay, this is my target data set and here is what I want to infer in. And at some point in time, here is when I'll have the performance data to really measure. So I think these are important. Probably a long-winded answer to what you asked, but yeah.
Yeah, so let me turn the question over to Mayuk. So he actually runs the model not only probably in his lab, but he claims that he runs the models on the shipping systems. So on the customer side, maybe not enough power, and then probably still make it useful enough to respond. So Mayuk, how do you go about doing that?
Yes, so the at times you have to make trade-offs, like Giri was alluding to earlier, right? You have to decide whether I want to go for accuracy or, in machine learning parlance we call it recall. So are you able to catch all the problems? If there are 20 problems, are you able to catch 18 of them, 19 of them? So that's one measure. Or the other side is, if you are able to predict something as a problem, how sure you are that it is really a problem, right? So these we typically have to balance between these two, right? So in our case, when we are running them on the device, so first of all, our footprint has to be very, very small because we are running on the storage device. So we have a very little CPU and memory footprint available for running those models. And thankfully, the data that we operate on is metric data. So if you realize that most of the cases when you need GPUs and all, right, where your data is probably you're doing audio processing, speech processing, or you're doing image processing, video analytics and stuff like that, where your data set is really, really large. So when reading in a video itself is like 1024 cross 1068 pixels, right? It's large amount of data, and you have to feed in a sequence, for 40 frames per second or 80 frames per second or whatever. You have to feed that in. That becomes very, very large. So you need to have a very, very specialized device deployed. But in our case, the storage, the sensor data are very, very small. For example, they are all metric data. They're text, numbers, floating point numbers and all, and they're not that big. So fortunately for us, even though we are learning deep learning models, we didn't really have to use GPUs, right? We could still run it on the CPUs with a very, very limited footprint. And because our problem has been redefined to what we want to predict and how accurately we want to predict that, and how much history we want to look at, right? So on the device, we look at last few hours worth of data, and based on that, we analyze and we predict what is going to be the load on the system for the next few minutes, right? So that's our horizon of prediction, and that's our analysis window. So we can keep flexing this analysis window depending upon how much of headroom is available to us. Right, and thankfully the data is metric, like I said, so it all works out fine for us.
Sure. So Niranjan, like we have talked about that accuracy and speed, and probably it will infer or refer to performance capacity and other things. What else do you think is important when there is analytics data? What other parameters are of relevance besides latency, bandwidth, and capacity kind of parameters?
Yeah, so in terms of, I always feel that the storage follows the requirements, right? That the application or the workload has, right? So if from the perspective of speed, if you want to do some fraud detection, it has to happen real time. Then the storage must meet those requirements, and maybe we could use in-memory database or whatever it is, right, to be able to meet those SLAs that are required for that application. So and same for accuracy, if we have to do a holistic analysis, batch processing kind of thing, then we need to have storage which are capable of meeting those requirements. Besides, I think scale, capacity, performance, latencies that you mentioned for analytics processing, I think there are a few other things I think that could be interesting from analytics perspective. For example, the data comes from variety of data sources, so and they may have different privilege levels. So the privilege, right, which data should be visible to whom, and which data, how it should be analyzed, and how should results be shown to whom, I mean, who should be able to see those results. So the privilege levels themselves, and that also has some security and compliance angle to it. Those I believe could be very important, and storage system or the data formats that we have should be capable of handling those things.
So the point that you brought about, Niranjan, I think, Giri, you might be facing it day in and day out. You're dealing with financial data of people or organizations. And so what do you expect of the storage to do? Maybe you can start off with what are your needs, and then what do you expect the storage to be able to do, and what you can just let the other parts of the system deal with.
Right. See, I think fast, cheap, and reliable, right? I mean, these are the three. If it comes to that, which of these can we give? That is what we would expect from a storage system. But one important aspect, right, is really, especially in the domain, in the financial domain, right, is that there is a lot of regulatory requirements. Right, and those regulatory requirements impose a lot of constraints on how we work with data, and the ability of a system to help us deal with that is very, very important. You would have heard this recently, right? It was in the news that HDFC Bank was prevented by RBI from issuing newer credit cards for quite some time, right? Because they did not have disaster recovery in order. Similarly, there is PDP bill that is going to come. The government of India is at some point will pass that, right? So how do we deal with data in that context? EU GDPR is already there. So I think some of these criterion percolate into what the systems themselves can do or not do, and hence the choice of what we probably deploy and use also depends on that. The other, and it depends, right? I mean, financial sector is huge. I mean, I touched upon probably lending a little bit, but if you look at, say, trading, then the SLA that you can provide to your end users, right? At what rate can you show them the data, and then if you're probably doing some inferencing on it, how much delay do you introduce? Those start coming into picture as well. So I think these are some of the aspects, Ankit.
Sure. So are there some of these models that you see that can be passed on to the storage layer? Because
Absolutely.
yeah.
Absolutely, right. I mean, there's a lot of nervousness around customers' data going into a third-party environment, right? Lending Card is not just a lending platform; it's also a technology platform where other lenders can onboard and lend. So they would ideally not want their customers' data to probably come into Lending Card. So we work on certain techniques wherein we probably can push the compute to the storage and make sure that that is running where the storage is, and make sure that we can do inferencing. Of course, that will be difficult for training, but we can certainly do inferencing like that. So that aspect of the system, sure, yes.
So how much of some of these processing we can do it in a way that can be run in a distributed fashion? Someone may not be wanting to share, or there might be other reasons that it adds up latency, or maybe you have enough compute on the edge device. So
I'm getting Ankit to be quite choppy. Is it just me?
as in, how important is it?
It's quite choppy. We lost you there for a second. Okay.
Just hold on a moment. I think bad network.
Yeah, Ankit, there seemed to be some issue on the network. I think he just
I
got
just
dropped out.
stopped the video. Is it better now?
Yeah, I think it is. I think
Yeah.
maybe we continue like this for a while. If the network's improved, maybe we can turn on the video towards the end.
All right. So
sorry, Ankit, but we seem to not be getting any audio again from your end.
let me see if I can do something else. Apologies for that. Is the audio fine now?
It seems fine now. Ankit, go ahead.
Okay, great. So yeah, what I was alluding to is that we may not be able to share the data across for various reasons, be it some compliance reasons, or it could be like there is too much data to just move to a central place or something on those lines. So how relevant or important is edge computing itself in the analytics space?
So we'd like to answer the edge part a little later, but I would like to talk about an innovation in that space, obviously, where there are federated machine learning that is happening today, which is a real thing. Look up swarm learning also, which is a very real thing that's happening today in the industry, especially in academics and other areas, where you can train a model across different data sets which are residing in different data centers which are not co-located. The data is not sitting in the same place, right? But the model is still able to federate and learn, and that is very common in medical, in the field of medical application of analytics to the medical science, where the hospitals and university hospitals are collaborating in such a fashion where using swarm learning, the machines or models are being trained where the data doesn't have to leave the boundaries of the data center of the hospital or the university, but still the model is able to coordinate and update itself. Like what you pass around is just the weights or the gradients is what we call, or the weights that's basically passed around. The data is not passed or extracted or pushed over from those across those boundaries. So that's a very, very real thing now. Now, coming to the edge story, the edge has been preferred. Edge computing has been preferred. Privacy definitely is one big thing why it is preferred. More than privacy, I would say that the reason why edge is preferred is because some of the analytics are time sensitive, plus some of them have to happen on the edge. You do not really have to pull or haul all the data all the way over from your edge centers to a cloud, because that's going to be expensive, right? That's expensive. So you could have things in some countries. There are some sort of analytics that happens on with instruments that are kept next to for example your homes or your TV sets, where they would observe what is the activity that is going on. For example, if somebody is watching an advertisement or not, and those sort of analytics have to happen on the edge. You cannot probably hold all the data back into the cloud to do analytics and send a response back stating that, oh, this event has occurred. So I think privacy is important, but one of the main criteria for doing edge analytics is the cost perspective, right? Cost and the time sensitiveness of the use cases themselves.
So, Giridhar, you want to add anything on top of that?
Yeah, I think from simply purely from an edge point of view, Ankit, very, very relevant, right? And people are most comfortable.
Hello, sir. Not getting invite, sir. I
Hello.
think noise disturbance is there.
Hello.
We can hear you, Giridhar.
All right, there was someone else speaking in the middle. Yeah, sorry. So from an edge perspective, Ankit, people are most comfortable with their data not moving out of their control, right? And in a lot of cases, regulation also imposes that, particularly in the financial sector. And one having to sort of adhere to those regulations needs to say that, okay, I have a system in place which ensures that because this is physically not moving out, right, there is no breach in privacy or the regulation that I am adhering to. In some sense, it's like saying that there are two models, right? I mean, one is that you send the data wherever you want, and then you prove that it is secure, and there are probably no leaks and things like that. In the other model, you say that, look, the data is going nowhere and hence there is no problem at all. I think that's one area where the edge really helps. The other area is really localization, right? And there is more and more personalization happening. And as a part of that personalization, if a model is being built exclusively for me, or the cohort that is me, then that sort of again it sort of farms out. It's probably multi-model, or you could then say that this is a distributed thing, or even some of it happening online in terms of training at the edge as well. So I think these are some aspects.
So, Niranjan, you deal with some newer technology areas, and so if you can't share the data, any technologies that someone can still provide a processing and provide analysis on the data. So, like people talk about homomorphic encryptions as a way of being able to still process. What else do you see, or how much of it is real? Is it homomorphic is just like a pipe dream, or is something that works for only few functions specifically, like one encryption, few things you can do, but then you can't do other things? Or is it something that can be generally applied and made useful?
Well, not so much specifically about homomorphic encryption and things
No,
like that, but
that's just like one thing. How else can
yeah.
Someone provide a service and still be relevant and useful?
Yeah, some of the newer technologies I can talk about that may be relevant here. We talked about edge computing, where we want to. There may be several reasons why edge computing is required. Data sources themselves may be distributed. There could be security compliance issues, the volume of data. So I think computational storage is one important area that could help analytics save power, because there is a lot of power consumed in fetching data from storage devices into the compute. If we can push the compute itself onto these storage devices, that could be amazing. And these days, there are fairly generic ways of deploying compute functions in these computational storage devices, right? Of course, the speed of processing themselves is very high in computation in these devices, because the bandwidth that exists within these devices is far higher than that is available outside to bring that data into the compute. And of course, it frees up the CPU cycle for doing other things. So I feel definitely computational storage is some area where which can help analytics. And of course, other area, the persistent memories and things like that, especially in memory databases, right? It can support larger working sets, frequent and quick checkpoint creation, for example, quickly starting from checkpoints. So some of these newer storage technologies can definitely benefit analytics depending on the use case.
Sure. So before Giri, I asked you for your comment, just a reminder to all of the audience that if you have any questions that you want to direct to any one or more of us, please use the chat box in the WebEx window, and we'll be glad to take those questions. So over to you, Giri. What's your take?
Ankit, if you could repeat that for me, I just lost you there for a moment.
Yes. So the question was, you may want to do some processing. How or what kind of newer technologies, both from a hardware, software, algorithms point of view, are there in place that could help where you could still provide the processing of such data?
So I think if you look back at how compute has been happening, Ankit, there are certain primitives, right? And whatever you build is built on top of that primitives. And we look at optimizing that further and further. So you have general purpose CPUs. Now, when you look at GPUs, like, in general purpose CPUs, you had a certain instruction set. With GPUs, you have done really well with fuse, multiply, add. And so that sort of, in some sense, gets going, right? And if you look at, say, something like data protection, Reed-Solomon codes, probably primitives for that, right, within the hardware itself are something that people are building in. So, SmartNICs are doing that. There are data processing units which are even looking at slightly higher order functions, like, if I'm wanting to search in a string, right, and do pattern matching. So all these, right, sort of contribute to the betterment in some sense of the analytics workload, right? The ability to maybe program some of this directly, so that while data is in flight, you get these to work. The second thing is, again, how do we provide guarantees of privacy? So if I am operating on a piece of data, you alluded to homomorphic encryption, right? If I could, rather than saying that I have to have a huge amount of software in a virtual machine or a container, I have very specific validated and verified code and certified code that is being pushed to maybe a hardware enclave, and then I'm running it, right? And the ability to do that as a higher order primitive wherein there is a part of my analytics which really needs that functionality, right? So all these bits, all these hardware innovations sort of help towards that end goal, Ankit.
Sure. So, well, we talked about the new technologies briefly. There is a lot of talk about the computational storage, and earlier in the day, there was a talk from Jim Handy as well on the computational storage. And there we had a thought like computational storage is also basically a way for storage vendors to play a bigger role in the entire end-to-end vertical, because you may have a lot of compute takes away bulk of what needs to be done in the vertical, and storage remains a generic thing. So what's your take, Niranjan, on the computational storage? Like, is it something that actually makes storage a more useful thing, or is it a way for storage vendors to say, well, I will do some of the compute and therefore earn more money?
Well, as I mentioned, there are some physical limitations, like the volume of data is so huge, right? Bringing that volume of data onto the compute and processing it is just not practical. Whereas the bandwidth available within the devices themselves is pretty high, which means that if we can push compute there, it makes a lot of sense, and just bring the summary of data out or something like that. So the fact that it is being standardized, for example, SNEI is trying to standardize the computational storage APIs. I have also heard about the Nvme protocol itself being extended to support computational storage, some way of handling them. These standardized ways of doing things will help increase the adoption of them, and it may be easily possible to adopt them in a way that is not vendor specific. The heterogeneity will be brought in there. So I feel some of these advancements will help make computational storage being useful for the applications.
Okay, let me switch gears and try to look at some questions from the chat as well, what our audience wants us to tell about. And I think it seems to be directed towards you, Mayuk, but then others can also pitch in. So it's more like, I love your first device, but then I hate your 100th device because of the complexities that come in managing so many of them. So are there any learning workloads? So this is from Rohit. Are there any learning workloads used by scientists so that they can automatically apply the learning to configure the storage?
So on the interesting point, awareness of the workload. So we have heard a lot about application-aware storage, right? Now, when we talk about application-aware storage, those applications are traditional applications, SQL, Oracle, virtual desktop, virtual servers, and all, right? And there has been a lot of work that has happened on that area. But e-storage now have what is the work that is happening in the area of being aware of the analytic workloads, right? It's not as popular as being application aware. Now, the patterns of Oracle, SQL, everything is very well known, right? Because storage vendors have been designed.
And also the software, the projects that do these analytics are so diverse. Like maybe just under the Apache Foundation, you can find so many different implementations.
Right.
So awareness would have a whole different meaning. Right?
Correct. So
yeah, go ahead, Mayur.
Yeah, so which also brings up a very interesting point that could you have a localized intelligence where you learn over a period of time what are the typical type of analytic workloads that gets deployed for this tenant or for this customer. So you have a customer who has several employees who are data scientists who are exploring data, training models and stuff like that. And could you learn could your storage device learn over a period of time what are the typical workload patterns, and then figure out, okay, what's the sweet spot for an optimization, right? And then automatically understand, okay, these are the different groups of workloads that typically that I see in the area of analytics, for example. And these are the broad categories, and I will have to figure out a way to optimize myself in order to be able to do that. So, and today with self-driving storage, which is a thing now, which is a reality, by the way, storage can actually optimize itself for those workloads through some very minimal hints that somebody who's deploying the workload can provide. For example, saying that I'm going to do a computer vision. I'm going to be working on computer vision, like Giri was alluding to earlier. For example, when we are data scientists deploying a workload, you can say, am I going to just explore, or am I going to run a computer vision workload? And when you're going to say run a computer vision workload, you can ask, are you going to use a CFAR data set, or are you going to use ImageNet, right? So just asking a few questions, you already understand what is the dimension of the image, how large is the data set that you're thinking. And machine learning means you're going to be pretty much shuffling, randomly accessing the data. You know what your batch size is typically going to be, 64, 128 or whatever, right? So you can glean a lot. And I think it is a lot less complex than a SQL and an Oracle. Because believe me, we have explored a lot on detecting workload patterns of SQLs and Oracles, and they have huge variations depending upon what exactly you're doing on SQL, right? You're running month-end reports or whatever, right? Or what type of queries you're running. But here, I think if you can glean the data set well, the patterns are going to be very easy to figure out, because either you'll be using PyTorch or using TensorFlow, right? And those source code is available. You can go and look and see what they are doing and how they are accessing your storage. Right? So I think that there's a huge potential in that area in order to be able to automatically configure storage workloads.
Sure. Okay, so well, let me take up the next of the question. Maybe Giri, you can help with this one. So how modular are all of these analytics workflows? Can I actually just swap in and swap out, or certain different modules like different data formats, different frameworks, analytic engines, and then the source itself that's feeding in the data? Because this might change from even for a single workload. When you are learning it, you're designing it in your labs, and then finally you're deploying it.
Correct. So, Ankit, there is this very nice paper from Google called The Hidden Debt, Technical Debt in Machine Learning, right? And it talks about what are the various things that that one would need in terms of a support system to be able to actually train and put machine learning models into production. And it hypothesizes that about 8% of the work is a sciences work. The rest of the 92%, right, more than 90% of the work is actually doing things that you just spoke about, right? Trying to pick up data from multiple places, cleaning it up, making sure that what has been tested and trained goes into production. It is repeatable. So there are a lot of challenges there, right? And it is and it's a fragmented ecosystem. The models themselves, though, right, are reasonably well pluggable, and in fact, that is one of the reasons why this works really well, right? That you pick up a model that is there somewhere, and you use transfer learning, and then you use it within your own context and with your own data. So the model themselves, Ankit, to be honest, they tend to work, right? But what is more challenging is the things that surround it. Is your data clean? Is your test on the data repeatable? Sometimes if you're looking at time series data, right? I mean, what you've tested today would be different from a time point of view when you test it tomorrow. And hence, how do you design the experiment itself? Then how do you version it? So this entire thing sort of dovetails into ML ops, right? Or machine learning development lifecycle.
Sure. All right. So that brings us actually to the top of the hour. And we had some really nice insights right from the application side, right from what's new, what's coming in from storage and compute side. So any last set of thoughts that any of you want to express? Like, are we really prepared for the future? One quick liner from each one of you, if at all. Niranjan? Sorry, you're on mute, Niranjan.
Sorry about that. Yeah. So one quick liner would be the storage hardware itself has geared itself. to meet the requirements, right? So it's all about how it can configure itself according to the SLAs of the workload that are running, right? And the more it can do that, the more it's going to be able to meet these analytics workload. But from the technology perspective itself, it is there. The challenge is how does it auto configure itself, or how does it configure itself? How do we specify SLAs and things like that, and whether
Sure.
the system can configure itself. Thanks.
Sure. Mayuk?
Yeah, so I would say that definitely yes, we are prepared for the challenge, and as you can see that storage is no longer seen as a device which is just going to store your data. It is an integral part of your entire end-to-end use case. It is part of your workflow, right? And so we are basically managing the data. We're no longer managing storage. We're managing data, and data is an integral part of your use case, and that's how we envision that storage is changing now.
And Giri?
I mean, I would slightly differ with Mayuk here. See, the bottom of the stack has evolved rapidly, right? And it has seen substantial, significant innovations in the past few years. Ditto with the top of the stack, right? The middle layers are lagging, right? And I think that is what is probably holding us back, right? I mean, in terms of the software layers that we have and the frameworks that we have to be able to make use of the underlying hardware really well and exposing it in a way which is usable by the applications. I think that is where I would say there are challenges, and I'm looking forward to more innovation in that area.
Sure. So I think from the audience, there might be few people who have listened to Giri and are not really holding themselves back with what Mayuk said. Like, we are all ready. Probably they will innovate and give new ideas. So we agree to disagree. And on that note, over to you, Anvit. Thanks so much, Niranjan, Giri, and Mayuk for joining us today.
Thanks for having us.
Thanks for having us.
Thank you so much, Mayuk Datta, Niranjan Pendarkar, Giridhar Yasa, and Ankit Mathur for that very invigorating panel discussion at the IEEE Data and Storage Summit. With that, we're going to move into a very, very quick break. As I was mentioning, Mayuk Datta, Niranjan Pendarkar, and Giridhar Yasa. Thank you so much once again, sir. Thank you for sparing the time and sharing your thoughts at IEEE Data and Storage Symposium. And thank you, Ankit, for moderating.
Thank you.
Well, with that, we're going to be going into a very quick break. We will be starting the next session sharp at 1 p.m. We are a little over in the panel, but 1 p.m. sharp, we have a session by Rakesh Dash, and that's going to be on AI, ML, and data. So do not miss this session. Grab yourself a meal, get yourself a lunch, get something to eat. Back at your desk, 1 p.m. sharp, we will be starting with the next session. Until then, this is me, Anvit, signing off for a few minutes.
Hello, we're IEEE, the world's largest professional organization striving to advance technology for humanity. And today, we want to tell you about our strategic plan for the future. But who is IEEE? We're a global community of more than 426,000 members in over 160 countries around the globe. We have 45 societies and technical councils and 10 geographic regions supporting our worldwide technology community. And each year, we publish over 160 publications and hold more than 1,600 conferences. Our digital library, IEEE Explore, houses nearly 4 million scholarly scientific documents. Working closely with industry, we have developed more than 1,600 internationally recognized standards and projects. In total, IEEE is one of the largest knowledge generators for technology professionals across governments, academia, and businesses. Our mission and vision for the future are simple yet profound. Our mission: we foster technological innovation and excellence for the benefit of humanity. Our vision: we will be essential to the global technical community and to technical professionals everywhere, and be universally recognized for the contributions of technology and of technical professionals in improving global conditions. To accomplish our mission and realize the IEEE vision, we focus our work around several core values: trust, growth and nurturing, global community building, partnership, service to humanity, and integrity in action. The 4 goals of our strategic plan are to expand and enable dynamic, nimble, flexible, diverse communities to help individuals from around the world to share, collaborate, network, debate, and engage with one another. Provide technically vital forums for the discussion, development, and dissemination of authoritative knowledge related to traditional technologies, while focusing more of our resources towards serving the professionals working on emerging and disruptive technologies. Lead humanitarian efforts around the world to use technology to solve the world's most challenging problems. Leverage IEEE's technology-related insight to provide governments, NGOs and other organizations, and the public with innovative, practical recommendations to address public policy issues. In order to support these goals, we are engaging in several key initiatives. Provide more opportunities, products, and services aimed at increasing our value to professionals working in the industry, particularly younger professionals and entrepreneurs. Ensure the vitality and relevance of our core activities in standards, conferences, education, and publications while providing increased value to our members. Develop programs in public service focused on knowledge and technology in our fields of interest related to public policy and humanitarian efforts. Evaluate and adapt organizational structures and processes to meet the demands of a changing environment while managing the financial and sustainable health of IEEE. And if you would like to download our complete strategic plan, you can find it at the IEEE website.
Well, we're back after a very, very short break indeed, because we have an action-packed lineup even after the break. We've got lots of sessions coming up now, but the first session after the break is by Rakesh Dash, and the session is going to be by Rakesh Dash, who's Master Architect Analytics and Big Data Platform for Storage at Hewlett Packard Enterprise. He'll be speaking on AI, ML, and data. Over to you, Rakesh, if you're ready.
Thank you, Anvit. Am I audible?
Yes, you are audible. We are unable to see your video, though. Oh, you're visible as well now. There you are.
Yeah. Okay. Let me share my screen.
Sure. And we can see your screen as well.
Perfect. Thank you. Bring on the slides. Is it in the
perfect?
Okay.
It's in presentation mode. It's all right. Thank you.
Okay. So I was just listening to the panel discussion, and it was quite amazing actually. And I would say that this presentation will also be in continuation to that that panel discussion. And I'll try to keep it focused on data, not get into AI/ML much. Hopefully that is fine. So I was just trying to find out what should be the name that I should give to the presentation, and thought I'll just keep it very generic, and then we'll explore what's there. So the agenda is very simple. So we'll get to a little bit detail into where are we in respect to AI today, right? AI ML. What is it that is happening today in the industry, right? And one of the biggest challenge in AI, which we'll see why, it's about data management. So we'll get into a little bit about that, and what is industry trying to do to kind of help in the AI journey. And data being one of the central theme of the symposium, and how storage can impact and all that. So we'll see some aspects of that. And I'll talk about the lakehouse architecture, which is kind of a new innovation that is happening around the data management. So we'll see a little bit of detail around that, right? So with that, let me get in. So we're talking about AI/ML so much. I would say that in last couple of years, it has become just too big. Now, is it just a hype? Is it real? I think this is a very nice survey done by PwC, and very impressive data set, about 1 million data points. And basically, this is the question posed to the participants where, are you realizing the benefit of AI? It's not like, are you developing something? Are you already realizing the benefit of your AI, right? And if you see, there is a tremendous amount of participants who shared that when they were asking about benefits of AI in different areas. There were 10 different areas they chose. Customer experience and improved decision making, cost saving, and all that. So these were the top 5 areas where customers are actually getting the benefit of AI today as we speak, right? This is on 2021 latest. So that means there are many areas where customers are already getting the benefit of AI, right? Does that mean AI is completely mature and it's able to do everything that is necessary? I think the previous panel discussion kind of brought very important points, right? There are a lot of challenges from the low level hardware to the top level algorithms, and in the middle level also, right? And here, the significance of AI, why it is going to only increase and will not decrease. This is a very nice data point by Gartner, which is telling that 65% of the decisions today that we make have already become more complex compared to what they were 2 years before, right? And it's only going to become more and more complex. And why is the complexity is increasing? Because the decisions are becoming more connected. That means a decision is actually impacting far more decisions than it was doing before. It has to become more contextual, geography specific, gender specific. It has to become far more contextual in where the decision is being taken, and it has to happen rapidly, extremely rapidly, because the rate at which things are changing, there is no time for like the previous, let's look at after 3 years how to repivot kind of. It's every quarter we may have to repivot, right? And with that kind of thing, what they have done is they have seen simple decisions, complex decisions, up to chaotic decisions, and how frequently we need to make the decisions, etc. They put a graph, and a lot of important areas they have tried to cover, starting from spam filter up to hiring decisions to kind of lending loans. So many of these things they have tried to put together and trying to see how can we make automatic decisions. Can we help, if we can't actually make the decision making automatic, at least can we augment the decision making? And can we actually support the decision? Can we give more data points which can be used for taking better decisions and faster decisions, right? And more contextual decisions. So the summary of this slide basically is that yes, decisions have become complex, and the only one who is trying to tackle all these challenges is going to be AI/ML, right? Now, this is the reality check, right? Where are we really? I mean, this graph, if you realize, this graph is actually also called a wisdom graph kind of, and the peak is actually called the stupidity peak, right? The peak of stupidity. So effectively, what it tells is what is really happening. This is actually a hype cycle for artificial intelligence that Gartner have created, where they're telling everything that we talk about AI. There is a point in this, right? So it is only when it is in the plateau of productivity, it is really productive and people are using it, right? I mean there is all the stack is in place and people know how to use it. They know what is the benefit, what is the disadvantage, what is the advantage, and they're able to take the maximum benefit out of it. Before that, this is the place where most hype is going to happen, right? That means AI, and everyone will talk about AI, but the meaning and the usefulness is not going to be as much, right? But if you see, there's a lot of these few points, right? Intelligent applications and deep learning, and many of these things are clearly telling that there is definitely that peak has already gone. Now we are trying to climb down, which is trying. So this elements are clearly telling that now reality is sinking in, right? That means things are becoming more real now, right? And by the time it reaches here, that's the time when we start to really become efficient in actually exercising that, right? And this is trying to highlight a few more points as well, right? So where are the industry focusing today? So while doing the journey from all this way, the current focus, right, for 2021, what is the focus? The focus is, one of the biggest focus is data, right? Getting the right data at the right time, at the right place, and be able to use it in the different algorithms, etc. That's a tremendous challenge, right? And then responsible AI, how to operationalize AI, and efficient use of data, model compute. These are other areas also which companies are focusing, but today for this particular session, we'll focus only on the data, right? And another very important trend that Gartner have kind of identified is the fact that two things happened, right? One, that COVID-19 happened and suddenly history doesn't mean much now, right? Because the trend that was captured for a long time, COVID came and just suddenly changed it, right? So that means machine learning, if it's going to depend on anything which is more than 2 years or 3 years, then suddenly it has a very, very different trend compared to, let's say, 5 years back when there was no such pandemic going on, right? So data itself got very, very skewed. The second thing that happened is the volume of data is growing so rapidly that taking it to a central location and be able to process is not only about the concern of data security, it is also not feasible and practical anymore, right? So now, instead of talking about big data, there is to talk about now small data and wide data, and Gartner is predicting that 70% of the applications will move to small data and wide data by 2025, which is like 2 years, 3 years, right? Which is very soon. We talked about big data for what, maybe about a decade or so, but now we're talking about small data and wide data so soon. So this is one reality that is going to set in very, very soon. Now, slightly changing the gears here, right? So now whenever we talk about data management, right? Now, the first thing that comes typically to mind is a database, right? That's the professional forever that we can think about. It was there. And I've just tried to put a simplified diagram for that. I have taken some reference from Postgres, but most databases follow these techniques only. Basically, there is a client typically trying to reach from JDBC, ODBC client and trying to run some queries, right? And a few things that happen here. So one, there is a file system. Without a file system, there is no persistence in place, right? So there is a file system, and the file system takes care of two types of data. One is the data itself, what customer is interested in, and the second one is called WAL, which is a write ahead log, right? Which effectively is a simplified way to tell that this is the guy who is really giving me the capability to have consistency, atomicity, or whatever acid on the data that we want to do, right? So all those acid property, this is the guy who really enables it. Now, the buffer part, anyway, we know buffer is the reason why things are going to happen faster and all that. So we're not going to dive much into that today. And then there is a query engine. So SQL has become de facto standard. Many these distributed databases try to come up with their own language, but eventually ended up supporting SQL as well, right? Because there is just enormous amount of investment over 2-3 decades, and people are just comfortable with expressing their data requirement as SQLs. So now, why am I saying about this, right? So the trend is very important of how this, I mean, when we want to deal with data, previously there was just one solution: get a database and it's going to do for you, right? Now, what happened is, with the volume of data increasing, they realized the databases are not able to scale, right? So companies like Facebook, what they have done is, okay, first you take a database and follow all your database principles and create normalized tables and absolutely perfect queries, right? When data volume increases, they first dump the normalization part of it. They just denormalize all the data. That means a lot of duplicate data, but good performing queries. But for Facebook, what they had to do is finally take the database out. They created a simple key value store just using the disk drive. That means nothing in the middle, right? So that is the kind of drastic step people had to take because databases were not enough. Another set of folks, what they did is they tried to dismantle the whole database itself and try to give all those functionality separately as a consumable piece. We'll try to see how the dismantling and assembly is currently happening in the industry today, right? So let's get first to the data files, right? This is where your real data is getting stored, right? Now, if you see, there are two basic formats or mechanisms with which data is currently stored, right? They're either row formatted or they're column formatted. Because we're talking in the context of analytics now, we'll be focusing more on columnar storage. And the reason for columnar storage is with the data denormalization, we now have a problem of huge number of columns, right? And a row, if I load, that means I am loading too much of unwanted data. And typically, analytics use case needs a very small amount of columns only, but most of the data in that column, right? So, and columnar stores also have done a lot of innovations around how, because the data is now duplicated, and typically a column now keeps a very similar type of data. They are able to, based on the data type and the data characteristic, they're able to apply very good compression and deduplication algorithms to actually reduce the amount of data to the point that the best known compression algorithms like bzip2, etc., are now falling short with what amount of capacity, the storage capacity that someone is going to take, right? Means if they're using a columnar storage. To give you an example, like let's say bzip2 is able to give you 90% compression. We have seen even better than 90% compression if we use files like Parquet, and that is still not considered the best in terms of compression, right? Parquet is one of the most popular formats, but it's not best in terms of compression. So there are many things that is happening around that. So that means one of the first things that happened is the file format itself. Now, previously the file format was only accessible through the SQL interface, right? Now what happens is you have directly accessible the file format itself. That means your file format is open sourced, right? And because files format is open source, a lot of innovation happened and some good candidates like Parquet came up, and a lot of useful tools which support Parquet effectively, right? That means it's not MySQL or Postgres deciding what my file structure should be. The structure now have become open source. Now we can build tools which support Parquet, right? And apart from getting the compression, etc., we are also getting a lot of good benefit around openness of it, and the lot of good products and tools and technologies that is coming on top of that, right? So that means if you have your data stored, like previously we were storing in, let's say, CSV files and JSON files, etc., you can open and read it. Now you can keep in Parquet, which is now suddenly have become storage optimized, big data compatible, right? And mentioned a few names around other technologies like ORC and some other formats are there, right? Some of the restrictions they put is like these files are typically read-only, right? Because analytics data typically doesn't change. It is not like transaction data, so it typically doesn't change. Because data is not changing, keeping a sorted data is very easy. So it is sorted, and because it is sorted, right, and read-only, we can now suddenly have a tremendous amount of things that we can do to optimize the performance of how we want to process the data. If I just cache a little bit of data in it, of the statistics of what our data is, then I will be able to very quickly and efficiently process the whole content, right? I don't have to actually go to the data to see. I only have a small amount of metadata kept in the cache to be able to kind of summarize the whole data, right? And be able to perform on that, either to include in my calculation or to exclude it, right? So those kind of filtering and push down operations can happen on that. Now, this is one thing which changed. So the underlying data format has now become open sourced, right? The second thing that is happening is because the data formats have become open source, the SQL engine also have become open source. So tools like Spark SQL and Presto and many more like Drill and all that, they have now started supporting not just Parquet, any file format that you give, any file which have a format, right? Like even CSV, JSON, and all of that also they support, but the standard one that they will all recommend is use Parquet, right? Or use ORC or maybe Evro. There are other formats as well. So, but the main point is now SQL engine is not a database game anymore, right? Because the file format has become standard, open source. Now the engines also have become kind of different. I mean, we can have different, I would say, different kind of problem domains they pick, right? So while like Spark SQL has picked the problem domain of a general SQL engine, Presto has taken up the problem domain of, like, let's say SQL is what I want to give, not the programmability that Spark can give, right? So different one have given different kind of different ways they have tried to use the data, whatever is already available, right? Now, this diagram is what I have put together is how Spark today does. And if you see this, this SQL engine have nothing, it doesn't take care of much about the data itself. The RDD is like a pointer, I would say, right? It's more like a representation of the data, right? Where the data is stored and how it is stored and all that, but it has no access of data till the final execution happens, right? So the whole thing is abstracted. That means the SQL engine itself is now completely abstracted out. So data is abstracted out. SQL engine has also proliferated, and now we have more choice in terms of SQL engine. So now we have a mix and match that we can create, right? Now this is a very this file, which typically people don't talk about much. It's considered as like a black box. We shouldn't know. Databases do some magic, and then finally we get transactionality, we get ACDET, all that. But the underlying technology is extremely simple, right? And this kind of gives a snapshot of what is the kind of data that is there, right? This log ID, which is constantly increasing, never going to get duplicated, right? Effectively giving some sense of order, right? It's based on time, concurrency, and all that. And then there is transaction. So that means each transaction have multiple steps, we know that. And then what is the actual operation itself? And just keep that in a file, which is like, it's going to be an append-only file, and sequentially, typically it will be read sequentially, right? Ordered by time. And this is one of the most efficient operations that anyone will want to do with a disk, right? And this is what is the foundation of the ACID property that we actually typically get from a database, right? And this is what is really enabling that. Now, what happened is, now even this, right? So now data is there, SQL engine is there, but what about transactionality? What about my ability to change it? Because I talked about read-only files, right? So what about my ability to change it? So now this also is something that people also extracted around and just made it to a separate consumable on its own, right? The technology itself, right? Now, what is the consequence of that? So this is a slight detour, but I would just try to highlight here WAL file or Kafka, right? So if we kind of dig deep into what Kafka is effectively a pub sub system. It's like a queue, right? Now a queue, and we're talking about a WAL file, right? It's a file which is just keeping data in sequence, and a queue also is keeping the data in sequence. Also, it is enabling you to read in sequence, right? And in this case, also going to enable read in sequence. So now two things happened because of that, right? One, now Kafka has become such a popular technology now that it's able to handle trillions of messages per day, right? So it's even compatible to the hyperscaler. You can just have one Kafka installation while people have multiple. You have just one Kafka installation across your organization. That means that is the data fabric now in the organizations. And what enabled is the simple technology of read-only files, append-only files with sequential reads, right? And when we do that, what happens is in this, the left side to right side transformation is significant, because now in an organization, data was spread across and everyone was kind of generating their own data, but consuming it in a different place was kind of tremendously complex. Now, because we can have an organization-wide fabric, right? It's like the data fabric. So now the architecture becomes very, very simple, right? Architecture becomes very, very simple. But this is a slight diversion, but I'm telling because of this dismantling of a database, what all things happen, right? Now, let's put together. So we have dismantled enough. Now let's put together some of these ideas and see where is industry heading with these ideas by putting it together, right? So now we discussed about Parquet, which is a very, very efficient columnar storage format, right? Which is where the data is really stored, right? And we also talked about log files, right? Which is your transaction log or WAL files, right? WAL files, write-ahead log files. Now, this is a folder structure effectively, right? And which is what we're calling a data lake now, right? Or delta lake. So delta lake is the implementation of data lake, the new generation data lakes. So what it is doing basically is, let me keep all the data in a Parquet format, and any modification that we do, we'll just collect them all in this JSON files, periodically snapshot them into these Parquet files, right? And we just keep the what is the last checkpoint, right? And keep doing more and more. So this is basically to ensure that we don't lose anything. So this 1, 2, 3, 4, 5, all that is actually, we could say that this file names itself, the sequence numbers and the name itself is like the WAL files, right? It's not a file, but it's a collection of file in some sequence, right? Now with it, what we actually achieved, right? With so Parquet is still read only, right? Parquet is still read only, but by putting this structure of logs, we could now update it, right? So now there is a big ecosystem built around it, which is using these open formats and your data logging of the transaction, the sequencing, and etc., and all of that is actually used to just put together a simple file system, right? And expose a library. That library, wherever you want, you can put it part of Java, you can put it part of Scala, you can put it part of Python. Doesn't matter where you want to put. Now you have a database of your own kind of, right? Which is not only analytics optimized, big data optimized, it is also giving you the AC transaction ability, right? And by the way, the runtime is absolutely not necessary. Your data is going to be as relevant because the data is readily usable. If you have a tool like either Presto or some other kind of SQL tool, also if it is available, you can actually explore and do stuff. And for machine learning and all that, also it is going to be useful because if you have a Jupyter notebook, then for that you have plugins like Spark and other plugins that you have. Using that also you can actually access this, right? Because now it is open file format, right? So effectively what happened is the two file formats that we talked about, right? The transaction log or WAL file and the data file itself now put together into a directory structure, which is now compatible for analytics and HT transactions as well, right? Now, this is the final slide, and this is kind of taking it to the next step, where what it is trying to highlight is, now there is a big shift that is happening also. I mean, I won't say it is a happening. It was a need, but it was not possible so easily without these kind of technologies that is in place. So typically, when we are talking about data processing, we talked about ETL, right? Extract, transform, and load, right? But then for transformation, we should know what are we looking for. And today we are focused in collecting data. We don't know what we are going to need it for in the future, right? So we should be able to host data as is, right? In whatever raw format possible, we want to host the data. We want to transform later, right? We just want to extract and load it, and transformation is going to be an iterative process forever, right? Whenever we need, we should be able to look at the historical raw data and be able to transform it in new ways, right? So now, for we to be able to do that, what happens is now there is enormous amount of duplication because we are going to generate duplicate data. So we talked about how the storage is going to become optimized, right? So now, putting all that together, this concept of batch and stream plus storage optimized for analytics, or at least the technology optimized for analytics, and how it is actually enabling this ELT, not ETL. I mean, that is where most of the things are happening. And this architecture where you store the data first, and do the iterative cleansing of it and find new use cases of it, and be able to do a unified way for both batch and streaming, right? So that is what, if you all put together, that is what is currently being named as a lake house architecture. The name is actually derived from data lake and warehouse, right? So warehouse typically was used for analytics, but effectively that has now have reached kind of its limits, right? So now the concept of these two things are now trying to get combined into create something called a lakehouse architecture, which is kind of promoting this ELT based mechanism. Store anything and everything you want to store. We'll see about processing and cleansing it later. And there is this concept of bronze, silver, and gold. There are multiple names that you can give, but basically what it means is your data is quite unprocessed or unstructured in the beginning, but as it passes through the layer, whether it is in a batch processing mode or a stream processing mode, it becomes more and more sanitized, right? And becomes relevant for either we could say for analytics use case, but it need not be limited to analytics use case. It can also be used, and it is actually used as well for the prime time, the UI use cases and those kind of stuff as well, right? I mean, it is not slow in that sense. It is not sub-second latency kind of. It is minutes latency, but the volume of data. So latency wise, it is a little low, but it has enormous amount of throughput that it can get because this all technologies are horizontally scalable, right? So this is the summary of what I wanted to cover. Any questions?
Hi, Rakesh. It was a pretty amazing talk covering the breadth of different things, starting from like machine learning or basically the users, and you also touched about the databases and also showed us the inner workings of database, that it's not really rocket science, it's just writing files below. And then you took us to the streaming and batch processing world. So I have a few questions that have popped up for you, and probably you can help answer. So you mentioned about instead of ETL, you have referred to ELT. So which means you will transform the data later, which means the data is lying as is. So is it possible to use the same data in your regular application, the front end, whatever workload is running, and have maybe just a clone or a reference of that available to the analytics application? So do everything out of the same data, because now you're not even transforming. So you can probably just keep on using, and rather than ingestion, you can just use the same copy of the data.
Yes. So what is happening in that space is we talked about edge computing, right? That is becoming a real thing. So data is really spread across geographies and across different destinations. Definitely not in the same colo data center. So data is there. So now the advantage of this lakehouse technology is that first of all, your data as is, right? The raw format is usable because it also have a structure, right? We talked about columnar data format and all that, right? So it also have a structure. So underlying data is having a structure, right? All that is needed is, do we have an interface which can just expose the data or actually take a compute, right? So it should be able to either expose data, okay, now take whatever data that you want to. It could be like, okay, give me select star from your database, or it could be like, okay, select, do some aggregate, and then with some filters, and that you should be able to take that. So you should be able to take a subset of data, or what you can do is, okay, give me a compute, right? Give me your compute, I'll just do it for my subset of data and I'll give you the result back, right? Because not everything can be exposed through SQL. So that is what is effectively happening today already, right? Databricks is one of the pioneers in that domain, which is also the founder of or developer of Spark. So they have come up with Delta Share. So they are coming up with that because we cannot really move data, right? And we have to make it useful from where they are already. And technology is going in that direction and making it more easier to achieve it. Yes.
Sure. There is another question for you. This question is from Ravi. As per Gartner report trend, for small and wide data, so you also talked about at fair length about it. And so how does it impact the storage system? How does it impact the underlying layers? And are the architectures that we have today ready for it? Or it requires some improvement, some modification, or different view of it?
I would say technology is definitely, I mean, NVMe and object, I mean, the whole storage ecosystem is effectively uh, changing to adapt to this new data, new big data movement. But when you are talking about from big data movement to, let's say, a small data and a wide data movement, I won't say that the underlying hardware have to change significantly, right? The reason is even in the wide data, your localized copy of data is not going to be small. When we talk about small and large in this context of big data space, right? When we mean small versus let's say big, we're not really talking about the relative sizes. It is actually about the relative architectures. Okay. So today, an architect is thinking about, let me take all the data in one place and do my operations versus, okay, I'll keep all my data in different places, right? So and be able to do something here and do something here. So now the problem is not really about just the storage itself. It's about the middle layer where we have to become innovative to be able to orchestrate stuff there. So it's like Hadoop came and tried to just generalize this whole horizontal computing kind of a thing. The same thing has to happen again, where the algorithms now will have to distribute themselves, right? The MapReduce effectively try to create algorithms which is distributable in nature. So similar to that, in machine learning space also the same thing have to be thought through, right? Analytics is where if your data is sitting in multiple places, your algorithm will have to somehow create a reduce phase, which is going to collect data from all the different, collect the result from all the different places and be able to kind of mash them into create a useful and meaningful result. Today's algorithms are typically monoliths, right? It is actually the algorithms which is the restriction. I won't say the storage layer.
Sure. Let me take up one more question since we would be soon running out of time. The question is from Ameya. So there have been suggestions and also trends where we plan to use disaggregated storage when we design the lake house architecture. So are there any observations or any thinking or thoughts from your side to reduce the latencies even further?
So latency is going to become a problem. So the way I see in analytics space, the biggest challenge is not the latency. While latency is a big problem, right? And the underlying hardware, the software on top of it, right? Whether it is a SSD or HDD, and on top of that, whether you have object store versus a block store, that kind of decides to a large extent your latency. But then once the data is available in your fabric, is it going to travel miles or thousands of miles before reaching its destination for processing? So these are architectural decisions that have to be made. So without putting a use case in context, right? What algorithms we want to run, what data is available where, and how it reaches there, it will become very difficult for us to kind of judge whether how the technology is going to shape the use case itself, right? It should be the use case which is should drive the technology, whether it is software or hardware or somewhere in the middle.
Sure. So Rakesh, thank you so much for joining us and sharing your thoughts.
Thank you.
Over to you, Anvit.
Well, with that, I would like to extend a deep gratitude and thanks again to Rakesh Dash of Hewlett Packard Enterprise. Thank you, Rakesh, for sparing your time and enlightening us with your talk. Oh, well, they say we can make a connection between any two people in 6 or fewer steps. Well, the 6 degrees of separation as we know it. But what about analysts who frequently require data from multiple sources for their tasks in exabyte scale data lakes? Here to speak on discovering related data at scale is Ranjita Bhagwan, Senior Principal Researcher at Microsoft Research India. Over to you, Ranjita.
Hey, thank you, Anvit. Let's see why. I don't know why my video isn't working. Just give me a second.
Is there a physical? Oh, yeah, there you are. We can see you now.
Yeah, I just picked the wrong device. So, hello. Everyone, let me share my screen. Pardon me, I'm a little unfamiliar with WebEx.
We're able to see the presentation. Over to you now.
All right. Thank you, Amit. So I'm going to be speaking about a tool that we've built at Microsoft Research called Data Lake Navigator, and it addresses the problem of data discovery at scale. This is joint work with Sagar Bharadwaj, who is now a PhD student at CMU, Praveen, who is a research fellow at Microsoft Research in India, and Saikat Guha, who is my collaborator on multiple projects, and he's also a researcher at Microsoft Research India. And a lot of this work has been presented at VLDB 2021, just a few months ago. And before I go into this, right, I'm going to give a disclaimer that this is a research project and it's an exploratory phase and it's not deployed at Microsoft in any shape or form, but we are looking into that. Yeah. Also, this is a pretty small audience, so please feel free to interrupt or please post your questions on the chat and I can take it later. Give me a second so that I can time myself. Yeah. The whole problem of data discovery is part of one larger problem, and the larger problem is of being able to do data-driven design for our cloud services. Now, as you know, Microsoft and other companies run these extremely large cloud services, which have, increased in size, expanded by leaps and bounds in the last couple of years. And so these services, they generate a lot of data. And they generate a lot of system telemetry, which captures how the system is performing or how the service is performing. All of this data is stored in a data lake, right? For Microsoft, we have an internal data lake called Cosmos. There's also Azure Data Lake, and there, like Rajesh was talking about in the previous talk, there's Spark-based data lakes as well. So the data all goes into the data lake, and then the data analyst takes all of this data and tries to make sense of it and feeds back the learnings from this to the service so that the service design can be improved. So this is a continuous process, and we call this data-driven design or inputs to the cloud service. Now, one thing that is sorely missing here is a telemetry management system. What do I mean by telemetry management? It falls into three categories. The first is data generation, right? When a developer writes a part of this service, they have to decide what to log. What is the right data to generate and store in our data lakes, right? And what is the right schema to do these aggregations on, right schemas and right aggregations to do? Or how long should we retain this data? These are important questions because, like the previous speaker said, we can actually store a huge amount of data in very raw form in our data lakes. But there is an inherent cost to doing that when you're doing this for decades. And that cost is not small. So how long should the data be retained is an important question to address. The second pillar of problems is around the idea of data consumption, right? So a data analyst needs to be able to discover the data that is there available to them. And currently, this is very difficult to do because there's so much data, so many different kinds of tables, in so many different kinds of schemas that it's very easy for an analyst who doesn't understand the nitty-gritties of each component in the system to actually find all of the data relevant to their question. And this is what I'm going to be talking about in the rest of my talk. But there are other problems as well. So there have to be certain aids to the analyst to determine what models can be used to solve a particular problem, or how do we engineer a good set of features. And finally, there's the data analysis aspect. So how is the data growing? How useful or how variable is this data? Can we build visualizations around how useful the data is, and is the service storing the pertinent data, or what is the cost of storing this data, right? So all of this together, I would put this into the category of smarts that we need to build on top of our data lake or even our lake house architecture. So with that, let me go deeper into this one question on how we facilitate data discovery. Before that, let me motivate the problem. Let's say Anita here is a developer and she needs to build a root cause analysis dashboard. So if something goes wrong with the service, the dashboard will be useful in trying to figure out where the problems lie. Okay, so she starts with a table which stores alerts that were generated by the service. So this has, a time of the alert, the type of error, and the machine that generated the alert, for instance. So she starts with this, but to build a root cause analysis dashboard, she realizes that the problem could be with the network, or it could be with the underlying system itself, or the higher level application. So she needs data for the runnings of all these different components. And she finds all of these different tables. First, she has to find them. But even if she does find them, right, she has to be able to tell that, look, the machine column in the alerts table can be joined with the server column in the system table, or the host column in the application table. And this is non-trivial to do at scale. Now, to make matters worse, the tables also have these cryptic names, right? IPFix, EDS, StoreStream. These are all real examples that we took because, I'm also part of a group that's building such tools for multiple of our services. Now, the other problem is if you stare at these two columns, which I've highlighted in green, right? These two columns are actually joinable. They are related because a machine does reside in a data center, but it's not obvious by just looking at the data that they are actually related. So we have to discover these kinds of non-obvious relationships as well. And so since all of this is right now really difficult to do, Anita reaches out to all the data administrators across these different components. And sometimes it can take months to discover related data just to build this one dashboard, right? So how do people address this problem currently? The current state of the art is to build what are called data relationship graphs. So you can think of this graph as a bunch of nodes and edges, where the node is a table, a database table, or a stream of data. Let's just call this table for now. And an edge between any two nodes is annotated with a relevance metric, which the higher the relevance metric, the more related those two tables. Now, how do people compute these relevance metrics currently? It is a combination of both data-based metrics and metadata-based metrics. So a data-based metric, an example of a data-based metric is the Jacquard coefficient, which captures overlaps between the actual values that are stored in the two columns. So the more the overlap, the more related two columns in the table are, and therefore the more related the tables are. You can think of it that way. The second set of metrics are metadata metrics. For instance, column name similarity. So you could say all columns named server are related, for instance. This is a way of capturing metadata metrics. Now, this is what state-of-the-art techniques do. But the problem here is that finding the right metric combination is hard-coded because there is no context to learn from. What do I mean by this? Most of the current techniques that have been published, they say, well, we're going to take data metrics and metadata metrics and just form some arbitrary combination of these, and based on that, give one relevance metric to each edge. But this is not ideal because it's then left for the data analyst to figure out, well, is a relevance metric of 0.8 or 0.7 good or bad? it's unknown, right? So that is one problem. The other is that these current state-of-the-art techniques, they involve going through all the data in a column. For instance, to compute the Jaccard coefficient, you have to do one sweep over the entire column of a table. And so these techniques do not scale well when you have a table with hundreds of millions of rows, which is quite standard really these days. So the techniques do not scale well for large amounts of system telemetry. So here is where we spotted an opportunity, and that is of this cross-layer advantage we have at enterprises. At Microsoft, we've had millions of daily jobs run over 10 plus years on Cosmos, our internal data lake. And thankfully, these jobs are all logged, right? And so there's a large number of logged scope scripts. Scope is a SQL-like language and they have these join clauses. And these join clauses, they leverage developer knowledge over years, over decades of what columns are related. So if you stare at this little snippet of a scope script that I've selected, this is saying from the join clause that the server column of a table called storeops is related to the column called machine name from a table called machines. Now, interestingly, storeops is maintained by one organization and machines is maintained by another. So if somebody is within one organization, it's non-trivial for them to actually understand the schema and the data in a different organization's data lake, right? But because we are capturing this information from these scope scripts, we can actually automatically get this or automatically leverage this developer knowledge, which wasn't possible earlier, or wasn't possible without all these queries that have been logged. Okay, so now what do? We have access to these join clauses over 10 years or so. So first thing we do is to learn a classifier. All of these join clauses are giving us a ground truth, labeled data, that these two columns across these two tables are related. So we can build a classifier. Then the second step is to use that classifier to build a data relationship graph. So this is an example of a data relationship graph where you can say that the machine name column in the alerts table is related to the server column in the EDS table with a relevance of 0.92 or so. So in the rest of my talk, of which I have about 20 minutes left, I'll go over each of these in a little more detail. Okay, the first step is to learn this relevance classifier. The first thing to do for this first step itself is to collect ground truth. So like I said, we've got these joined column pairs. Then we pick a random set of column pairs and label them as negative, that they know they're not related. Of course, that could have some errors, but I think the number of column pairs are so huge that those errors will be minimal. Once we have this ground truth, we have to extract features from the data. So we extract, like I said, both metadata and data features, and I'll go into what are the different kinds of features in a bit. Next step is to train a random forest classifier. We tried different kinds of classifiers. The random forest gave us the best bang for the buck. And finally, we have this classifier to which we can feed unseen column pairs or any random pair of columns, and the classifier will spit out whether those columns are related or unrelated. Okay. So this is the first step. We've built the classifier. Now, let me talk about the difficulties we faced when we were actually extracting join clauses from scope scripts to generate that ground truth, right? So for each of these scope scripts or these queries, right, we have a query plan or an abstract syntax tree. So this is what it looks like. Right? So we parsed about 1.6 million scope query plans in less than 6 hours. We got about 16,000 unique column pairs from these join clauses. But there are various sources of error. For instance, aliasing, right? Some developer suddenly changes the name of a variable from org to organization or the other way around, and we lose the connection between org and organization. And we lose a lot of valuable ground truth because of these aliasing effects. The other problem is in transformations. So in the join clause, you may actually use a UDO a user-defined function that will convert an address to a country and then do a join with another column which actually captures country. And this also causes some inaccuracies in our data, but this is something we had to work with. Okay, so let me talk about what are the features we use. This is the feature extraction. The first set of features are metadata features. So we take column names. I got a question. Let me take that in a bit. Maybe at the end itself is better. Sorry. So first we take the column names and we use a custom tokenizer to tokenize them, right? So machine name becomes machine name, server stays server, everything becomes lowercase. Okay. And then we also figure out column name uniqueness. So we use simple IDF based metrics to say that, okay, the token name is very common, or ID is very common, right? You will agree with me if you've done any data wrangling that the words name and ID are just too common. We throw them away. We don't consider them. And then we measure column name similarity. So we use pre-trained software-specific token embeddings to do this, so that we can capture words like machine and server are actually related, right? So, and we use cosine similarity across multiple tokens to actually capture this column name similarity. Note that the number of features we use is not much. It's of the order of 10 or 20. So the classifier itself is not complex at all. But we still needed something to put things together, put these multiple features together, which is why we used classification. Next are the data features. So we sampled, so like I said, right, going through hundreds of millions of rows is not feasible to do this. So we went through maybe the top, we tried 50,000 and 2,000, and we decided to go with 2,000 because we didn't see too much difference between the two. And for we sample the top because random sampling is again impractical in such large data lakes. And then you compute Jacquard similarity of the sample, and then we used Schlosser's estimate. There's a paper on this to actually extrapolate that to the whole data set. Then we did inclusion dependence as well. And the third metric which we used was quite useful, was this pattern similarity. So an example is shown in the table here. So we take source, data center, and location, and we mask out numbers, right? And that leaves behind these terms, and then you do Jacquard coefficient on top of this. And that gives us pattern similarity. So we used, this is a subset of the data features that we used. Note that the Jacquard similarity and inclusion dependence may have errors in it. But this is the best we can do. Okay, so I've spoken to you about learning the relevance classifier. Now I'll speak briefly about how we use the classifier to build the data relationship graph. Let's say we have a data lake with 30,000 columns, right? Now, just using simple combinatorics, the number of column pairs out of these 30,000 is 450 million, which is just prohibitive, again, if you're computing this over and over again, periodically, which we do. Now, so we need some pruning to figure out that certain set of these random column pairs are just not, doesn't make sense to consider them in creating this graph. So to do that, we do two things. One is metadata clustering, which clusters columns with similar column names together. This is again based on the word embeddings that we've done. And then anything that's not within a cluster, we don't generate column pairs for that. The other is reverse index on the data samples. So if two columns have similar values in their data samples, we will consider them in the in creating this graph. So from this we get candidate column pairs, and from 450 million we cut it down by these pruning techniques to about 40 million column pairs. And this is on a real data set, which is why we have this number 40 million now. Then we feed this to the classifier, which tells us, okay, this column pair is related, this column pair is not related, and finally we get this data relationship graph, with edges between related columns and nothing between unrelated columns. So let me tell you a little bit about our evaluation. Yeah. First thing is to actually examine how good is the classifier, right? So this table here shows us the F1 score that we got with metadata only classifier, which used only metadata specific features. There itself, we got a pretty high F1 score, which was 0.94. And note here that it's just, we are taking the joint clauses as ground truth here, dividing the joint clause into a train and a test set, and then just trying to figure out from the test set of joint clauses, how many the classifier gives are actually related. So that's the reason that this is not evaluating the data graph itself, it's just evaluating the model. So F1 score with metadata only features was high at 0.94. Right? With data only features, it was a little lower, 0.87, but taking both together, we got 0.96, which is pretty good F1 score. But the model itself is doing quite well. Now, here are some example column pairs which the metadata only features or the data only features were specifically useful in capturing. For instance, user ID and customer ID was captured by the metadata only features, and for whatever reason it was not captured by the data features. Data only features were able to capture strange aliasing like MNGR and manager name, which our word embeddings cannot capture because this is very, developer specific, what kind of abbreviation they use. So this is from real data that we could capture all of this. So the conclusion here for us, from a scale point of view, was that even building a metadata only model, you can do quite well. And it has way, way better scalability than anything that uses data-based features. So we can start out with metadata only models, deploy it, and see how we can add on data-based features. That was our finding from this experiment. So the next set of evaluations was on actually building the data relationship graph. And we had to evaluate this on two dimensions. One was how fast can we build the data graph? And second, how good is it? Does it actually help us find related columns? So for the first question, it turns out that our technique scaled very well because it took about 81 minutes to build the graph for a 4.5 petabyte data lake, which is about 30 times faster than state of the art. For state of the art, we used two systems called Josie and Aurum from IEEE 2018 and SIGMOD 2019. The next question was, is the data graph useful or accurate, right? So for this, we took data from an O365 core service. We had domain experts label column pairs as related or not. And so we, of course, when there is manual labeling like so involved, the scale of the experiment is smaller. So we had 266 manually labeled column pairs. And then we actually evaluated how many of those column pairs were actually flagged as related by Data Lake Navigator, our data relationship graph technique, and how many false positives and false negatives we had. Based on that, the F1 scores are presented in this table on the right. Data Lake Navigator gave us an F1 score of 0.79, which was significantly higher than what Josie and Aurum, which are the state-of-the-art techniques, gave us. So we have an accurate yet scalable technique of data discovery. And the secret sauce here really is the access to these previous user queries, which helps us do so much better. So with that, I'd like to conclude. I have spoken about the Data Lake Navigator. It's an automated system to capture relationships in large data lakes. We use ML to learn characteristics of joint column pairs from a decade or so of user submitted jobs. It is a scalable technique. It took 81 minutes to build a data graph for a data set of 4.5 petabytes. And it is, by the way, it's not significantly more for larger data lakes. It's accurate because we have significantly outperformed state-of-the-art systems on a manually labeled data set that we create. So thank you very much, and I'm happy to take questions at this point. I know I finished soon, so yeah.
Yeah, that was a fairly relevant and nice talk, because we have been playing around with data and building models ourselves. So this is pretty much up the sleeve for us. So here are a few questions that we have for you. So is the performance of the model dependent on the method that is used to measure, like similarity or distance? For example, if instead of the Jacquard, other methods were used, will the classifier vary in the performance itself?
So by performance, I'm assuming that the person asking the question means how good the classifier, the accuracy of the classifier. And I'll answer the question assuming that. Yes, absolutely. It depends. You know, it's a classic problem of feature engineering. So if instead of Jacquard, right, you use some other metric, it is highly possible that the classifier will do better. Now, there is actually one technique that we have examined since this work was published, and this is on learning regular expressions by giving examples from the columns. So you can think of it as, you know, you feed in some examples of values of the column, and there are these tools, which open source tools, which will give you a regular expression or a set of regular expressions that will capture the most specific regex that characterize the inputs or the examples you've given. Now, this helps us greatly, right? However, there's a cost associated with generating these features. So the regular expression learning is more expensive than, say, doing vanilla Jacquard. Or Jacquard is more expensive than just doing column name similarity. So when we decide our set of features, we have to keep in mind the cost of generating these features as well, and the bang for the buck they give. So even if you generate those features, how much accuracy gain are you going to get? So you have to consider all of that before you actually build the final version of this system.
Sure. So the next question for you is that you are actually building a relationship between the different data. And here the person asking the question, Ameya, he says, I'm wondering, in case of an execution anomaly, how fast and with what kind of probabilistic accuracy can it be established on all related information?
Could you repeat that question, please? I didn't quite get it.
So since you're building a relationship, right, and we talk about accuracy, so the portion which is not, as in like 1 minus the 0.94, or where it didn't go fine, right? So it could be a false positive as well.
Yes, yes.
So yeah, so when you're executing, how fast and with what accuracy can you establish, like when you introduce and start running, like, oh, I think we made a mistake for these pairs?
Yeah, yeah. So one thing I probably should have mentioned in the talk, but I skipped that, was that all of these are best effort mechanisms. Anytime you throw machine learning at a problem, or any data-driven technique, in fact, will never be sound, nor will it be complete. So there's always going to be false positives and false negatives. So a lot depends upon the application that uses this graph. So for instance, if I build an application around this data relationship graph, which allows a search, right? So you as a user can put in, I have this column called machine, find me all the related columns to this, right? And then the search engine will use this graph at the back end and then give you a set of responses. Then it could throw out a completely unrelated column, right? Any search engine will do that. And then it is up to the user to actually use their, use their domain knowledge to figure out, okay, this is actually not really useful. And they can mark that, and the system can actually take feedback from, these kinds of annotations. And these are very standard techniques that have been looked at in the IR literature and machine learning as well, on how this feedback can be taken. But that said, right, it really depends upon the use case. So in this example that I gave, we haven't yet built an application that uses this, by the way. But in this example that I gave you, it is probably not too much effort for the user to tell us that it's not related. Or even if they don't tell us, it's not such a big deal, because showing one false positive in a list of 5 to 10 queries may not be such a bad thing, especially if the alternative is not having anything at all, right? So that's where I'm coming from. We're coming from a very low denominator. So yeah.
Okay, so I think you might have answered this question partially, but I'll still put it across in case you want to add on to or re-emphasize certain aspects. So the question is from Soham. Does the relevance classifier also consider data similarities with different formats? Say a prefix that does not carry over to a different table?
To some extent. So when we built our parser for the scope scripts, right, we put in some heuristics in it. So if we have a join clause which uses a prefix computation, right, or substring computation, then we can actually special case those and figure out, oh, okay, one column is a prefix of the other column. And we can use this kind of information. But to generalize that to any kind of transformations is rather difficult. So while we can do it for prefixes or postfixes or certain kinds of substrings, which we did with also the pattern masking that we put in, for other kinds of transformations, for instance, right, if people who know networking will know that IP address can be translated to a DNS name. So we saw a bunch of these kinds of joint clauses where one column was the DNS name, the other was an IP address, and then there was a transformation which converted the IP address to the DNS name. It's very difficult to, for us to automatically figure out how to deal with this. So once you go into more complex transformations, all bets are off.
And I think it could be also dangerous at times, because sometimes when you name certain columns, you end up putting the same prefix followed by some name just to give it a unique name.
Right. Oh, so I assumed that the person asking the question was talking about data, but yes, with metadata too, this might happen, and what you're saying is true. Yeah. So the errors happen because of these conventions that developers use, right, for naming, etc. Oh, so Soham says not the metadata, but fine. But I think what Ankit brought up is also valid, that somebody can just say, system colon this or network colon that, and that also can introduce all kinds of spurious similarities. But the hope is that this column name uniqueness feature that we have will capture some of that. If system is used across a lot of tables, we'll just drop it because it's not really adding anything. Yeah.
Sure. So it was an amazing talk, and really great to learn like some of these things can be automated, and we can search or get data out of where otherwise the relational database systems had the forte, like because the schema is all well defined and you know the entire system well. So really amazing talk, and thank you so much for joining us today. Over to you, Anvit.
Well, thank you so much, Ranjita Bhagwan of Microsoft Research India, for spending your time and your talk as well.
Thanks.
It's time for our next session, and let's talk about high-performance computing. Here to speak on scaling AI and big data with Deos and Optane are Johan Lombardi, Senior Principal Engineer, Intel Corporation, and Jiafu Zhang, Big Data Machine Learning Engineer, Intel Corporation. Over to you, Johan and Jiafu.
Everybody, thank you. I cannot share currently.
Yeah, just a moment. I believe
okay.
It's coming.
Okay.
Yeah, you should be able to do it. Yeah.
Can see my screen?
Yes, we can see
Yes.
yours. Yeah, but we are unable to see your video. If you can, please do turn on your video.
Yeah, let me switch off. Where is this damned? Yeah, sorry. I think I will need to restart. It cannot access my video, so I will have to restart to rejoin WebEx. Are you okay without video? You want me to rejoin?
No,
Up to you.
I think it's all right. Probably you can just start sharing. Chinappa, do we have some time to restart? No, I think we can just start with the presentation. Over to you, Johan.
So hi everybody, I am Johan Lombardi from Intel, and I have the pleasure to present with Jiafu today from the Big Data division. On my side, I am the lead DAOs architect, and I've been working on DAOs since 2012. So it has been almost 9 years that we have been on this project. Initially, we started with several fundings from DOE in the United States to develop the next-gen storage system for exascale and beyond. After several research programs, we end up in 2015 to write DAOs as it is today, as a standalone product that can operate with other storage tier, but is really is a storage tier by itself, right, and not a burst buffer or anything like that. And then we have been working on stabilization, creating partnership, proposing a commercial offering for DAOs since that time, and you will see where we are on our roadmap in the next few slides. So in terms of structure of this presentation, I will give you first a quick DAOs overview, explaining what problem we are trying to fix, what kind of technology we have selected to address this challenge. I will then present an overview of the DAOs ecosystem. For those of you who are familiar with Ceph, we really provide a new API similar to Rados, that is called the DAOs API, that really allow a lot of capabilities. So effectively, it allows you to integrate more directly your data model or your specific framework with the native DAOs API to provide more functionality and more capability. So I will give you an overview of this overall ecosystem. Then I will transition to the second part of the talk, where Jiafu will step in and talk about the DAOs integration with Spark. We wrote a Hadoop connector for DAOs, and we've got some very interesting results using the native API as well as the POSIX emulation. And then last part will be some idea about what we could do with the asynchronous API. So the DAOs is fully asynchronous, but obviously you need the framework or the middleware to be asynchronous as well to be able to leverage this capability, right? Otherwise, the framework will always do an IO block, and then whether you are asynchronous or not under the hood doesn't matter. So you really need to take asynchronous up to the highest level of the stack, and Jeff will give us an overview about the work he did with Spark. So with this, let's move on to the first item in the agenda. So what is DAOs? DAOs is a distributed storage system. So on the right side, you have a small picture representing a fabric. So a cluster with a fabric. So there are different ways to deploy DAOs. It can be more like the pooled model when you have dedicated storage rack, or you can also have the hyperconverged model where you integrate storage into the compute rack. All our production deployment to date are more on the pool model when you have dedicated storage rack. The hyper-converged disaggregated model is still something we are working on, and there might be installation in the near future. But so far, we have dedicated storage rack represented here in light blue. When you have DAO storage node that provide the global namespace to all the compute node, and the compute node are represented in gray in this picture. So we provide storage pools over the network, right? So you can partition this distributed storage in different pools, like ZFS pools. DAOs has a lot of similarities with ZFS, except that DAOs is distributed versus ZFS was a local file system. So you can carve out all those storage systems into a single storage system and then create different pools that will be distributed across all those storage nodes and can be associated with different projects typically, right? You can have one project for doing some certain type of computation and another project in your institution that will do something else, right? But they won't step on each other's toes. They will have totally isolated storage with different capacity and so on. So the requirement we had really early on was really to provide a very high level of performance. So we decided to leverage next-gen storage technology. So we are built on top of Nvme SSD and persistent memory. We decided on day one to have two different channels to storage, one for persistent memory, where we store all the metadata that are directly mapped in our engine, and then all the bulk data are stored on SSD. Really, the goal is to provide in a single storage tier very high bandwidth, very high IOPS, in order to be able to serve HPC needs, right? HPC needs super high write bandwidth, read bandwidth for checkpoint restart. But obviously, there is more to that, right? With complex workflow that we start to see that combine HPC, AI, and big data, you need to be able to sustain also very high IOPS, right? And also read bandwidth becomes very important for AI. So the idea is that instead of having a custom storage tier for each of those solutions, trying to have a single storage tier that can serve all those different type of application. We also decided at the beginning that we wanted to have strong consistency. So DAOs is using distributed transaction in the term of database, right? So we have serializable transaction. So it means that you can implement SQL natively on top of DAOs, and the storage will be completely distributed, and your SQL database will be serializable. And we are working on some SQL support on top of DAOs to expose this capability. Very close to the application, as I said, very tightly integrated with application. That's really our business. Capacity-wise, you can build very large DAO system, but obviously, since we rely on the latest and greatest storage technology, usually this is not the cheapest. So we combine DAOs with capacity tier, like S3 or other storage tier that are more targeted at capacity, not necessarily performance. And we try to integrate DAOs with those type of technologies so that we can provide super fast storage to the application and then capacity through the tiering with a capacity tier. Okay. So in the overall cluster, that's roughly what I said, right? You have the compute node where you have all the compute happening, capacity storage on the right side. It can be cloud object store, or parallel file system, whatever you prefer. And the IT is to inject a high performance storage tier in the middle, right? So it's not a burst buffer. It means that this storage tier can operate by itself. It manages its own metadata. You can run without a capacity tier, but obviously you will be limited to the capacity of the DAO tier at that point. So as I said, different pools, you can create pools over different storage node and use them for different purposes, right? To store your checkpoint data, as a scratch system, key value store. So you will see it in the next slides. In terms of node design, so we provide very high level of performance. So we are very sensitive to the hardware. So this is a typical DAO's node design that we put into the storage rack. So today we mostly use dual socket system. We have some deployment with 4 socket system, but dual socket is more standard. So what we do is that we have persistent memory attached to both CPU. We have SSD attached to both CPU, and we try to have a fabric interface to each CPU. DAOs provide a level of performance that is so high that we are very sensitive to the traffic over the UPI, over the cross CPU link. So what we do in software is that we start a control plane that is written in Go. That is just a single process that starts. Look into with AGBU-lock, the configuration of the storage node. How many CPU do you have? How many persistent memory, fabric interfaces, NVMe SSDs, and detect the affinity, right? So, and it try to configure 2 engines here. If you have a quad socket system, we run 4 engines. So we run 1 engine per socket, per CPU. And it's going to configure everything in a way where it only ever access local devices, right? It will store the metadata in PMEM, the PMEM locally attached to the CPU. It will send the IO through the network on the fabric attached to the CPU, and always use SSDs directly connected to the root port connected to the CPU. The two engines are independent. They don't share anything except that they run on the same node. So they are part of the same fault domain. And obviously DAOs take this into account, right? So we have massive level of parallelism inside the storage node, but obviously when you do a replication over the network, you don't want to place two replica of your data on the engine running on the same storage node, right? Because if the storage node is a single point of failure, so if it fails, you will lose your two replica. So that's the reason why we inject the data at the management level, so that the placement algorithm from DAOs will not place replication or erasure code, data fragment or parity on the two engine on the same node. So this is managed by DAOs itself. So in terms of media management, I mentioned that we have both persistent memory and NVMe SSDs. So first of all, we need this on every storage node, right? Every storage node on our side, they are all equal. There is no dedicated metadata service or anything. They all play the same role. And on each of the storage node, you need some persistent memory and some SSDs. Effectively, we can run completely just with persistent memory. Obviously, at that point, I mean, you will be limited by the capacity of PMEM, but we combine it with SSD to provide capacity. We cannot run today just with SSD, right? You need both. And the reason is because all metadata that maintained by DAOs are directly stored in PMEM. And then if the data is small, we'll store it in PMEM, and we'll just have a direct reference in the PMEM tree from the metadata tree to the data inside PMEM. Or if the data is big, and for DAOs big is like 4K and above, then at that point it will store the data of the application on the SSD, and we will just in PMEM have a reference to the LBA on the SSD where the data is located. And DAOs has this capability where you can do very small I/O, like 256 byte I/O. You're gonna get the performance of PMEM, the latency of PMEM, and in the background, DAOs will aggregate all those 256 byte I/O into larger blocks and migrate them to the SSD in the background. So you will see really the performance on write of PMEM, but effectively the capacity of the NVMe SSD, right? Because we have this ability to do aggregation and migrate data to the NVMe SSD. What we don't support today is prefetch. So when it's migrated to the SSD, if you read it back, then we will have to read it from the SSD, but we don't keep it in PMEM. So for instance, you are writing 256 byte, and so on. You get a 4K block at the end. We migrate this 4K block, but then when you read, let's imagine 256 byte again, we will pull this 4K block from the NVMe SSD. We will serve the 256 byte IO, and then throw away the 4K block we read, right? So, but there are work we can do in the future to do prefetching and to also being able to serve very fine grain on read for this purpose. In terms of ratio, obviously, PMEM is more expensive than the SSD. So you can't afford to have a system just with PMEM, and really the ratio you maintain on every node between PMEM and SSD for us is between 1 and 6%. So it means 1 terabyte of PMEM for 100 terabyte of SSD. This is 1%, and 6% would be 6 terabyte of PMEM for 100 terabyte of NVMe SSD on a node. And this ratio varies depending on the workload, right? And so it depends if you are doing a lot of key value store operation with a lot of tiny key and values, then you will need more PMEM. But if you are doing more larger blocks, like you are doing this as a file system and you will never see an IO below 4K and so on, then in this case, you can afford to go as low as 1%, right? And we have a simulator, a small script where you can describe your traditional workload, and the Python script will tell you at the end what ratio you need to make sure you utilize the capacity of PMEM and SSD the most efficiently. So I mentioned pooling. So this is really the overall framework here. So we have this notion of storage pools. You have the Apollo project at the top, which is one pool. You have the Mercury project, which is another pool. Those two projects are completely independent, but they can share the same storage system. And we have this notion of engine, DAOS engine that can run, as I mentioned before, and the data will be distributed, sharded across all the engine. But we still have here persistent reservation of storage, right? So the Apollo project is represented here in dark blue, right? So it slice the PMEM and the SSD everywhere. So this is storage that is reserved for your Apollo project that you can use. And the Mercury project is represented here in purple. So let's imagine it's only you decided to allocate this project only on one engine. So it's going to be stored there. But everything is partitioned. If one project gets full, it will only get full across the space that was allocated to this project by the admin, right? It won't consume the space of another project. We have strong space reservation system through the pool. So that was it for the overall overview. Let's now move on to the DAOS ecosystem. So as I mentioned before, so DAOS is end-to-end in user space. By the way, I didn't mention it, but it is open source. So we use a BSD plus patent license. It's completely available on GitHub. And everything is end-to-end in user space. So we do full OS bypass. It means that the engine, when it starts, it does a few system calls at the beginning to memory map the PMEM and to be able to send I/O from user space to the SSD by using UIO or the IOMMU. But then when it's done, it can receive I/O from the network in user space and write to the storage to the storage or PMEM or SSD directly in user space. It doesn't do any system call, and this is very critical to achieve a very high level of performance, very low latency, which is very much welcome for AI app, but also very high IOPS for big data and high bandwidth. This is really our model, but we haven't do end-to-end user space model on the client. Right? On the client, DAOS is the client for us is just a library, which is called libDAOS. Sorry about this. That can just be, I mean, you can write your application directly on top of libDAOS or use one of the middleware that we have already integrated with libDAOS. So this is the overall ecosystem. We have our own POSIX abstraction on top of libDAOS. That's called libDFS that allow you to run all the legacy application. We have integrated HDF5, MPIO, HPC middleware that can run directly on top of libDAOS to end-to-end user space IO and leverage the libDAOS capability. Hadoop connector, Jiafu will talk more in the second part of this presentation, but the work we have done here. We are working on Python integration. So we have a PyDAOS interface that is being integrated with PyTorch. And we are working a file system backend to TensorFlow IO that should be available very soon. It's almost completed, that allow you to run TensorFlow directly on top of DAOS. But beyond that, beyond all those frameworks, we have had a very good traction with specific industry partner. We have specific data model for domain-specific requirement. Like for oil and gas, they have this Segway format. So we have been working with oil and gas partner to integrate their data model directly on top of libDAOS. We are doing the same thing with climate and weather forecast with FDB. And we have been also working with CERN to integrate root format for particle physics and data acquisition from Atlas directly on top of on libDAOS. So Intel provide level 3 support for DAOS, and we have been working on enabling an ecosystem with partners. So we work with all the major vendors today to make sure that they add DAOS to their offering. But we also work with cloud provider like Google Cloud. We had the user group, DAOS user group, a few weeks ago when I co-presented with Google on how to deploy DAOS in the cloud. And we are, so you see many names here, and we are also going to have 2 very big deployment next year, early next year. There will be LRZ in Germany, but there will also be Argonne that will deploy Aurora, and that will support a very DAOS as a primary storage system that will support a bandwidth of above 25 terabytes per second. Right, that's what the system will be capable of achieving. In terms of roadmap, we have shipped, so as I said, we started this adventure in 2012, and we shipped DAOS 1.0 in 2020, 1.2 earlier this year, and we're now working on the big new release that should go out this week, I hope, or next week, but very soon. That will be DAOS 2.0, this version here that comes with Erasure code, a lot of telemetry, capability, and so on. And we are on the pace to deliver a new DAOS version every 6 months. So 2.2 will come the first half of next year, then 2.4 the second half, and so on. So we will be supporting different type of distribution. So we will be supporting Rocky Linux next year. We will be have support for Mellanox UCX interconnect, and also HP Slingshot. So there will be a lot of good things that will be coming in the next few releases. Let's now move on to the second part of this presentation, where we will transition to Jiafou to give us an overview of the work he has been doing on Spark.
Thank you, Johan. So there are two parts for Spark DAOS integration. The first part is the overview of Spark DAOS integration, and the second part is DAOS asynchronous API support in Spark. So Spark is a unified analytics engine. It has several high-level tools like Spark Circle, Spark Streaming, and MLlib for machine learning, GraphX for graph processing. They also support different languages like Java, Scala, Python, and R. And to manage resources like CPU and memory, Spark also supports multiple resource manager like EN, Mesos, Kubernetes, and its own standalone resource manager. To connect to different data sources, Spark supports HDFS, Cathedral, and HBase. So nowadays, Spark is widely used in different companies. Next page, please. There's a faster remote storage. It's necessary to integrate Spark with DAOS directly. So to enable and accelerate Spark with DAOS, we have two things to do. One is use DAOS as input-output storage instead of typical HDFS. And second is use DAOS as shuffle storage instead of local file system. So on the left, as you can see, it's a co-located cluster. Spark take input, output, and data to HDFS, and then shuffle read and shuffle write and shuffle read from local file system. Each load need to provide both computation and local storage. But for DAOS, we use disaggregated cluster on write. Both input output data and shuffle data will be stored in DAOS. Okay. Next page. So this Spark is a JVM-based application, and DAOS is written in native code. So we need to use JNI as bridge. And in JVM, for each I/O operation, we will have I/O description object in JVM. Then we use it to read and write to DAOS. Each I/O description object will have two buffers. One is description buffer, and the second is data buffer. So to enable zero data copy, we use off-heap memory, also called direct memory, so that we can only transfer memory address to DAOS. Data will be read and write directly to the direct memory. Next page. So Hadoop file system is widely supported in industry. Like HDFS is the implementation for local disk, and the S3A file system is the implementation for Amazon S3 file system. So for Dell's Hadoop integration, we also choose Hadoop file system as interface. So here we use Dell's Hadoop file system. We have Dell's Java wrapper and Dell's DFS library underlying. Next page. So before we're talking about our customized Spark Shuffle plugin, let's see what Spark Shuffle is first. So for each map task, it processes records and serve into different partitions, which is sorted and indexed in local file. And later reduced tasks take their partitions from local files in each compute load remotely. And as you can see here, we use local file as shuffle storage. So next page. So as our first customized remote shuffle plugin, we use Dell's container as shuffle storage. Partitions from different tasks is still sorted and stored in Dell's file. Here is Dell's file, and that reduced task take their partitions from different Dell's files. Yeah, let's see the performance in next page. Here the benchmark with different shuffle block sizes. As you can see, the performance is not very good, around 200 kilobytes. So we did some analysis and we found the frequent file lookup and open has large overhead when doing shuffle read. So especially when the shuffle block size is very small. Thus, we come up the second option, the Dell's object-based Spark Shuffle. So instead of use Dell's POSIX container and Dell's file as shuffle storage, we use Dell's object, and we use Dell's object API to write and read D key, A key. So as you can see, partition is written on the D key, A key, and partitions from different map tasks for specific reduced task are written on the same D key. And each reduced task take all its partitions from each corresponding D key. So it actually the D key will act as aggregation for the partitions. So it will facilitate the shuffle read. Next page. So here's the performance. As you can see, when it's the performance is improved a lot, especially the shuffle block size is around 200 kilobyte. The performance is about 1.5 times of Dell's file-based shuffle plugin. For the shuffle write, it remains good as the Dell's file-based shuffle plugin. But however, as you can see, can you scroll back? As you can see, the performance is still not very good. Still some room before reach the hardware limit. So we have some discussion with Dell's team, and we decided to support the Dell's asynchronous API in Spark. So let's move to the next page. Okay, and Dell's asynchronous API is event-driven. and each asynchronous operation is bound to an event, which belongs to an event queue, from which we can pull the completeness of event. And there is one event queue per process. It could be a problem for some platform like JVM. Since tasks run in threads, if there are large number of threads in one process, event queue could be a bottleneck. So next page, in Java, we create one event queue per thread instead of process. It has several benefits. The first is avoid potential bottleneck, and the second is avoid memory sink for asynchronous objects among threads. And we can also configure how many lines per event queue. From Intel API test, we can see the asynchronous read is much better than synchronous read. If we have more than 30 threads per executor. So to support Hadoop asynchronous API in Hadoop DELS, we first abstract the I/O layer so that we can provide both synchronous and asynchronous implementation. With asynchronous implementation, we first have I/O description object, then we bound it to an event, which is from event queue. Then we call the asynchronous operation. After that, we pull its completeness from there's event queue. So it's a process of like asynchronous operation in Hadoop DELS. Okay, next page. We here's the benchmark with the workload DFS IOE. For the read, synchronous and both synchronous and asynchronous performs equally, reach about 96.6% of roofline. Of course, there's some room to improve. Next page. And for the write, asynchronous APIs performs slightly better than synchronous API, especially when we have more cores per executor. And for the shuffle plugin, we have two interfaces to abstract. One is shuffle DELS read, and the other is DELS write. As Hadoop DELS, we provide both synchronous and asynchronous implementation. For the asynchronous implementation, we first have IO simple description object bound to an event. After calling the asynchronous operation like fetch, DELS fetch or DELS update, we pull its completeness from DELS event queue. And here the performance of scalar in memory repartition. The shuffle block size is 200 kilobyte. As you can see, both synchronous and asynchronous reach roofline. But for the shuffle write, asynchronous API performs much better than synchronous write, especially when there are more cores per executor. Yeah, I think that's all for my part.
Yeah, thanks, Jafu. So just that's the last slide of conclusion. So I put a few links in there about, so as I said, it's completely open source, so it's available on GitHub. We have online documentation at docs.daos.io. It's also on docs.daos.io. We have a community mailing list, so we have a very active community. So we have a mailing list, but a lot of is happening lately on Slack. So there's a lot of exchange on Slack, and which is great. We have all the engineers there helping for people who want to try it out. We got the DAOS user group, a few weeks ago when it was a live presentation for 4 hours and a half from partners and new developer from the Intel team, from outside Intel. It was a pretty good event with a lot of attendees. We went up to almost 150 attendees at the top. And so everything all the presentation were recorded. So if you go to doug.daos.io, you will see all the presentation available online, and you also have the recording of each of the presentation that is available in case you want to have a look. Any question, comment from anyone we can do in the remaining time?
Yeah. Hi, Johan and
Hi.
Jiafu. It was a really great talk, and DAOS has been like up on the news and charts for its amazing and blazing performance. So everyone is probably all clued to hear more about it. So here's a question. The question is from Amya. So he says, thinking from a large dataset processing like in Spark, PMEM, and SSD together seems to boast the data and access movement operations. Also, Intel did work on optimized analytics package to efficiently process and move data. So are these through a common theme or vision? Are they related? Any thoughts that they could work together?
So maybe you can give me more information. You are talking about this DAAL library, for instance, or any other type of work. I mean, Intel is a big company, so there is a lot happening, obviously,
Sure.
on many tracks. So I'm not sure what effort specifically.
Amya, you can probably unmute and directly ask.
Yeah, Intel has another project called Optimized Analytics Package. It has optimized multiple Spark libraries to efficiently process the data and move the data across the multiple nodes in the cluster. So what it tries to do that, rather than doing the row-based processing inside the Spark engine, it tries to do columnar processing, and it tries to use PMEM, and it tells that, how best you can use Intel Opt-in for that job.
Okay.
And this DAOS project also, it's talking about that, this PMEMs and SSDs. So I was wondering that both are part of the same vision, or they both are contributing to some common vision of Intel.
Jiafu,
yeah,
there is anything you want to say?
Yeah, I think he's talking about the OAP project from our organization. It's optimized analytics package. It includes multiple things like Spark Circle and remote shuffle plugin. I just showing to you guys. There is a project called A21 for the Argonne National Library. National Lab. So yeah, we have a joint effort to deliver both stealth, fast stealth, remote storage, and optimized analytics package as a remote shuffle plugin.
But Jiafu, I think the work you have been doing here, is it complementary to this OAP project, or there are places where there might be some overlap, actually? Do you know?
It's a part of the OAP. Yeah.
Okay.
It's a part of OAP. Yeah.
Okay, that is good to know that it's a unified effort in a common direction rather than two projects trying to do the same thing.
Yeah, I think on their side, it's more like the runtime. How do you get the data and the runtime into format, I gather, at least, is into the PMEM. For why DAOS is really the persistent storage, right? So the data is there. It's gonna stay there after the job has returned. So yeah, definitely we will investigate more into synergy with this team for sure. Thanks for the question.
Sure. There is another question that's about, you mentioned that for the backend connection, that is to the SSDs, you would be using Nvme, and this is facilitated by the RNIC. So when you look at multi-tenant kind of workloads, more than one user using the same cluster. So do you see some challenges, any observations, things to be taken care of?
So, you know, first of all, DAOS is a client-server model, right? So when you said SSD, you mentioned NVMe, right? So we don't use NVMe or Fabric on our side. The protocol here, let me see. The protocol, yeah, maybe I should use this slide. The protocol here, so you have the compute node, the compute instance at the top, and the storage instance at the bottom. Over the network, this is our own protocol, right? So multi-tenancy is managed this way. The compute node will set up, will have an endpoint, they will start an app, they will create an endpoint, and they will talk to an engine endpoint, right? And here we have our own authentication mechanism. We don't have much on the quality of service yet, but that's definitely something we will invest in the future. So, and this is our own protocol. And then when we receive the IO on the engine side, we write to NVMe. I mean, it can be NVMe or Fabric. We use SPDK here to access the SSD. But here there is no multi-tenancy issue, right? Multi-tenancy is managed by the engine itself.
Okay. Okay.
Does it answer your question, or you meant something else?
Yes.
Sorry. Yeah.
That really clearly answered the question, because we just move the control plane a little bit upward.
Exactly. And we have an agent running on the compute node that authenticate the app, and we can sign, we authenticate the application locally, then we sign his identity and pack it in the request. And then the engine receives the request, it verify the certificate or it was encrypted, the identity of the process. This is all we can trust who this IO is from, right? And then we apply our own access control entry and list to manage security for multi-tenancy. What we don't have is quality of service. It means that if you have a pool, like in this slide, if here you have an engine with two pool, right? You have a blue pool and the yellow pool. They are on the same engine. So from a security standpoint, they are very isolated. From a space usage standpoint, they are very isolated. But what they are not isolated yet is from a performance standpoint, right? They will still use the same SSD, and they will still use the same socket, CPU and engine that we have. So if one of the project is hammering the storage system, the other one might still be impacted, right? So this is the next step for us, is to look into quality of service over the network for different tenant, and also quality of service to the storage for different tenant.
Sure. So in the slides from Jiafu, you had mentioned about support for HDFS. And so HDFS supports something called a replication as well, because if any node were to go down, you have another copy of the data elsewhere. So how do you deal with the data replication aspects?
So it's totally handed over to DAOS. So DAOS here, so you have the Hadoop connector. So Jiafu work is writing this Hadoop connector between libDAOS and Apache Spark and Hadoop. So here, when you have HDFS, it does its own replication and so on. But here, you don't need any of that, because libDAOS is managing replication and erasure code inside libDAOS across the different engine. The data is either replicated or erasure coded across different DAOS nodes. If one DAOS node goes down, DAOS itself, there will be a collective operation across all the engine that will restore the redundancy of the data on the surviving node, right? So it's totally abstracted and managed by the underlying storage system in this case.
Sure, great. So in the interest of time, let me take one more question. So this is from Vijay Papnai, and his question is that this particular method or solution for DAOs, it's tightly coupled to the application. So
Yes.
is it the general direction for applications to follow, or there are other approaches as well?
Well, so I mean, obviously, I mean, our approach was to say, okay, I mean, we want to support traditional POSIX. So we have POSIX, right? We have POSIX abstraction. You can mount a file system. You can use it as a legacy storage system here. And this is what is represented on the left side. But the intent is that people can migrate smoothly to DAOs by using this POSIX layer. And then on a case-by-case basis, they have different apps that might be using different middleware. And then those can use a middleware that is optimized for those, right? And this is what we do with HDA5, MPIIO, Spark, TensorFlow, and so on. That's really our approach is to do both actually, right? Supporting legacy app without any change. You might not get the best performance, right? But it will work. And you can at least, in my opinion, get the same level of performance that what you get with existing storage system today. And then you spend some time to enable your app with one of those middleware we support, or it already run over a middleware we support. And then they will have better performance and more capability. And then there is this extreme step where you have some institutions that have already specific data model that they port natively on top of those, and their app were already built on top of that. So that has been really our approach. Other approach might just be like, I don't know, we try to standardize on POSIX. We try to do POSIX, or we standardize on S3, right? On our side, we try to do everything at the same time, basically.
Right, right. You should fight you should fight only the battles you can, and then one by one get more apps onto it.
Yep.
All right. So that was a really great talk, Johan and Jiafu. Thank you so much for joining us today.
Thank you for the invite.
Over to you, Amit. Thank you.
Thank you so much, Johan Lombari and Jiafu Zhang, for presenting to us Deos and Optane and scaling AI and big data with Deos and Optane. Thank you again for spending time at the IEEE Data and Storage Symposium Winter Edition. Well, for our last session of this, the IEEE Data and Storage Symposium 2021 Winter Edition, brought to you by IEEE Bangalore Section and Huawei Technology India, we have with us Professor Onur Mutlu, who will be throwing light on the future computing platform, challenges and opportunities. On your screens now, Professor Onur Mutlu.
Hello, can you hear me?
Yes, Professor, we can hear you.
Okay, great. Let me share my video as well. Okay.
Yeah, we can see you too. Hello there.
Hello, how are you?
We're doing great. Thank you so much for making time, sir.
Yeah, thank you. I think it's better to show my office rather than some virtual background over there, right? Yeah. Okay. Let me try to share my video.
Perfect professor's backdrop with a whiteboard and an eraser.
Yeah. When I'm in my office, it looks nice, and I can go to the board and use it as well if needed.
Brilliant. Over to you, sir, whenever you're ready.
Okay, sure. I'm sharing my presentation now. I don't know if you can see it.
We can see the edit mode. If you can just start the presentation.
Okay, sure. Yeah, I also have another computer here just to make sure everything is appearing fine. Okay. Does this look good?
Yes, sir.
Okay, great. Just a second. Let me do something over here so that I can make sure everything looks fine also. Okay. Okay, great. Yeah, thank you very much for inviting me to give this talk. I understand this is the last talk, so I will try to be relatively brief, although I have a lot of material to talk about. So initially, at the beginning of the talk, I will refer people to some other material if they're interested in learning more about this exciting topic. I'm going to be talking about future computing platforms, and I'm going to give you some challenges and opportunities as I see them today that is limiting us in building better platforms. So this is going to be a very, let's say, fundamental talk that will touch to the fundamentals of computing, hopefully, and hopefully people will enjoy it and ask questions about it. But I think the key takeaway from the get-go is we really need to rethink the fundamentals of computing today with the given constraints and with the given workloads that we have and with the trends that we expect to see into the future. And this is an exciting topic, clearly, because it doesn't come every day that we have to think the fundamentals again and again. This happens once in a while, I think. And I think today we have a great opportunity to do that. And if we do that well, I think we can create much more efficient, more robust, more secure, and more safe systems for the future. Let me quickly introduce a little bit of what we do, just so that you can find more information, and also mention people who have contributed to this research. But our goal is to build fundamentally better architectures. We work in computer architecture, hardware, software interaction, systems, bioinformatics, and security. And these are four key current directions that I believe are important to enable us to rethink the fundamentals of computing. I think we need to rethink how we design security, reliability, and safety into our systems, fundamentally robust or trustworthy architectures. I'm going to talk a lot about that today. And I think hopefully if we have time, I will also talk a lot about fundamentally energy efficient architectures. And I think we're not doing well in these two dimensions today. And the second part requires us to be memory centric, data centric. And I believe first part also requires us to be data centric. What I will not have time to talk about is enabling fundamentally low latency and predictable architectures. And I think this is really important, especially low latency decision making in machine learning tasks that are affecting our lives, safety criticality, health criticality, etc. This is really this is going to be more important, but I will not have a lot of time to talk about it. And more specialized architectures for different and very important workloads for our lives, machine learning, genomics, medicine, and health. You can see that these are all actually health critical or safety critical applications. And I think people can empathize with, especially the genomics, medicine, and health aspects today with the COVID-19 pandemic. If we actually had devices that could essentially make the right decisions very quickly, maybe we could have been out of this pandemic relatively quickly, as opposed to potentially humans making decisions and making the wrong decisions. So maybe we need to build a much more intelligent infrastructure going into the future to enable making right decisions quickly into the future. But I think that all of that requires all of these four different directions to be done in a nice way. And hopefully I will give you an overview of the first two directions, and I will mention the other two, but we will not have time to talk about that. Okay. So this brings me to the transformation hierarchy, because if you really want to rethink the fundamentals of computing, you really need to rethink the entire stack, if you will. We have problems and we get them solved by electrons in today's dominant technologies. And computer architecture traditionally has been the interface and the microarchitecture, which is a very narrow view. I will take an expanded view of computing architectures today, because we really need across the stack approaches, all the way from algorithms to devices, and rethink what happens in between so that we can actually get the most efficient and high performance systems, as well as most reliable and secure systems going into the future as well. And this requires us to co-design across the hierarchy, again, algorithms to devices, and specialize as much as possible within the design goals that we would like to achieve. We will talk about goals also. What are the goals of computing, especially today and going into the future? And these are, this is a very busy slide on topics that we work on that are actually examples of this cross-layer approach, algorithms to devices. I will not have time to talk about everything over here, but I will give you some examples. And you can find information in the later slides that I will show you soon. So I will acknowledge my group before I continue, because they're the people who have actually contributed to everything that I'm going to talk about. And we actually release some newsletters. If you're interested in learning more about our research, you can find them online. We strongly believe that teaching and education and research are actually very coupled with each other. They drive each other. And as a result, we actually put a lot of lectures online. If people are interested in learning more about what I'm going to discuss today, we have both undergraduate as well as graduate advanced lectures online. And we're actually live streaming them online. If people are interested in attending, we'd be happy to have you in the course, regardless of wherever you are in the world. You can find information about these lectures. Currently, I'm teaching the Advanced Computer Architecture course, and it's live streamed, and we have nice attendance across the world, but we're always looking for more people to join and share the knowledge. We also have seminar courses. You can find them online. They're also live streamed, and hands-on projects and seminar courses, which I'm going to mention. We also put out a lot of seminars. If people are interested in topics, expanded topics on what I'm talking about, they can find information about these seminars. We will keep pushing into the future. And I'm a strong believer in open sourcing everything, including the software and the hardware we build. And you can find these open source tools that I will talk about some of them today, and you can find them on our GitHub, as you can see. Ramulator is an example that is used in, for example, memory research by industry and academia. MQSIM, which is not shown here, is another example that's used in storage research, for example, again, in industry and academia. And I will mention several others today. And if people are interested in learning more about the research that goes on in my group, an expanded view, this is a short talk that I delivered on architectural mentoring workshop at ISCA this year. And I'd be happy to get any feedback if people are interested in that. And we have a lot of interviews posted online on computing futures. And everything I will mention is available as papers, talks, and artifacts online on these websites, and you can find them, note them. I'm happy to make these slides available. You can find them online after this talk. I will put them online and also send it to the organizers. Okay, now let's jump into the main subject of the lecture, future computing platforms, challenges and opportunities. And I will start this with a very basic question. Why do we do computing? And my answer to this is to solve problems. Basically, if we don't want to solve problems, there's no reason to do computing. And rewording this answer, we would like to gain insight into solving problems. And this is Hamming's answer, Richard Hamming, in this beautiful book. He mentioned that. And extending the answer, we would like to enable a better life and future for us humans and other species in the world and in the universe, right? Then the question becomes, of course, how do we solve problems to enable all of those good things? And the answer today we give in our computers is by orchestrating electrons. And today's dominant technologies, we essentially orchestrate electrons to solve problems. Of course, how do you translate our problems to electrons? That's why we have the transformation hierarchy that I showed you, because we cannot speak electron language. Electrons cannot speak our language. So we have to communicate with them somehow. And we create some abstraction layers to make our communication easier with electrons. And clearly there are courses in every level, multiple courses in every level in a university that you can take. But I'm not going to go over that in detail. But I will mention what I said earlier. We would like to really break the barriers between these abstraction layers. Ideally, of course, we would like to speak the electron language, but I don't know how we will achieve that. So computer architecture is the science and art of designing computing platforms, hardware, interfaces, system software, and the programming model to achieve a set of design goals. For example, we would like to get the highest performance on Earth on workloads XYZ. This is a supercomputer-like design goal. Performance is the most important design goal. Energy may be close second, but cost is less important. Another design goal could be longest battery life at a form factor that fits in your pocket with cost less than some amount. This is like a mobile system, like a cell phone today. Another design goal could be best average performance across all known workloads at the best performance cost ratio. This is like a general purpose system. And I can come up with other design goals that may be very specific, right? Accelerate machine learning training and be the fastest at it, right? That could be another design goal. And now you have a machine learning accelerator at hand. Make genomics real time so that doctors can make decisions within 1 minute after analyzing someone's genome in terms of a life-critical situation as to what kind of drug they should administer to the patient, right? Now you have another specialized system for genome analysis, a decision maker, essentially, that should be extremely safety critical, extremely robust in a sense. So basically, all of these are different kinds of computer architectures and computing platforms. But in the end, designing a supercomputer is different from designing a smartphone or an accelerator. But many fundamental principles are similar. And let me just show you some of these platforms that we have today. This is another thing that I didn't mention, but this has important implications in terms of thermals, battery life, security, etc. Another platform that we would like to enable, Mr. Bean is riding his self-driving car, if you will, over here, and he trusts us a lot, but we are not there yet in our self-driving cars. We cannot place this sort of trust in our self-driving cars today. And that's why I'm going to mention a lot about security today. Security, safety, reliability, trustworthiness, and robustness in general is going to be a key thing that we have to solve in our systems in a fundamental way so that we can actually enable this sort of systems that we're going to rely all our lives on. This is another self-driving car, a more realistic one, if you will, even though it's an older one. This is the computing power that needs to go into a self-driving car to make it work. Another platform that looks like this is it's a genome analysis platform. Today, it's not very capable, but the form factors are there. It takes a long time to actually analyze a genome, even though it has a form factor, it's portable like this. Can we make it much faster? This is a data center, another platform. This is a supercomputer. It was the fastest supercomputer on Earth from China for some time. I don't know the ranking today, but clearly a supercomputer and data center, even though they may look similar, they're designed for completely different goals. This is a machine learning accelerator, Google's TensorFlow engine, not TensorFlow, sorry, TPU, that executes TensorFlow in the end. But it's a machine learning accelerator, a systolic array, and this is a version 4 of it. This is Tesla's self-driving car. You can see there are some fundamental reliability principle applied here, but maybe it's not robust enough yet. And this is a wafer scale engine. This is the first version, and this is the second version, designed for machine learning training and as well as inference tasks. And you can see that it's the size of a whole wafer, and it's the biggest chip that we have on Earth today, as far as we know. And you can see that this is designed to specialized for machine learning training in particular. And that's what you need to have so that you minimize the data movement in systems. But this is not the only idea, of course, to minimize data movement. We're going to talk about minimize data movement and orchestrate computation and do a lot of computation in parallel in a chip like this. And but this I believe is a step in a good direction that pushes the boundaries of computing platforms today. And clearly, there are many other machine learning, artificial intelligence chips that I don't have time to talk about. You can see that there's a growing area. The landscape in 2021 looks much crowded compared to landscape in 2019. And I expect 2025 will be even more crowded. So people will be building these engines. This is another example. This is a real example of a processing in memory engine. This is made by the UpMem company. And basically what they have done is they have put processing elements inside the DRAM chip so that you can do processing without moving the data to the processor or somewhere else or another accelerator. And this is relatively general purpose. We analyze it in our works. And these are DIMMs you can buy actually. This is the system that we analyzed, and you can read our papers. I hopefully will have time to mention this a little bit, but you can also find these live seminars and talks that we deliver on this topic. I think this is a fascinating topic because this is again a step in my opinion, the right direction to minimize the data movement in computing systems and to make computing much more efficient by dealing with data. This is another example. I don't have a picture, unfortunately. I should really embellish these slides with some pictures of FPGA-based platforms that can do near memory acceleration. Today, we have FPGAs with high bandwidth memories, and we can actually significantly accelerate genomics and weather modeling, climate modeling applications. And you can find some information on this particular paper here. And even big companies are actually looking into, let's say, more revolutionary ideas than they have been in the past. A big company like Samsung, for example, which has been extremely traditional in its approach to computing, finally incorporated some processing in memory power, let's say, inside their chips so that they can accelerate machine learning applications. And they're actually interested in making it more general purpose as well. You can see that these machine learning accelerators on the memory side can do multiply and accumulates relatively fast. And I believe they will also be helpful with genome sequencing going into the future. And genome sequencing is something I will briefly also talk about, but we need a lot of computational power in genome sequencing. We have these portable devices, but we need to actually do much more processing near the sensor, near the sequencing device, inside the sequencing device, inside the memories, inside the storage. And we have some works in this area that talk about processing both inside memory as well as inside storage to minimize the overheads in dealing with large amounts of genomic data so that we can achieve the goal that I mentioned earlier. Can we actually enable making very quick decisions so that people can actually do these decisions nicely and privately with their doctors? Okay, so hopefully I've given you some examples of this expanded view of computer architecture. Everything that I showed you, especially the specialized ones going into the future, are actually breaking the barriers between algorithms and devices. You really need to rethink the entire stack to look into a machine that's of capability of Cerebrus's wafer scale engine, UpMem DRAM system, for example, as well as Samsung's memory that can do computation. Okay, so those are some examples of computing platforms. And I believe with creativity, people will come up with even bigger computing platforms that are going to get rid of the inefficiency that we have and hopefully enable secure systems. But let's also talk about what kind of future do we want so that we can guide the development of those future platforms that are going to be everywhere with us in our lives. And I will start with security, reliability, and safety, because if you look at systems that we design, infrastructure that we design, bridges are an example of infrastructure that we design as humans. We have been designing bridges for thousands of years, and they're critical because if they don't function well, if you get a bit flip on bridges, this is what happens. Basically, it's a safety, reliability, and security problem. It's a trustworthiness problem, robustness problem in the end. And we don't want this happening in our bridges. Bridges are very small, very few compared to the computing platforms that we're having in the world today. We're going to have billions and billions of computing platforms, some of which are going to be safety critical, many of which are going to be some sort of reliability critical, but some of which are going to be extremely safety critical for us. So we need to ensure that our platforms are actually even more reliable than bridges going into the future. And I mentioned this a lot in my undergraduate classes, for example. This is another bridge example, right? These folks who are constructing New York are sitting on this bridge or rod, and they're very happy right now. But if there's a serious bit flip on this, they will not be happy in the next moment, right? So security is really about preventing unforeseen consequences taken in a broad sense. And I believe we should really be thinking about this rigorous approach to prevent unforeseen consequences that we cannot even foresee today. Can we actually design systems that are adaptable, evolving, and reconfigurable enough such that they can actually enable us to fix problems that we find in the field going into the future? I'm going to give you an example of that with Rowhammer, for example, because that's a very serious example of a real system, real security issue that's affecting our lives today. Okay, and I think I've already mentioned that we will increasingly have platforms that we have to rely on, and can we make them happen? So that's why reliability, security, and safety is an important goal for the future. The next goal, I think, is can we enable a sustainable and efficient future, or do we want to live in a world that we cannot even breathe in going into the future? I would argue that we want sustainability and energy efficiency, and I will not spend a lot of time on this because hopefully this is obvious, and we're having a lot of problems with climate today. And I think computing can enable solutions to it, but if you don't do the right things, computing can actually be a bad contributor to those climate problems. And I think today computing is looking to be a bad contributor to those climate problems because unfortunately the amount of energy spent on training even the training some of the large models that we have, for example, consumes a lot of energy, a lot of computational power, and it's not really overcoming the downsides. The benefits are not really overcoming the downsides at this point. So I believe by taking a fundamental approach to computing, we can enable much more sustainable energy efficient systems. And we have a lot of difficult problems. We have clearly climate, a huge problem in front of us, congestion, a huge problem, intelligence, figuring out what we really mean by intelligence and what's really happening in intelligence. Can we actually design these intelligence systems much better than what we have today? And public health clearly is an important problem. There are many, many health problems actually, medical problems. And I can keep going on and on. Genome analysis is an important problem clearly. Today we can actually generate a lot of genomic data that we can process. And we need to really have high performance engines to actually process the data in a reliable fashion if you want to make sense of it and if you want to really enable it going into the future. And this is one example paper that we have written. I'd recommend people to look at if they're interested in it because it really combines two different fields, genomics, computer architecture, and VLSI design to actually enable a full system that can accelerate genome analysis. And we actually designed specialized accelerators as well. So if people are interested, they can read some of these papers that I mentioned over here. And in the future, I think we will need increasingly specialized systems for doing this sort of analysis. And I believe for other medical analysis as well. Genome analysis is really important because that can enable many, many different directions in both understanding the fundamentals of life as well as in health and public health, etc. But there are other medical issues for which we need some more specialized devices as well. If you're interested in this more, we deliver some lectures and you can find some interesting algorithmic issues as well as architecture issues in these lectures if you watch them, and we make them available in our computer architecture lectures as well. So I think this was a long discussion that we really need high performance. We cannot give up high performance because we have increasingly tougher problems and we have increasingly more problems. We've solved a lot of problems and we're trying to solve even more, but solving problems enables new problems for us to solve also as humanity. And I think we cannot give up high performance in the design of our computing systems to solve these problems. That's why this drive has to continue. And I think the last point I would like to make is everything is becoming more personalized today. Sorry about that. Everything is becoming more personalized today. We have personalized medicine, comparative genomics, which needs to be personalized also. We cannot leak out private data when we're comparing genomes of different humans, for example. And there are technologies that are enabling this, these portable technologies that you can see over here. And I've given you examples of it. That's genomics. In robotics also, I think we need actually this sort of personalization as well. In architectures as well. Basically, we're going to a direction of significant personalization and privacy so that we can make the best of the computing devices that we have. And this is happening in every aspect of life, maybe slower than one would expect. But I think this is going to happen a lot faster going into the future. And I think how to enable that in a private manner, this personalization in a private manner is going to be important, because personalization can also enable energy efficiency and sustainability, because not every single person is doing the same thing with a computer. Designing a computer to be exactly the same way for every single person is inefficient to begin with. So over time, personalization, dynamic adaptation, evolution of the computing devices to become more personal and private is going to be important. Okay, so hopefully that was a high-level overview, and I will go into a little bit more detail right now on questioning what limits us in designing the best computing architectures for the future. And I will try to provide directions for fundamentally better designs and architectures. And I will mainly advocate principled approaches. We really need to be principled in how we design systems going into the future, because I believe today we're violating some really fundamental principles to achieve the goals that we would like to achieve. And I will mention that applications are increasingly demanding. As long as people dream and be creative, applications will keep coming. And as applications push boundaries, computing platforms will become increasingly strained in all of their limits. Energy efficiency, reliability, predictability, security, safety, basically whatever limits and metrics you can imagine, we're straining our computing platforms today. and they're going to be strained even more into the future. So I will share my key realization right now. Maybe it's not going to come as a surprise based on what I said earlier, but modern systems today are bottlenecked by data storage and movement. And that's true for almost all applications that scale to large amounts of data. So, there are certainly the other applications that exist that do not require large amounts of data, but I will argue that that's an easier problem. The problem that we're having today is the problem of data storage and movement, and we need to solve this problem so that we can enable this future that we have discussed. So my focus is going to be on data storage systems. I will broadly call it memory, but memory clearly consists of memory that's on the chip, processor chip, main memory, and storage. So this is all memory for me. Clearly, there's some distinction between memory and storage, etc., but maybe that distinction will be blurring with emerging memory technologies that make the properties of memory devices and storage devices similar to each other going into the future as well. So I will mainly focus on main memory, but I think everything I will discuss is really applicable to all of the memories that we design in our systems, wherever they may be. And memory is really a critical component of all computing systems. Whatever you design, you have to have some sort of main memory. And main memory systems are scale in many dimensions: size, technology, efficiency, cost, and management algorithms to maintain the performance growth and the technology scaling benefits that we really want, as we discussed earlier. So you can attach these memory devices to processors, FPGAs, GPUs, machine learning accelerators, a heterogeneous combination of them, which we're doing right now, and the wafer scale engines. And you will see that these engines are all bottlenecked by main memory in the end. So basically, computing today is bottlenecked by data, rephrased another way. And data is really key for these applications, the future basically. Important workloads are all data intensive. They require rapid and efficient processing of large amounts of data, and we're doing increasingly sophisticated things on data. And data on top of this is increasing. We can generate much more data than we can process. So we're demanding more and more from our computing infrastructure. And memory is becoming less and less effective the way we design it today. Basically, if you look at these applications, they're all bottlenecked by some sort of memory. So memory is a bottleneck. If you look at these mobile applications that are critically important, we're exercising some of them or their counterparts. WebEx is, for example, doing video playback and capture. We're doing internet communication through some sort of web browsing right now, and there are many AI algorithms in place that are happening. Who knows what they are and who's using them? But clearly, memory is critical for performance of these applications. And genome analysis, I mentioned this today, scientific discovery and medical advances are limited by how fast and efficiently we can process data that's in memory. And I've given you already these pictures, so I will mention just that memory is a bottleneck as we show in these papers, for example. This is a paper from 3 years ago, but we have several papers that are more recent as well that show that both memory and storage are bottlenecks. Okay, so memory is also critical for energy. This is a study that we did with Google for about 3 years ago again, and we found out that more than 60% of the entire system energy on a mobile device is spent on data movement across the memory hierarchy. This is because processor is here, memory is here, they're far away from each other, and data has to move from memory to processor back and forth, back and forth, back and forth, back and forth, so that we can keep doing the computation. And this is extremely inefficient. And this is mainly looking at the memory bottleneck, but storage is also there, basically, storage bottleneck. Some applications are very much storage bottlenecked today. Okay, memory is also critical for reliability. This is data that we gathered together with Facebook in all of their servers that they employ worldwide. It's a lot of servers. This is actually very statistically significant data. And you see this picture, basically. As the chip density, the memory chip density that's employed in a server increases, the server failure rate also increases. Clearly, this is a correlational study, so you cannot say anything about causation. But there's a good reason why this could happen, because as you actually put more cells in a denser area, these cells are becoming much less reliable because cells are smaller. Cells are also interacting with each other with a lot of noisy ways. As a result, cells as well as their cell-to-cell interaction is becoming fundamentally noisy. As a result, we're having increasing error rates in memory. And if you're interested, there's a lot of analysis that we do in our works, example of this work. So let me revert my realization. Modern systems today are bottlenecked by memory in general. And how do we actually solve that? And if you're interested in this, a little bit of history of this, we have an early overview paper that talks about memory technology scaling and how to potentially make strides in solving them. I would recommend people to look at it if they're interested in some history as well as potential ideas going into the future. And it's always good to read these relatively old papers. I'm not suggesting that this is really old. I'm going to give you examples of really old papers soon. But I think DRAM scaling is becoming much harder today, and we should really think about new systems architecture, algorithms through devices perspective to actually solve these problems. Now that brings me to these 4 key issues in future platforms that I'm going to mention today. As I said, we're going to start with security, reliability, and safety, and then we're going to move on to energy efficiency, and we will not have time for the other ones, but these are actually related to each other. All of these are actually related to each other. Let's start with the first one. I will start with the first one. I will start with a high-level perspective on this. This is Abraham Maslow. He's a very famous American psychologist who actually had a lot of impact on psychology, economics, politics. He's very well known for this Maslow's hierarchy of needs, which says essentially that our physiological and safety needs are much more important than everything else. If these needs are not satisfied, then we cannot even think about highest forms of abstract art, or a lot of the things that I've already talked about, basically. How do we actually enable much more higher performance and sustainable systems? We should really satisfy our safety and security first. And that's true for computing systems as well. And I've already given you examples of this bridge. This is a real bridge, that the Tacoma Narrows Bridge, that bit flipped, let's say, in 1940, and it caused a safety, security, and reliability problem. And we need to be actually preventing unforeseen consequences, in my opinion, to enable trustworthy, fundamentally trustworthy and robust systems. Unfortunately, we do not seem to have design principles for guaranteeing reliability and security, especially at the hardware level. But this is true for the system and the software level as well. We really need to have a cross-stack approach to security, algorithms to devices. How do we guarantee security with fundamental design principles? I'm going to motivate this with multiple examples. Clearly, these errors cause a security problem, reliability problem, safety problem. And this is because of the DRAM scaling problem. I'm going to pick on DRAM, but that's true for many, many technologies also. If you look at DRAM, dynamic random access memory, it stores charge in a capacitor, and this capacitor must be large enough for reliable sensing. And there are sensing structures around it, access transistor and sense amplifiers, etc. They need to be large enough for long data retention time. As you reduce the size of the cell, it becomes much more vulnerable. And this is very fundamental. It doesn't matter what kind of cell you have, memory cell you have. You could have a flash cell over here. You could have a phase change memory cell, STT-MRAM cell. You could have an RRAM cell. As you reduce the size of it, the memory becomes more vulnerable to reliability and noise issues. And we've been studying these reliability and noise issues for a while now. We built a lot of FPGA-based infrastructures to test DRAM, as well as flash memories. I will briefly mention flash memories later on. And we actually did a lot of studies. We've open sourced this infrastructure. It's called the softMC infrastructure. You can actually find a newer version of it called PyDRAM as well. Newer version that's tailored for processing in memory. And we're happy to support it. So we actually support industry and academia in their research, and multiple papers built new works on it as well. While we were doing a lot of these reliability and safety studies, we found out that together with Intel, one can predictably induce errors in most DRAM memory chips that are out in the field. And this is called the DRAM row hammer problem. Basically, it's a simple hardware failure mechanism that can create a widespread security vulnerability today. And people are writing articles that sound like this, basically. Forget software, now hackers are exploiting physics. Why is that the case? Basically, this is really a physical phenomenon. Basically, if you want to access memory, you need to apply high voltage to the word line that contains the cells that you want to access. You need to open the row. And if you want to access some other cells, you need to apply low voltage to this word line, if you will. Basically, this is called a activate and precharge pair in DRAM. Now, if you keep doing this repeatedly, high voltage, low voltage, high voltage, low voltage, high voltage, low voltage, activate, precharge, activate, precharge, activate, precharge, enough times before the cells get refreshed, it turns out physically adjacent cells that are vulnerable in totally unrelated locations in memory that are just physically adjacent get bit flips. Basically, you corrupt data in locations that you're not even supposed to touch. This could be belonging to some other application, the operating system. It could be belonging to a neural network that is safety critical. It could be belonging to some patient data that's really important, and a bit flips, and now you actually have a completely different diagnosis. Basically, you don't want to have these such bit flips. So we call this the hammer job, and call this the victim rows. And basically, we showed that more than 80% of the chips that are manufactured by the 3 major DRAM manufacturers are vulnerable to this effect. And this is a technology scaling problem. It's happened to all of the manufacturers. And basically, this issue was not a problem in real DRAM chips within reasonable refresh intervals until 2010. First appearance in 2010. And over time, this issue became much worse because you could actually put many activates before the cells get refreshed. If the cells get refreshed much more frequently, then you could solve this problem because you could actually enable refreshing of memory, replenishing of data before you could actually deplete charge from the cells because of this hammering caused induced charge leakage. I'm going through this relatively quickly. I'm assuming some people are familiar with it, but you can read the papers. Clearly, there's a physical effect. This is because cells are too close to each other, And whatever action you're doing in one row of cells is affecting the other row of cells. But it should not, because these rows have nothing to do with each other. And someone can exploit this at the high level, at the user level program. One can write a user level program that looks like this. You could actually optimize it. This is on our GitHub. Later, Google improved this program. They took our program and they improved it. They made it much better. And there are many, many other versions of the program that you can find today that are even better improved. But fundamentally, what the program does, it bypasses the caches, bypasses the row buffers, and basically ping-pongs access to 2 rows in DRAM. And if the chip is vulnerable, hopefully you will get bit flips. And we showed that essentially Intel and AMD systems at the times are vulnerable, but there's nothing specific about Intel and AMD. As long as you can access your memory fast enough, you can actually induce these errors. And what is worse is we said that this is actually not good for reliability and security. Someone can hijack your computer. This should not happen, basically. And access to one memory address should not have unintended side effects on data stored in other addresses. Later, Google Project Zero folks read our paper, and they basically showed essentially that you could actually take over an entire system. Even though you're at a user level, you could actually take over the entire Linux kernel. And I'm not going to go through how they did it. This is beautiful security engineering. And this sort of research needs to happen based on the fundamental bit flip phenomenon. Someone needs to take that bit flip phenomenon and show that you could actually enable a security attack that's extremely serious, as these Google folks did. I'd refer you to their Black Hat presentation, as well as the blog post that I mentioned over here on the slides. And clearly, this became well known as the rowhammer phenomenon. And people actually mentioned this, as you can see. It's like breaking into an apartment by repeatedly slamming a neighbor's door until the vibrations of the door you were after. So people actually look at this in interesting ways as well. And many people built a lot of attacks. I'm not going to go through every single one of them. They don't have time. But you can see that people were able to take over someone's cell phone deterministically. People were able to do these attacks much faster with GPUs. People could do it on a remote machine through the RDMA, Remote Direct Memory Access Interface. People could actually leak out private data, even if they could not somehow get access to the computer in full. And recently, people showed that deep neural networks that could make safety-critical decisions are actually vulnerable to rowhammer bit flips. And if your accelerator actually gets bit flips, an otherwise reasonably good accelerator that is more than 90% accurate can actually go down to 10% accuracy. So it can have actually not a useless accelerator for machine learning. If you're doing pedestrian detection, for example, your safety criticality reduces to very low levels. Essentially, this sort of bit flip has to be prevented, and otherwise we'll have problems in all of our computing platforms going into the future. And there's a lot more research I'm going to skip over here. Clearly, there are other security implications. Maybe this is a solution also. Of course, it's a joke. And solutions today are unfortunately a bit ad hoc. Basically, increasing the refresh rate is clearly one thing we can do for chips that are in the field, but this is not what we want. We actually want to get rid of refresh as much as possible because it's a performance, energy, and quality of service problem. So if you're limited to solving the problem with increasing the refresh rate, it's actually not good. We actually showed that you need to increase the refresh rate to unreasonable levels, prohibitively bad levels for performance and energy efficiency if you want to actually be completely secure. So we need to really design fundamentally secure computing architectures and predict and prevent such safety issues going into the future. So I will argue for principled designs. One example in the right direction is our solution is probabilistic adjacent row activation. Basically, you change the memory controller and cooperate with the DRAM chip. Based on this cooperation, after closing a row with very low probability, you activate adjacent rows. And this gives you a very good reliability guarantee. And you can actually increase your reliability guarantee by adjusting the value of that probability. And you can see that this is stateless, low power, low cost, and low complexity. And it's an effective and low overhead solution. But we actually come up with better solutions that I will mention in the future. I'm going to skip the slide, but basically the best way to implement this is by modifying the memory controller as well as the DRAM chip so that they can cooperate with each other. And this is employed in some of earlier memory controllers designed by Intel. You can actually choose your rowhammer solution. You can see that you can increase the refresh rate, or you can have some rowhammer activation probability that you can adjust in the BIOS. And this is a paper that introduced the rowhammer problem to the field. And we've written a lot of papers that I'm not going to discuss more. I will mention some of the more recent research on this topic, because there's a lot that happened in 2020 where we showed that actually this problem is getting much worse. Newer DRAM chips are much more vulnerable, and existing mitigation mechanisms are not effective. DRAM manufacturers put some solutions into the DRAM chips that they claim that are completely secure, but we showed that you can actually bypass these solutions with some clever reverse engineering techniques, and basically you're back to square one. Those solutions are not effective. And rowhammer is still an open problem, and security by obscurity as it's being employed in the field, unfortunately, is not a good solution. And we actually did some studies with Microsoft, for example, to answer the question, can we actually declare a DRAM chip rowhammer free somehow with enough testing? And it turns out we cannot do that. It's actually a tough problem. It's not an easy problem. And there are clearly sessions at top conferences. This is a top security conference, for example. There was a session on rowhammer with multiple papers, and other security conferences, as well as architecture conferences, as well as digital design conferences are having rowhammer sessions as well. So this is one of the latest solutions, the block hammer solution. I believe this actually has provable security guarantees, and it's also another step in the right direction, but I do not have time to cover it. And we also have 2 key rowhammer papers that provide a lot more insight into the problems of rowhammer in micro that appeared essentially last month or 2 months ago. And I would suggest people take a look at it. But I believe there's more to come, basically, not just in rowhammer, but hardware security vulnerabilities. And we need to really take a fundamental approach to solving them as opposed to patching them. Because as we keep patching them, people who want to exploit them will be also doing things to ensure that those patches are not valid, let's say. And if you're interested in more in this topic, we have a lot of lectures, and I'm happy to talk about it as well. Okay, so let me actually take a step back. This is an example. This is just one example of memory reliability issues. DRAM is becoming less reliable and more vulnerable due to other difficulties. There may be other errors slipping into the field as well. Rowhammer is example, retention errors, read errors, write errors, etc. Who knows what else? In some cases, when our computers are not functional, maybe it's because of memory errors, and it's hard to diagnose them. And these can also pose security vulnerabilities. And all memory technologies are vulnerable. DRAM, flash memory, emerging technologies. As I said, fundamental issue is that as you reduce the size of the cell, it becomes more vulnerable. How do we actually protect ourselves when this is the case? I will give you a blueprint of what we can potentially do. I think we need to understand first. We want to develop methodologies for failure modeling and discovery. We want to model and predict based on real device data as well as simulations. And we want to architect. We want to have principled co-architecting of system and memory together. Not just say, this is the problem of memory manufacture, or this is the problem of system manufacture. We want people working together to solve these difficult issues. And this requires good partitioning of duties across the stack, as well as good interfaces. And finally, we need to be very careful and diligent in our design and test. We want to have principled design, automation, and testing methods, online testing methods, so that we keep basically trying to find out what problems are happening in the field with our memories as well as data. Because any vulnerability like this is not good for security. Okay, if it may not be a security problem, it's not good for data corruption and reliability issues, because your data may be not good, right? As a result, you may have a bad decision in a life-critical situation. So I believe this is my 3-step methodology to keep memory and in general systems secure. Of course, I don't have the answers to exactly everything yet. And hopefully some people who are watching this talk may be inspired to actually come up with some solutions in these different directions. And that's why we've been building a lot of understanding of DRAM. We've been building a lot of understanding of flash memory. This is our flash infrastructure. And if you're interested in this, we've been writing a lot of papers on this. This is a summary paper that was published in Proceedings of the IEEE that talks about a lot of issues in state-of-the-art solid-state drives. And we also released a lot of lectures on flash memory and SSDs. Even though that's not the topic of this particular lecture, I would encourage people to take a look at these courses and lectures. So that brings me to the end of the first big part, let's say, fundamentally secure, reliable, and safe computing architectures. How do we enable them? And I think from the memory perspective, we need intelligent controllers that can patch, detect, and also predict these failures and avoid them. Now, let me quickly jump into the energy efficiency issues. We want fundamentally energy efficient architectures, and they need to be memory centric. And let me deconstruct what I showed you earlier over here. Basically, this is Maslow again. And even though he said security and safety are important, perhaps energy is even more important, because if you don't have energy to live, maybe you don't really care about your security and safety. And I've already shown you this picture. We want a sustainable, energy efficient world, but we cannot give up high performance as well. And the problem today is data access is the major performance energy bottleneck in our systems. It's causing a lot of energy inefficiency and performance loss. And unfortunately, we're not handling data access really well. Data is moving all around in our systems. It's extremely costly in terms of energy. We're wasting a lot of energy. And we're trying to overcome that energy waste by building even more complex systems, complex cache hierarchies, complex storage hierarchies, complex processors, complex accelerators that can overcome and tolerate these latencies, multi-threading, out-of-order execution, prefetching mechanisms. All of these are in place to actually overcome the data access bottleneck. They're causing even more energy waste. And they're causing performance loss because when they don't work or when they don't work perfectly, they actually are there to increase our complexity and increase the power. So I would argue that we need to solve the problem. We need to get out of this vicious cycle of data access, complicating our systems and increasing the energy. And we need to identify the problem. Processing of data is performed far away from the data today. And if you look at computing system, it consists of three fundamental components: computation, communication, storage, and memory. And we've heavily optimized the computing unit for decades and decades and decades. Basically, we have a processor-centric design paradigm. As a result, data storage units and communication units are essentially dumb. They cannot process the data. And as a result, we have limited choice. Data moves all around the system. So this is by design, basically. Yet we know that this design is not good. This is Dick Seitz, who was a designer of a chief architect of alpha processors, which were the fastest processors of their time by Digital Equipment Corporation in 1990s. He basically said that we designed this processor to finish 4 instructions every cycle. It's finishing one instruction every 4.5 cycles. Basically, it's operating at 1/18th of its peak processing capability. Why? It's waiting for memory. And he basically finishes this one-page article, which I would suggest everyone to read. I expect that over the coming decade, memory subsystem design will be the only important design issue for microprocessors. And basically, this is data from my PhD thesis about 10 years later. We show essentially the same thing together with Intel. Most of the time, the processor is waiting for data. And that's the paper that we wrote. If you're interested, you can take a look at it. That's the first paper that I wrote in my PhD, if people are interested. And fast forward about 10 years later, Google wrote this paper on their data center workloads. And this is a beautiful paper as well. And they basically show that essentially the same thing. Most of the time, the processor is waiting for data to come back from memory. A very small fraction of the time, 10 to 20%, is doing useful work, if you will. And you can read the paper for more detail. Basically, we are at the peril of a processor-centric design. We have grossly imbalanced systems. Processing is done only in one place, processor and the accelerators. Everything else just stores and moves data. As a result, data moves a lot. This is energy inefficient, low performance, and complex. And we complicate our processors and accelerators, as well as our software, to tolerate data access from memory. And this leads to complex hierarchies, mechanisms, hardware, and software. And it's energy inefficient, low performance, and complex. I would argue that we need to get out of this mindset because this processor-centric design requires us to dedicate most of our system to storing and moving data. If you look at, even though we are processor-centric, more than 95% of the real estate of a single node is dedicated to caches, memory, storage, interconnects. Even then, the system is still bottlenecked by memory. We're dedicating most of our resources overwhelmingly for memory, yet we're still bottlenecked by memory. So this should give a signal for us. Okay, let's look at the system side. System side, I've already mentioned this. Energy consumption is becoming increasingly key limiter in systems, and data moment energy dominates compute. Let's take a look at that as an example. These are old numbers, but the trends remain the same. An arithmetic operation is very cheap in terms of energy efficiency, and memory access is very expensive. And the difference in the expensiveness is 2 to 3 orders of magnitude. Does it really make sense to move the data to the processor so that we can actually do a very simple energy efficient operation? We're expending 2 to 3 orders of magnitude energy many, many times to actually do a very simple energy simple operation. I think we really need to shift our mindset to think about the energy costs of our operation, given that we're very limited by energy and power going into the future. What do we do to minimize the data movement that's costing us a lot of energy? Okay, I'm going to skip this because there are many, many papers that actually show similar results. And this is the reason why more than 60% of the total system energy is spent on data movement in mobile devices, as we showed with Google. We do not want to move data, I would argue. We need a paradigm shift to enable computation with minimal data movement. We need to compute where it makes sense, where data resides, not only in one place, but we need to enable collective intelligence, if you will, computation capability in all of our devices, storage, communication, memory, even tapes. We would like to enable computation capability. Wherever data is processed, generated as well, sensors, for example. And genomics is a great example of the sensors. And we want to make computing architectures more data-centric as opposed to processor-centric. And this brings us to processing inside memory, but you can actually generalize this to processing inside storage, communication, caches. I will give you examples from processing inside memory. And if you look at a system with memory, today, main memory is very interesting because a lot of applications are designed to fit inside memory. There's main memory databases, main memory graph processing engines, main memory media processing engines, main memory machine learning engines. And we want to actually ask questions to memory. Memory, can you do these operations for me? Can you do this training by yourself and give me the trained model, for example, in machine learning? And the memory provides the results back to where those results need to be communicated. Clearly, we're not there yet, but we have many questions. How do you design the memory and the controllers, the processor chip in memory units, the communication interfaces in software and hardware, system software compilers and languages, and algorithms and theoretical foundations of memory? And this is an example of what I mentioned earlier. We really need to rethink the entire stack, co-design across the algorithms and devices to enable a new computing paradigm like this. But we can start step by step. But in the end, I think we will need to re-examine the fundamentals of computing, like theoretical foundations. So if people have taken computing complexity, algorithmic complexity courses here, they probably counted operations. They basically looked at big O, big theta notations, which essentially represent the complexity of algorithms with operation count. But I would argue that that's not the really important part today. That, of course, plays a role. But what about memory? We're missing a huge data part even in the fundamental theory of our computing. How do we incorporate data and data movement and data access and the amount of data to the theoretical foundations of computing? Hopefully that's a food for thought for those of you who are theoretically inclined to solve this problem. And if you're interested in this, we have a lot of review on processing in memory, and this is one example paper that we wrote recently that covers a lot of the recent work as well as history of processing in memory. And I would suggest you take a look at that. Now, I will also argue that we need to think differently from the past approaches. Processing in memory is an old idea. All earliest papers are in late 1960s, more than 60 years almost. And even though these papers are quite good, we really need to think differently. And I would argue that there are two different ways of thinking about processing in memory today, two approaches. One is processing using memory, and this is fundamentally different from what we design our computers today. The second is processing near memory. This is actually closer to what we do today. Processing using memory says we want to use the analog operational principles of memory so that we can do computation using those analog operational principles so that we can gain significant performance and energy without modifying the memory a lot. Processing near memory says today memory is here, processor is here. Increasingly, we move the processors closer and closer and closer and closer in memory such that they're merged with each other in some way. Of course, this could be enabled by new technologies like 3D stacking as well. But processing near memory is fundamentally a processor like we know today, or accelerator like we know today, and getting it closer and closer to memory. So fundamentally, processing near memory is closer to what we do today, but it's equally important. And ideally, I think we would have both of these approaches used in our systems. Now, if you have time, let me go over quickly what these two approaches are. And processing using memory is actually enabled by many, many technologies. It could be done in conventional technologies as well as emerging technologies. Processing near memory, also true, but it's enabled by logic getting closer to memory, essentially. Let me give you some quick results, basically, of how to do this. So copy initialization, for example, we do a lot of copy initialization in our systems. And Google actually showed that more than 5% of cycles in their systems is actually spent on only these two function calls to do data copy and initialization. I find this fascinating. Only two function calls responsible for 1/20th of all of our execution cycles in the Google data center. How do we do copy today? Basically, to copy data from one memory location to another memory location, we have to go through the processor. We have to bring the page to the processor, we have to do the copy, and we have to write back to the destination page. This is really a lot of waste. High latency, high bandwidth, cache pollution, and unwanted data movement. For a 4 kilobyte page copy, it takes 1,000 nanoseconds and 3.6 microjoules. If you want to do a 1 megabyte copy or 1 gigabyte copy, or if you want to initialize a 1 terabyte database, for example, this is even more costly. So let's think data-centric. If we think data-centric, we don't do this. We don't bring the data into the processor because there's no reason to bring the data into the processor unless we're thinking processor-centric. This is really a mindset issue, I would argue. If we're data-centric, we do the processing where data resides, inside the memory, as much as possible, of course, because sometimes we may need the data to do the processing. Of course, if you have processing engines inside the memory, then of course the question still becomes, why do you even need to move the data outside memory? Basically, doing this copying inside the memory is low latency, low bandwidth, no cache pollution, no unwanted data movement. And with simple mechanisms, you can actually improve performance by more than an order of magnitude and get to energy improvements that are close to 2 orders of magnitude. And the idea is very simple. This idea is applicable to emerging memory technologies like non-volatile memories as well. It's called row clone. You basically activate one row in memory, which brings the data into the row buffer. And then you activate the destination row, which takes the data from the row buffer to the destination row. By using this temporary buffer inside the memory, you can actually do a back-to-back activate. And with negligible hardware cost, you can achieve this copy. Again, I'm not going to go through the details of how you do it in other parts when the data resides in different portions of the memory chip. We do all of that in our papers. And in the end, the results are quite promising. You can see that significant performance and energy improvements are in store with very little change in hardware. In fact, recent work showed that you could actually do these techniques fool the memory device to actually do row clone like technique by reducing the activation to pre-charge latencies in the memory controller. By violating those latencies, you can even existing memories that are not designed specifically to do these operations reliably, they have the potential to do this. This basically shows that there's a proof of concept. Existing memories are capable of data movement and initialization. And that's the paper. And we actually answered a lot of questions after this paper, and these papers actually deal with different issues related to data movement and initialization. And you can take a look at these papers if you're interested. But more importantly, I think it's the mindset that matters. Basically, today, we have the mindset of designing a lot of heterogeneous accelerators. Why not think of memory as an accelerator as well? Why not put specialized computation capability, data movement, and initialization capability inside the memory? And I think if we think this way, we will enable a lot of interesting functions inside the memory, like that's starting to happen in 2021 or in 2019, also with UpMem, finally. Okay, very quickly, we can also do in-memory bulk bitwise operations at low cost using analog computation capability in DRAM. Activating multiple rows concurrently performs computation, and this leads to 30 to 60x performance energy improvements. Again, very significant, and you can read this paper. And new memory technologies are enable even more opportunities. There are many new technologies, clearly, memristors, resistive RAM, etc. They can operate on data with minimal movement because fundamentally they are non-volatile. DRAM is fundamentally volatile. As a result, in DRAM, you have to move the data just a little bit so that you can operate on it. But new memory technologies are even more promising. And also, new memory technologies enable matrix vector multiplication due to their three-dimensional structures. I believe that's very important and interesting to explore as well. How do we actually scale this matrix vector multiplication operations to very large arrays is going to be important in the future. So, and very quickly, this idea is also applicable to emerging memory technologies as well. But if you do a triple row activation in DRAM, you actually connect three cells in a row into the bit line. And basically, they share their charge. And due to the charge sharing principles, if at least two of those cells are charged, you get the charge state. If at least two of those cells are discharged, you get the discharge state at the end. And this is a bitwise majority function. It's actually a very nice function. You can convert your algorithms. You can rethink your algorithms such that they're expressed with bitwise majority as well as not. And as a result, you can write your algorithms from scratch in a completely different manner so that they can fit the substrate that can do bulk parallel operations. You can actually do this operation in 8 million or 10 million bits concurrently inside DRAM. And of course, the details I'm glossing over because there are implementation details that you need to solve to enable this. But basically, you can also do bitwise AND and bitwise OR operations by changing this Boolean equation. And we actually implement NOT as well. And if you actually do this, you can get significant performance improvements. These are end-to-end performance improvements in databases. You can get 4 to 12x performance improvements by doing these bulk bitwise operations in databases. And the performance improvement scales with the size of the database that you're dealing with. So I think this is a quite promising engine. And more recently, works have shown that you could actually do this in a limited manner in real DRAM chips. Even though the DRAM chip is not designed for this purpose, you can actually do this in DRAM chips by violating the timing parameters. And that's, again, a very good indicator that DRAM chips are fundamentally capable of doing this. And these are some papers that I'm flashing at you that talk about this bulk bitwise execution paradigm. And more recently, we've introduced a SIMDRAM framework that makes this more programmable. I don't have time to talk about this in detail, but this basically enables a path for defining an instruction, and the instruction gets implemented in the memory controller through some transformations, logic transformations, so that you can convert the instruction to majority and not immersion functions that are executed inside memory. And this is an end-to-end processing in memory framework. You can efficiently compute any complex operations in DRAM, as long as you can imagine them. It provides the ability to implement arbitrary operations, and it leads to minimal changes in the DRAM architecture because it uses the ambit substrate. And this is a busy slide, but you can see that you can generate majority and not logic, generate a sequence of DRAM commands, and associate them with the instruction. And when the instruction gets called from the software, the memory controller executes the microprogram that's associated with the instruction so that the memory executes the instruction. So this is an end-to-end programming model that can enable this sort of ideas to flourish in real systems. And this paper shows that there's significant benefit to it. I don't have the results over here, but we show that you can outperform existing GPUs and CPUs significantly. And you can actually enable other functions in memory. Security functions are actually important. We talked about security. If you're doing in-memory processing, you should also enable security functions like physical unclonable functions, true random number generation mechanisms, etc. I don't have time to talk about that, but these devices fundamentally have the capability to enable these security functions in a nice way. So we can essentially do a lot with the memory devices that we have today if we think a little bit differently about them. Right now, we're thinking about our memory devices as storage devices. They cannot do anything other than just storing data and providing the data when the master, meaning the processor, wants them. Why are we thinking that way? Because we're processor-centric. Let's break that mindset and think data-centric. These devices are there. They can also do computation. Let's enable them to do computation in the best ways we can so that we can have a much better overall system as opposed to just a processor-centric system that limits us in terms of energy efficiency, performance, security, and reliability. Let me talk about the second approach, again, relatively quickly. This is processing near memory. As I said, we're going to put the processor closer and closer and closer to the memory over here. And here, the benefit comes from specializing the processor for real applications like graph processing. And graph processing is really important. You can see that there are many systems, and scalable graph processing is very challenging today because it's not a computational problem. Again, the bottleneck is memory in graph processing. Basically, we have frequent random memory access and little amount of computation. And one opportunity, not the only opportunity, but one important opportunity is 3D stack logic and memory. And this is already happening. We have memory and logic layers in systems, and other three-dimensional technologies are under development. Basically, you have a logic layer that can be connected to the memory layers at high bandwidth and low latency and reasonably low energy. Can we put processing in the logic layer so that we can do graph processing or machine learning underneath so that we can have very fast access to data? And this is our example system for graph processing. This is a bit old right now because a lot of work's improved upon it, and they actually show that even better benefits are possible than what we have shown. That's great, actually. We release this work and other people actually can improve on it. And basically the idea over here is to have an interconnected set of 3D stacked memory plus logic chips that look like this with simple cores. So inside the logic layer, you have many simple cores distributed with a crossbar network or some sort of network. And each core is simple in order so that you don't violate the thermals. And basically the way computation is done on data is data doesn't move, but the computation, each core sends a message to another core to perform computation on the data that's housed by the memory stack on top of the core. Basically, we convert the data movement to instruction movement. And it turns out that's a scalable approach. And if you want to scale up the system, which you should, so that you can achieve actually very large capacities of memory, then you actually need to have a network of these devices that look like this. And you connect this to a host processor. This looks like a primitive GPU. GPUs were like this 20 years ago. They basically were, well, some GPUs are still like this, let's say, but they're non-cacheable, physically addressed. They have a different programming model underneath. And that's what we have over here. We have a different programming model for graph processing. It could be used for machine learning as well. It could be used for other applications as well. People have shown examples of that. You partition your graph and you move the data only when it's really absolutely needed. Almost all the time you move the instructions to the data so that the large amount of data doesn't move. Graph updates are performed locally in each node. And we show that this actually leads to significant benefits. And there's a lot of detail in the paper that I'm not going to cover here, but you need to be able to exploit the memory bandwidth using prefetching techniques. And this system looks nothing like existing systems. Basically, processing and memory are coupled with each other. As a result, you cannot distinguish processing and memory chips because processing and memory chips are together here. Whereas these are the traditional systems where processing and memory chips are separate. As a result, they're limited by the bandwidth that's provided by the main memory to the processor. Whereas here, we have huge amounts of bandwidth, as you can see, even by 2013-14's numbers. Okay, and as a result, by mapping your algorithm nicely to these devices, algorithm to device approach again, using a different programming model and by changing how you think about virtual or physical memory, on 5 graph processing algorithms, you get more than 13x performance improvement. Recent work improved upon what we did. They basically showed almost 100x performance improvement, actually, maybe even larger than 100x today, because there's been a lot of work on this topic over the course of last 6 years. And you actually get significant energy reduction. Again, recent work showed that these energy reductions go up to 2 orders of magnitude. Okay, and that's the paper. And this is just one example. And I think this is a very promising example. Let me quickly talk about a less specialized example, because we want to also be general purpose when we design processing in memory systems. And we did this study with Google a few years ago. And I already mentioned one result from this paper. Basically, we wanted to understand energy consumption in consumer devices. And we examined these 4 important workloads that we mentioned earlier. And we basically found out that data movement is huge cost in terms of energy. And we wanted to examine moving computation close to data to alleviate this data movement. The big challenge in small devices is that you have limited area and energy budget. So you need to be extremely careful in terms of what you offload and how you offload it. And we found out, very interestingly, that a significant fraction of the data movement often comes from very simple functions in applications. And we can design lightweight logic to implement these simple functions in memory. For example, small embedded low power core, like we showed in the tesseract approach, or small fixed function accelerators, or configurable logic, reconfigurable logic that can be morphed into fixed function accelerators and data flow engines. And I believe these are all important to have in a processing in memory system. And by doing this, you can achieve significant performance energy improvements, more than 2x. This sounds lower than 13x or 100x, but this is a step in the right direction. And also, this is more general purpose and much more simple than what we have discussed so far. And if you're interested, like TensorFlow has some of these functions, and more than 50% of the inference energy is spent on data movement. And more than 50% of that data movement is coming from two functions, mainly packing, unpacking, and quantization. And you can actually accelerate them and get significant performance energy improvements. And again, if you want to learn more detail, it's in our paper and the videos associated with the paper. And we also have really more recent papers on neural network models in Google. And we accelerate those neural network models. I'm not sure if I have those slides, but there was a paper that we published in PACT 2021 in September that looks at neural network models that are used in Google and the inference bottlenecks. And we basically show that today's neural network models are executed in large accelerators, and they're not data-centric. By adding data-centric accelerators and customizing them to the data movement patterns in the neural networks, you can actually improve energy efficiency and performance by more than 3x today. Again, I'm happy to send the links to people who are interested. So that's an example, another example of generalizing the idea. So we can generalize the idea to GPUs. I'm not going to go through all of these. I'm just going to flash some of these slides so that you see that it's actually general purpose to do this processing in near memory. You can accelerate linked data structures, which are tough to accelerate today. Dependent cache misses, accelerate run-ahead execution, prefetching mechanisms. You can do FPGA-based infrastructures, FPGA with high bandwidth memory to accelerate climate modeling. You can do approximate string matching near memory. You can do accelerate time series analysis, which is really important actually in many learning applications, as well as astronomy, for example, economics, etc. And to understand what you should accelerate and what you should not accelerate, we actually proposed a methodology. It's called the DAMOVE, Data Movement Methodology and Workloads. And if you're interested, the paper is online right now. I will maybe mention that one more time before we conclude this talk, which is coming soon. But basically, these are all examples of revisiting the entire stack. We revisit the entire stack and co-design across the hierarchy. And I believe we can get there step by step by doing this carefully. And this paper that I mentioned earlier shows a step-by-step approach as well. Okay, and these are some excerpts from the paper. And we also write other papers that are more focused on workload and programming ease, if you're interested in looking at them. As I said, this is happening already. This is a processing near memory engine, which contains, essentially, there are some DIMMs, PIM-enabled memory, that contain processors inside the memory banks. And this is what it looks like. Basically, inside the memory bank, you have a simple processor. The question is, how do you program that processor and how do you accelerate applications? And that's where these talks and papers describe how we did that. And we release some of the benchmarks, and we see very significant results with these benchmarks. Basically, this system, even though it's not optimized, it doesn't have the decades and decades of optimization that CPUs and GPUs have had. In many of the applications, it can outperform CPUs and GPUs. And you can find out and try it for yourself on the PRIM benchmarks that we have released. And this is the paper that talks about it. And these are the talks that you may want to look at. Again, FPGA-based systems, similar approaches. They can actually accelerate climate modeling and genomics, for example, by orders of magnitude compared to existing CPUs and GPUs. And what to accelerate and what not to accelerate, I think that's really important, the methodological question, because people will tackle these issues going into the future. And we actually answer this question empirically by analyzing hundreds of applications from distinct domains that you can see over here. Clearly, some of these are very important domains. All of these are very important domains, in my opinion. And we open source our benchmark suite and our tool chain, which essentially answers the question what you should accelerate and what you should not accelerate near memory. Again, I don't have detailed slides over here, and we're already out of time. I think I apologize for that, but hopefully this was interesting. You can take a look at these papers if you're interested. And again, as I said, industry is finally taking this much more seriously, and they've also already developed chips that can do machine learning acceleration or multiply and accumulate acceleration. I believe there's more to do, but clearly they've designed chips. These are the ISSCC and ISCA papers from Samsung. And they're also covered in our detailed lectures on processing in memory that you can find. And there are even later lectures from this semester. And if you're interested, we have a tutorial on PIM and memory-centric computing systems that I delivered at IEEE Electron Devices meeting last year. And this is a bit outdated, but you can find more information and longer information than what we could cover today. And I would definitely recommend looking at our more recent lectures from fall 2021 if you want to really get the cutting edge works and papers on this area. Okay, so this concludes the second and last part of my, let's say, lecture. We want to design computing architectures with minimal data moment, or more appropriately, minimal energy. We don't want to waste energy, and we don't want to do computation. We don't want to be on the wrong side of the computation versus communication equation in terms of energy and performance. And if you want to design fundamentally energy efficient architectures, we have to be data centric. We have to shift our mindset. And if you want to design fundamentally high performance architectures, again, we have to be data centric. So I would argue that data centric is the answer. This doesn't mean that processor centric goes away. Data centric needs to coexist with processor centric. And we've discussed ways of how to do that briefly in this talk, but heterogeneity is really the future. We want both processor centric and data centric, but we don't want everything to be data centric. We want to have data centric systems that can execute code in memory and communication structures, and we want to identify when we should enable them and exploit them. And I think fundamentally reliable, secure, and trustworthy and robust computing is also data centric, because a lot of the issues that we have with reliability and security is because we're exposing the data outside of the memory. If we minimize the exposure, perhaps we can be fundamentally secure. Okay, I've talked about these two. I'm not going to talk about low latency and architectures for machine learning, specialized architectures. Also, although I've given you examples, I'm happy to talk about this in a later future talk, for example, more specialized for those, or if people are interested, they can watch our lectures or email me. Now, if you have time, let me conclude quickly. I will, again, challenge this mindset. So a very famous architect said, architecture should be based upon principle, not upon precedent. Basically, precedent means what comes before. And I definitely agree with this. And this very famous architect is Frank Lloyd Wright. Clearly, no one can argue that he has revolutionized architecture. He did not design this. If he were just another architect, let's say, he would be designing something like this. This is precedent-based. It's not bad, okay. But he designed some fundamentally different architecture that has had a lot of impact. This is based on some principle called organic architecture. And this is falling water. If you have not visited, I would recommend you go and visit. This is literally on top of falling water. And principled architecture, the shift of mindset came at a cost. This is much more costly than this one. But once you actually pay the cost, you come to operate at a different level. And this operation at different level, I believe, justifies the cost over time. So clearly, moving to a new architecture like a data-centric architecture requires some cost, but that will take us to a different level. Over time, it will really amortize the energy and efficiency and performance issues that we have in our systems, plus security, reliability, safety issues. Now, this is another example. This is a train station that's precedent-based. Everybody can design it, every reasonable architect, let's say. This is very different from this train station. This is Bahnhof Stadelhofen in Zurich. This is Gare do Oriente, designed by the same architect who was principled, zoomorphic architecture. This is City of Arts and Sciences in Valencia. This is the Oculus in New York City. All of these came at a cost. This is actually extremely expensive, for example. New Yorkers complained for a long time about the expense that's put into this train station underneath. But this is really brought architecture to a different level, if you will. And this is Santiago Calatrava, the architect. And these are principles. These folks actually develop principles for architecture. Clearly, architecture is a different field. Computing is very different. But the question is, do we have overarching principles for computing systems today? And if you look at a system that I show you over here, we're violating every single principle that the system operates with. As far as we know, in terms of what our brain does today, this is very data-centric. This is very data-aware, and this is very data-driven, meaning computation is coupled with communication. Data, different semantic properties of data gets processed in heterogeneous engines in different places. And also, learning happens naturally. Today, it's not clear our systems are actually good imitators of the learning that happens in the brain. So I believe fundamentally better architectures require us to question and rethink the computing systems we design. And I think this is another blueprint for fundamentally better architectures. How do we make systems data-centric, data-driven, and data-aware? And a short paper that I wrote on this topic that was invited to date, you can find, it's only 3 pages plus references. And I believe it gives you a blueprint of this fundamentally better architectures from my perspective. And I believe we need to exploit many good principles. I've listed some of them here. I've talked about a lot of them, even though I may not have pointed out everything that is pointed out here. But more than anything else, I believe we need open minds so that we can change the mindset that unfortunately is limiting us today. Okay, to conclude, I believe it's high time to design principled computing architectures to achieve the highest security, performance, and efficiency. We need to discover the design principles for fundamentally secure and reliable, trustworthy and robust computer architectures. We need to design complete systems to be balanced and energy efficient. In other words, data-centric and memory-centric and low latency. And we need to enable new platforms for critically important applications for our future, like genomics, medicine, health, AI, and machine learning. This can, hopefully I've given you many examples, this can lead to orders of magnitude improvements. And I believe even more than what I've given you, because this is just initial research, right? I believe with collective focus on these important problems, we can actually get even more magnitude improvements. We can enable new applications and computing platforms that we cannot even imagine today, like the genomics platforms and who knows what else. Hopefully this can enable us to better understand the nature and also better build principles based on nature that are more compatible with nature. I believe we're violating the principles of nature in the design of our computing systems today. And who knows what else again. I believe the future is very bright, even though we have a lot of challenges. If we think out of the box, think with a new mindset, we can think across the stack, algorithms to devices. We can, and also think about adoption, we can get there step by step. And again, I will point you to some papers, as well as works from my group, as well as these tutorials. And I will acknowledge people who fund us. Please keep funding us. This research is not possible with people who carry out the research, as well as the funding that enables those people to carry out the research. And I will acknowledge my students and postdocs, as well as collaborators who have done a lot of the work that I have discussed. And I will invite you to read our newsletters if you're interested. And that brings me to the end of the talk. Thank you very much for giving me the opportunity to discuss with you. I have time to answer as many questions as you have. I know we're over time, but I'm happy to answer any questions. I have time. Thank you.
Marhaba, Professor Noor.
Marhaba, Ankit.
Thank you so much. So yeah, there are lots of questions. I guess we may not have so much time to take them all. I promise I will have them sent across to you. So let me get started quickly. So the first question from Supratim is that, so the trend that you mentioned about the tesseract or the graph processing module. So does this trend mean that the ratio of logic to memory is increasing the amount of silicon in the system? Are we putting in more hardware to achieve the same thing?
Yeah, so that's a good question. I mean, not in the system that we examined, because there's one logic layer and many memory layers, but certainly it could. This sort of system where logic and memory are more coupled with each other can enable increasing the logic in the system as well, so that we can do much more computation, because we have access to a lot more bandwidth at lower latencies. So we need more elements to actually take advantage of that bandwidth at low latencies. So I would argue that we did not do anything special to increase the logic in our particular system, but the point is very well taken. And I think going forward, if you have more data-centric systems, we can actually enable our logic to be more efficient, as well as we can have more logic to take advantage of that data centricity.
Sure. So the next follow-up question is, if we move compute to where data is and distribute it widely, won't it increase the overhead of communication to collate the results together?
Yeah, so that's also an interesting question. So it certainly depends on the application, but yeah, it certainly depends on the application. For example, if your application today fits in a multiprocessor, a single chip, and the caches, that application is a great fit for a multi-core system potentially, right? You don't want to necessarily move that application or any portion of it on the memory side. But there are many applications today where that's not true. We're mainly bottlenecked by main memory and storage. And in many applications, collating the results is not your bottleneck today. So I believe that question is very application dependent. And I believe if you make the right choice, you will not run into the situation that by moving something to the data-centric side, you will increase the communication in the system. You should not do that, basically. And that's why we develop these methodologies, techniques to help programmers and designers to decide when to do this when to do this near data processing and when not to do this data processing.
Sure. So next question is from Archit. So you had talked about providing a reliable and secure and safe system, and you extensively talked about the Rowhammer and other things also. So he actually is seeking your opinion. What do you think about using blockchain technology to provide security, reliability, and safety?
I think that's a fun question to think about. I mean, clearly blockchain and that sort of like distributed ledger type of applications are very promising. I mean, I'm not sure how general purpose they could be to enable our security, safety, and reliability in every part, right? Because that's not it's not a silver bullet. It may be useful for financial applications that needs to be proven, but I don't know how to solve, for example, any security problem that we have in our systems using blockchain. If someone actually comes up with a way of doing that, I think that's possible. Maybe I'm misinterpreting the question. That's one way of interpreting the question. I don't think blockchain technology is general enough to solve all of our security problems. And then there's another aspect, I think. Maybe this is thinking about, okay, blockchain, is it good enough for our systems, even in the financial domain, for example? Then I would argue that blockchain is certainly interesting, but it exacerbates some of the bottlenecks that I've been talking about, right? There's a lot of data movement, there's a lot of communication that you need to do. And I think that needs to be seriously examined. I believe blockchain technology can benefit from near data processing, a lot of the approaches that we have discussed. But I think some of the distributed aspects of blockchain also needs to be seriously examined so that we do not really exacerbate some other issues like extreme energy efficiency, energy cost for a particular yet really important application. I don't know if there's enough data in the field that convincingly argues that the security benefits and privacy benefits of blockchain in the financial domain like justifies the energy cost of blockchain. I'm actually skeptical, even with these huge machine learning models that we train, right? We have these huge machine learning models that are out there today. We train them for, let's say, for a month or so on extremely power hungry GPUs and data centers. Does it really make sense to do that for the purposes that they're being used today?
Sure. So let me take one final question. I have a few more. I'll send it across to you offline. So like the way we have the VLIW hardware where the compiler actually takes a look at what all instructions can be carried out in parallel and basically solving some things upfront before the execution even starts. So can actually compilers look at, so like in your talk, you mentioned that most of the time we are actually loading the data. The compute is really running for a very short period of time. Most of the time we are loading caches and memory. Can the compiler actually foresee that, have a pipeline built in place so that the data is ready when the processor actually needs it, so that it doesn't have to be waiting for the cache to be filled or something like that?
So that's a great question. I think, I mean, there are multiple answers to this. VLIW has not been extremely successful commercially because it had too much reliance on the compiler. But I would say that in specialized domains, if you can actually enable the compiler to analyze your code really well, using, for example, restrictions in your programming language, and the programmer enables some guidance to the compiler as to what it can parallelize, what it cannot parallelize, and the structure of the program is expressed nicely, such that the compiler can glean a lot from that structure. I believe compiler has a huge role to play, actually. And this happens especially in domain-specific architectures, for example. Machine learning is a great example. I believe compiler, through a good programming model, compiler can extract a lot of information and enable that sort of communication and pipelining, streaming, etc., across the computation units, such that you minimize the data movement overheads, etc. But I believe all of those ideas are perhaps even better applicable to data-centric systems as well. So I'm not suggesting that, okay, we should do it for processing-centric systems, but I believe we should look at compilers for data-centric architectures. But we should be careful, because if we don't give enough information to the compiler, at the doing this at the general purpose scale is not easy, as many companies have found out over decades and decades. But if we give enough information to the compiler, I believe there's a lot of opportunity.
Sure. Well, I'll hold on to the rest of the questions since we are sort of over time. And thank you so much, Professor Onur. Over to you, Anvit.
Okay, thank you very much, Ankit, and have a good evening.
You too.
Thank you so much, Professor, for that wonderful lecture. I think it just was like every slide had some new information. Every slide had something which everybody was looking for. And I think after every section, we were like a light bulb moment. Oh, yes, this is something which everybody's thinking about. So once again, thank you for sparing the time and making time here at the IEEE Data and Storage Symposium Winter Edition.
Thank you very much, Anmit.
With that, I would now like to invite on the screens Chengappa MR for the closing notes for the Data and Storage Symposium. Chengappa, over to you.
Well, yeah, thank you, Anvit. And I deem it an honor and a privilege to propose the vote of thanks on this special occasion of winter edition of IEEE Data and Storage Symposium. On behalf of IEEE Bangalore Section and Huwaei India, I would like to thank our speakers and panelists who had graced us on the symposium across the globe, sharing their insights and on the latest and the greatest developments in the data and storage domain and technologies, justifying the theme of this winter edition. This has been the third edition of Data and Storage Symposium, and IEEE Bangalore section well understands that there is a desire for fast data-driven apps, and computing remains to be fundamental ask. To a certain extent, scalable AI lends a helping hand, but that needs higher performance infrastructures to support it. Data and storage technologies, therefore, are increasingly playing a pivotal role in its enablement. On these lines, IEEE Bangalore section aims to create a special interest group on data and storage systems. And this proposed special interest group would bring together industry and academic professionals working on various aspects of data and storage management technologies, and create an ecosystem of technical exchange and ideas and thoughts and transformation dissemination. Again, to conclude, an event of this dimension cannot happen overnight. The wheels for this winter edition started rolling months in advance. We have been fortunate enough to have been backed up by a team of very motivated and committed set of volunteers from Huwaei India and IEEE Bangalore section. I cannot thank everyone enough for the involvement that they have shown, and the willingness that they have expressed to take on this completion of the task beyond their comfort zone. I also envision that the proposed special interest group would plan to conduct highly focused and curated symposiums and technical conferences on data and storage systems starting next year. So please stay tuned. All the registered participant would be receiving the information on how you can collaborate on the special interest group. With this, I would hand over the virtual podium back to Anvit.
Thank you once again, Chengappa, and that's it from us here at the IEEE Data and Storage Symposium Winter Edition, brought to you by IEEE Bangalore Section in association with Huawei Technologies India Private Limited. It has been my great pleasure hosting this event and also a very big learning experience. I hope this symposium has enriched your knowledge and given you some food for thought. With that, this is me, Anvit KS, signing off. See you at IEEE Data and Storage Summit 2022.